Good morning, everyone. Good morning, good morning. Welcome back again to your Unacademy NEET English channel. I hope you guys are doing great. So people, quickly let me know in the chats if all of you can hear me. If I'm perfectly audible and visible to every one of you. Good morning, everyone. Good morning, and welcome back. So what's up? How are you all doing? So people, first let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you or not. Let me know quickly in the chats. I think, yes, I am perfectly audible, visible. Yeah, is that? All right, so as you all must be knowing, today we are going to start the bounce back series, wherein we are going to take like mega marathons and we shall be completing your whole syllabus in just 15 sessions, the entire syllabus of physics, chemistry, as well as biology. And today is going to be the first session of this particular bounce back 2.0 series. My dear students, one thing I would want from all of you. What exactly is that? Since you know, these mega marathons, they are going to run for like 10, 12 hours. So for example, right now I'm starting, I think I'll be ending at 11 in the night. So for complete 12 hours, I'll be teaching here. One thing I would want from all of you, that is the consistency. I would want you guys to be with me till the end of the session. And let me tell you, in the today's session, what exactly we are going to do. We are going to do the complete physical chemistry of your class 12th. Okay? It is not only just going to be the questions, not only just going to be the theory, it's going to be your theory as well as the question practice in the today's session. Okay? And at the same time, I'll try to start from the basics only. I'll try to start from the scratch only. One thing which you need to do, my dear students, you just need to take a note of every single thing. Whatever things I'll be mentioning on the screen, I would want you guys to take a note of every single thing and try to make the short notes with me. Do not try to write the notes in the elaborated form. Do not do that. I would want you guys to make the short notes exactly with me. Okay? So your chapter should be completed in like 5 to 6 pages. In such a manner, you'll be making your notes in this particular bounce back series. Okay? One thing which I'm telling you, every single thing will be discussed in detail. You need not to worry about anything. I'm not going to skip a single topic also. Okay? Do not worry about that. So, are you all going to be with me till the end? Are you all going to be with me till the end? Quickly, let me know in the chats. Yes, even JEE aspirants can also watch it. Even JEE aspirants can watch this particular series. Don't worry. Guys, it does not matter where you are studying, whether you are studying on this platform, on some other platform, from offline classes, does not matter. Only thing matters to you is that is the content. Okay? Only thing matters to you is whether you are getting benefited or not. That's the only thing that matters. Otherwise, does not matter. Okay? All the other things. Perfect. Just give me a second. Let me fix certain things and we shall be starting. And also in between, people, I'll be giving you the breaks as well. Do not worry. After every like 2.5, 3 hours, I'll be giving you like 15, 20 minutes breaks so that you can refresh, have some food also. Okay? Do not worry. Even you can consult this lecture for boards also. This is going to be super beneficial for boards also. Okay? Because every single thing I'll be covering here. As I told you already, no need to worry about any single thing. Perfect. Chalo, should we start the session? All ready? All ready, guys? I would want you guys to light up the chats with the fire emojis quick. I want you guys to light up the chats quick. I hope you guys remember the schedule which already I have shared with you. If not, let's have a look on the schedule also. See guys, today it's going to be the class 12th complete physical chemistry. Tomorrow it's going to be off, no live session. Day after tomorrow it's going to be complete class 12th physics part 1, right? After that it's going to be complete zoology of class 12th, then complete inorganic chemistry of class 12th. Then again I'll be coming with complete class 11th inorganic, similarly complete class 11th physical chemistry. Similarly, Yavar will be coming up with a complete class 11th physics, etc., etc. So in just 15 sessions, your whole syllabus of your class 11th as well as class 12th of your physics, chemistry, and biology, every single thing will be done. Perfect. So I think without wasting a lot of your time, let's get going. Let's get started with the today's session. So people, what all things we are going to cover in the today's session? Let's have a look on that first. Okay, let's have a look on certain things. What all chapters we are going to cover? Your class 12th physical chemistry, it consists of 3 chapters. You must be knowing about that. Your class 12th physical chemistry consists of 3 chapters. And those 3 chapters are going to be, one is going to be your chemical kinetics. The other one is going to be your electrochemistry. Another one is going to be the chapter solution. These are the 3 chapters which I shall be covering in the today's session. And these 3 chapters will be covered, I would say, in the detailed way. These 3 chapters will be covered in the detailed manner. What does that mean? That means your theory, all the theory and all the different types of problems which can be asked from these chapters, every single thing will be covered, including the PYQs as well. Okay? That's why I told you in the beginning only, it is not just the revision, it's going to be the detailed mega marathons of these chapters which we have come up with. Perfect. Should we start then? Should we start, guys? All ready? Quickly, let me know in the chats. All ready? Yes, as I told you already, you can watch this particular session, this particular series for your JEE preparation as well, for your boards as well, for your NEET preparation as well, does not matter, right? Because every single thing is included in the session. Tell me quickly in the chats, all ready for the session? Perfect, guys. Perfect. So guys, the first chapter which I shall be starting today, that is going to be your chemical kinetics. This is going to be our first chapter that we shall be completing in the today's session. So let's get going. Let's get started with the chapter chemical kinetics. First of all, if you ask me what this chemical kinetics is all about, what all things we have to study in this particular chapter. My dear students, as per the definition of chemical kinetics is concerned, in chemical kinetics, we deal with the rates of the reactions, number 1. We deal with the rates of the reactions. We deal with the factors affecting the rate, and at the same time, we deal with the mechanisms of the reaction as well. So these are, broadly speaking, these are the 3 things which we are going to discuss in this particular chapter, right? That is your chemical kinetics. So chemical kinetics, it deals with the rates of the reaction. Chemical kinetics is going to let you know why some reactions occur slowly, why some reactions occur fastly, right? Chemical kinetics, in this particular thing, we are going to discuss about the factors which affect the rates of the reactions. We are going to discuss about the mechanisms of the reaction as well. So these are technically the three things which are there in the chapter chemical kinetics. Okay. So the first thing which we are going to start here, what is that going to be? That is going to be some basic things. Some basic things which you must know before starting the chapter. My dear students, I'm going to mention a statement over here. From that particular statement, we shall be starting this particular chapter. And what is that statement all about? See, I'm going to write a statement. The statement is simple like this. As the reaction starts, the concentration of reactants, as the reaction starts, the concentration of reactants decreases with time, and the concentration of products increases with time. This is the first and the most important statement with which we shall be starting this particular chapter. As the reaction starts, concentration of reactants, it keeps on decreasing with time. Concentration of products, it keeps on increasing with time. What does that mean? Let's have a look, guys. First of all, if you are not familiar with the term concentration, what concentration exactly is all about? First of all, concentration we represent with square brackets, or you can represent it with C as well. And how do we define concentration? Concentration is simply defined as moles per unit volume. Moles per unit volume. For example, my dear students, let's say I'm writing concentration of reactant. What does that mean? Concentration of reactant means number of moles of reactants divided by volume of the vessel, volume of the reaction vessel in liters. As simple as that. For example, if I define concentration of products, what is concentration of products? Concentration of products will be defined as number of moles of products divided by volume of the vessel in liters. Now, I believe all of you would be familiar about one thing. All of you would be knowing about one thing. What is that? My dear students, you would have studied by now. When the reaction starts, number of moles of reactants, that keeps on decreasing with time. As the reaction starts, number of moles of reactants keeps on decreasing with time. And number of moles of products, that keeps on increasing with time. Now, it's very simple. It's very simple. Since I told you, as the reaction starts, number of moles of reactants, that decreases with time. If number of moles of reactants decreases with time, that automatically tells you concentration of reactant also decreases with time, because both are directly proportional to each other. As simple as that. Similarly, as I told you, as the reaction starts, concentration, leave concentration aside, as the reaction starts, number of moles of products, that increase with time. And if number of moles of products increases with time, therefore concentration of product increases with time as well. So just two statements which I would want you guys to remember. Number one, when the reaction starts, number of moles of reactants, that keeps on decreasing with time. Therefore, concentration of reactant also decreases with time. Number one. Number two, number of moles of products, that increase with time. Therefore, concentration of product also increases with time. And my dear students, if you want to understand it graphically, you can plot two graphs as well for the same. Let's say I'm plotting the first graph as concentration versus time. Concentration versus time. My dear students, as the time goes on, the concentration of reactants, that decreases with time. So this particular graph is basically valid for the reactants. Similarly, if you want to plot the graph for the products, you can plot the graph for the products too. I'll be writing concentration versus time. And for the products, as I told you, with time, the concentration of product, it increases with time. So this particular graph is valid for the products. Okay, so these are the two statements which I would want you guys to remember from now onwards. As the reaction starts, concentration as well as the moles of reactants, they decrease with time. As the reaction starts, concentration as well as the moles of products, that increases with time. So let me know once in the chats if this is super clear to everyone or not. Quickly, with a yes or no. Quickly with a yes or no. Everyone, people. Everyone in the chats. Everyone in the chats. Yeah? Perfect. Perfect. Guys, just a second. Just a second. Just a second. Okay. Now, let's move on to our first topic. What is that first topic? The first topic from which the question comes. Okay? The first topic from which the question comes. What is that? That is rate of the reaction. Rate of the reaction as per the stoichiometry. This is the first topic from which you get the question when it comes to your NEET examination, when it comes to your boards examination, when it comes to your JEE examination as well. Okay? Now, what exactly it means? Rate of reaction as per stoichiometry. Try to understand, people, what exactly it means. For example, imagine that I'm taking a balanced chemical equation. N1A plus N2B, it gives N3C plus N4D. Imagine this is a balanced chemical equation. Imagine this is a balanced chemical equation. And in this balanced chemical equation, as you can see, this N1, N2, N3, and N4. What exactly these are? These are the stoichiometric coefficients of reactants and products. I would say this N1, N2, N3, and N4. These are the respective stoichiometric coefficients of reactants and products. Now, my dear students, as I told you a few minutes back, as the reaction starts, what happens to the concentration of reactants? Concentration of reactants decrease with time. Concentration of products increase with time. Or I can say something like this: as the reaction starts, reactants disappear with time. Reactants keep on disappearing with time. Reactants keep on consuming with time. Similarly, if you talk about products, products keeps on appearing with time. Okay? Reactants disappear with time and products appear with time. So, my dear students, what exactly I want to do? I want to define two terms here. I want to define two terms here. The first term is what I call as rate of disappearance. Rate of disappearance. As I told you, your reactants disappear with time. So, rate of disappearance, I am going to define for what? I am going to define for reactants. And my first reactant over here is reactant A. So, I would say rate of disappearance of A. Rate of disappearance of A. This is going to be my first term that I am going to define over here. Rate of disappearance of A. My dear students, rate of disappearance of A. How do I represent it mathematically? How do I denote it? First of all, the term here comes disappearance. And disappearance term, I am going to denote with a minus sign. Disappearance term, I will be denoting with a minus sign. Right? So, minus. Now, I'll be writing change in the concentration of A. Change in the concentration of A divided by time interval delta T. Divided by time interval delta T. This particular term, it gives me the rate of disappearance of A. This particular term, it gives me the idea about the rate with which A disappears with time. Okay. Similarly, if I want to define the rate of disappearance of B, if I want to define the rate of disappearance of what? Rate of disappearance of B. How do I write it? Since I'm using the term disappearance, I'm writing the term disappearance. So I'll be starting with minus sign again, right? Minus. Now I'll be writing change in the concentration of B divided by time interval delta T. This term gives me the rate of disappearance of B. This term gives me the rate of disappearance of B. Similarly, my dear students, if I would want to write the rate of appearance, for example, I want to write the rate of appearance. Rate of appearance. Appearance is the term which is defined for products, right? So I can say rate of appearance of C, for example. How do I write it? In order to represent the rate of appearance, I'll be starting with a plus sign. Now I'll be writing change in the concentration of C divided by time interval delta T. This particular term gives me the rate of appearance of C. And my dear students, if I would want to write the rate of appearance of D, I can do that as well. Rate of appearance of D, how exactly we are going to write it? Again, we'll be starting with a plus sign. Then I'll be writing change in the concentration of D divided by time interval delta T. This is how you are going to write the rate of appearance of D as well. So here I define two terms. One is rate of disappearance, one is rate of appearance. Disappearance I defined for reactants, appearance I defined for products. Whenever I need to write rate of disappearance, I'll be starting with the minus sign. Whenever I need to write rate of appearance, I'll be starting with the plus sign. Am I clear with this? Am I clear with this, people? Everyone? Everyone in the charts, quickly. Okay? Now, people, try to understand few more things. Try to understand few more things. What are those few more things? Again, pretty much simple. See, I'm again writing a balanced chemical equation as N1A plus N2B. It gives N3C plus N4D. This is again your balanced chemical equation, right? Now, people, what exactly I'm going to define? First, I defined rate of disappearance. Then I defined rate of appearance. Now I'm going to define one more term. What is that? That's what I call as the rate of the reaction. Rate of the reaction. How exactly we define rate of reaction? Remember what I'm going to say. Rate of reaction is defined as rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of a reactant or product. How exactly? How exactly we can understand this? Rate of the reaction is nothing but rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of reactant product. My dear students, for example, this is the reaction. Okay? A and B, they are the reactants. C and D, they are the products. A and B disappears with time. C and D appears with time. Now, people, for example, I want to define rate of this particular reaction. Let me tell you, rate of the reaction I can define either with respect to A, or I can define with respect to B, or I can define with respect to C, or I can define with respect to D. For example, I'm defining rate of reaction with respect to A. If I'm defining rate of reaction with respect to A, then I'll be writing rate of disappearance of what? Rate of disappearance of A divided by stoichiometric coefficient of A. How do I write rate of disappearance of A? Rate of disappearance of A is going to be minus delta A divided by delta T, whole divided by stoichiometric coefficient of A is nothing but N1. So overall, I'll be writing it as minus 1 divided by N1, change in the concentration of A divided by time interval delta T. This particular term, it is going to give me the overall rate of the reaction. Okay. Number two. If I want to calculate rate of reaction with respect to B, I can do that as well. My dear students, rate of reaction with respect to B. B is again the reactant. So I'll be writing rate of disappearance of B divided by stoichiometric coefficient of B. How do I write rate of disappearance of B? Rate of disappearance of B is minus change in the concentration of B divided by time interval, all divided by stoichiometric coefficient of B, that is N2. So finally, I'll be writing it as minus 1 divided by N2, change in the concentration of B divided by time interval. This particular term also is going to give me the rate of the reaction, but the rate of the reaction I'll be getting over here in terms of B. Similarly, if you want to define the rate of reaction in terms of C, you can do that as well. I'll say rate of reaction in terms of what? In terms of C. My dear students, C is your product here. C is your product here. So rate of reaction in terms of C is going to be rate of appearance of what? Rate of appearance of C divided by stoichiometric coefficient of C. What is the rate? What is the rate of appearance of C? That is plus change in the concentration of C divided by time interval, whole divided by stoichiometric coefficient of C is nothing but N3. So overall, I'll be writing it as plus 1 divided by N3, change in the concentration of C divided by time interval delta T. This term also is going to give me the rate of reaction only, right? Or at the end, you can write rate of reaction with respect to D as well. Let me write that too. Rate of reaction with respect to what? With respect to D. So you'll be writing a rate of appearance of D divided by stoichiometric coefficient of D. So plus change in the concentration of D divided by time interval, whole divided by stoichiometric coefficient, that is your N4. So it's going to be plus 1 divided by N4, change in the concentration of D divided by time interval delta T. So all these terms which I have kept in the box, all these terms which I have kept in the box. So my dear students, all these terms, they are giving you what? They are giving you the rate of the reaction, be it in terms of A or in terms of B or in terms of C or in terms of D. Every single term is going to give you the rate of the reaction only, right? And let me tell you the value of the rate of reaction which you get by solving this particular term. Same rate of reaction you'll be getting by solving this particular term. Same rate of reaction you'll be getting by solving this particular term. Same rate of reaction you'll be getting by solving this particular term. Because everywhere I have kept the time interval as the same. Am I clear with this? Am I clear with this, people? Quickly in the chats. Am I clear with this? Say yes or no quickly. I do not want your chats to stop at all in the today's session. They should continuously run. They should continuously run. Perfect. All right. So people, for example, I'm giving you a simple reaction like this. N2 gas plus 3 times H2 gas, it gives 2 times NH3 gas. Okay? 2 times NH3 gas. Okay, before moving on into this particular question, let me tell you one simple thing again. I told you all these terms, what do they give us? They give us the rate of the reaction. So finally, I can say something like this. I can say rate of the reaction can be written as minus 1 divided by N1, change in the concentration of A divided by time interval, which is equal to minus 1 divided by N2, change in the concentration of B divided by time interval, which also equal to plus 1 divided by N3, change in the concentration of C divided by time interval, which also equal to plus 1 divided by N4, change in the concentration of D divided by time interval. And this particular equation, which I mentioned over here, this is something which you call as the differential form of rate. You call this particular equation as the differential form of what? Differential form of rate. Okay. Now, this was the question which was asked in your NEET 2021. You were given with this particular equation and you were supposed to write the differential form of rate for this particular equation. Who is this spammer? Just a second. Spammers should know that I have got the access of this particular channel. I have got the access to block you as well. So I blocked one. Okay. Don't worry. So whosoever has come for the spamming stuff, don't worry. I'll be taking care of that as well. Yeah. Perfect. Is that clear? All right. So people, can you solve this particular question? Can you write the differential form of rate for this? Can you form the differential form of rate for this? I believe you should be able to. I believe you should be able to. How exactly you are going to do? See, I'll write rate of reaction is equal. Rate of reaction is equal. With respect to N2, N2 is the reactant. I'll be starting with minus sign. 1 divided by stoichiometric coefficient is 1. Change in the concentration of N2 divided by time interval delta T, which is also equal. Write it with respect to H2. H2 is again the reactant, so start with minus sign. 1 by stoichiometric coefficient. Change in the concentration of H2 divided by time interval delta T. Write it with respect to NH3. NH3 is the product. So I'll be starting with plus sign. Plus 1 divided by stoichiometric coefficient. Change in the concentration of NH3 divided by time interval delta T. This is basically your differential form of rate for the equation that I had given to you. Okay? I believe I'm clear with this. Okay? The handwritten notes of this particular session you'll be getting on my Telegram. If you are not the part of Telegram channel, just be the part of Telegram channel, which is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official is the Telegram channel name on which I shall be sharing the handwritten PDF of the today's session. Okay? Perfect. So guys, I believe every single thing is clear till here. Now let me write one more thing. One more thing. Remember, for a homogeneous gaseous phase reaction. For the homogeneous gaseous phase reaction, let me tell you, rate of the reaction can be expressed in terms of rate of the reaction can be expressed in terms of pressure as well. What does that mean? See guys, understand. Imagine that I've got the reaction like this. N1A gas plus N2B gas, it gives N3C gas plus N4D gas. If you look at this particular reaction, do you see every single reactant and product is in gaseous state? Yes. Every single reactant and product is in gaseous state. So I'll be calling this particular reaction as the homogeneous reaction. It is the homogeneous gaseous phase reaction. Because every single reactant and product over here is in gaseous phase. So this reaction is your homogeneous gaseous phase reaction. Okay? This reaction is your homogeneous gaseous phase reaction. Now, my dear students, in case of the gaseous phase reactions, let me tell you, rate can be expressed in terms of pressure as well. So, I can say something like this. R is equal to, rate of the reaction is equal to, in terms of A, I'll be writing minus 1 divided by N1, Then I used to write change in the concentration of A. But here I'll write change in the pressure of A divided by time interval. Similarly, in terms of B, minus 1 divided by N2, it's going to be change in the pressure of what? What should I write? Change in the pressure of B divided by time interval. Similarly, in terms of C, it's going to be plus 1 divided by N3. It's going to be change in what? Change in the pressure of C divided by time interval. And at the same time, I'll be writing plus 1 divided by N4, change in the pressure of D divided by time interval delta T. So remember, when it comes to the gaseous phase reactions, for the gaseous phase reactions, rate can be expressed in terms of pressure as well. Rate can be expressed in terms of pressure as well. Okay? Rate can be expressed in terms of pressure as well. So, one thing which you need to know. Over here, I defined rate in terms of concentration. And right here, I defined rate in terms of pressure. Okay? So, remember one simple thing. My dear students, whenever in a question, you are supposed to calculate rate in moles, liter inverse, second inverse. Whenever in a reaction, you are supposed to calculate rate in terms of moles, liter inverse, second inverse. You'll be taking one of these terms and solve them. Whenever you are supposed to calculate rate in terms of, for example, atmosphere second inverse, bar second inverse, atmosphere minute inverse, atmosphere hour inverse, right? So in short, here you have got the unit of pressure, here you have got the unit of time. Whenever rate is to be expressed in unit like this, then use one of these terms over here and get the rate of the reaction. So two things. Rate of reaction in terms of moles per liter per second, take these terms and solve the question. If rate is to be calculated in terms of a unit like this, right, then take these terms. Out of these terms, you can take any term, solve the term, and get the rate of the reaction. I believe I'm clear with this. Okay? I believe I'm clear with this. For example, let's have a look on certain questions which will make all these things clear to you. This is the first question on your screen. This is the first question on your screen, people. If the rate of the appearance of O2 is 0.5 moles per liter per second, then calculate the rate of disappearance of N2O5. Rate of disappearance of N2O5. Right? Okay. See, guys. Understand properly. This is the reaction which is given to us. The reaction is given to us in the balanced format. 2 times N2O5 gives 2 times N2O4 plus O2. This is the reaction that's given to me. As per the question, look at the first statement. If the rate of appearance of O2 is given. Rate of appearance of O2 is given. How do you write rate of appearance of O2? Rate of appearance of O2 can be written as plus delta O2 divided by delta T. This is what you call as rate of appearance of O2. And as per the question is concerned, it is nothing but 0.5 moles liter inverse second inverse. This is your rate of appearance of O2. That's given to me. This is your rate of appearance of O2 that's given to me. What am I supposed to calculate? Rate of disappearance of N2O5. Rate of disappearance of N2O5. How do we write rate of disappearance of N2O5? You know it already. Minus change in the concentration of N2O5 divided by delta T. This is what I call as the rate of disappearance of N2O5. I need to calculate its value. How exactly am I going to do it? My dear students, all these questions are solved with the help of the differential form of rate. Okay? How exactly? See, let me write differential form of rate for this particular reaction. I'll be writing rate of reaction is equal in terms of N2O5. I'll start with minus sign. 1 divided by stoichiometric coefficient is 2. Okay? Change in the concentration of N2O5 divided by delta T. This is your rate of reaction as per N2O5 is equal to. Write the differential form of rate in terms of N2O4. How you are going to write? Plus 1 divided by 2. Change in the concentration of N2O4 divided by delta T. Rate of reaction in terms of O2 plus 1 divided by 1. Change in the concentration of O2 divided by delta T, right? So this is your differential form of rate. Now people just do one thing. In the differential form of rate, just try to equate this particular term with this particular term. Just try to equate these two terms. When you equate these two terms, what do we get? I get delta N2O5 divided by delta T is equal to, it's going to be plus delta, sorry, this minus 1 by 2 as well. Here you have got minus 1 divided by 2. Change in the concentration of N2O5 divided by time interval is equal to plus delta O2 divided by delta T. Or I can say something like this, minus delta of N2O5 divided by delta T is equal to, take this 2 over here, so it's 2 times plus delta O2 divided by delta T, right? So this is going to be 2 times. What is delta O2 divided by delta T? My dear students, delta O2 divided by delta T is given to me as 0.5, right? So 2 multiplied by 0.5, the value comes out to be 1. This is going to be mole liter inverse second inverse. What is this 1 mole per liter per second? If you look carefully, 1 mole per liter per second is nothing but minus delta N2O5 by delta T, which is what you call as the rate of disappearance of N2O5. That is something I was supposed to calculate as per the question. Am I clear to everyone, people? Let me know in the chats quick. Am I clear to everyone quickly? Quickly in the chats. Everyone. Perfect. All right, let's try to solve one more question. Look at this question, guys. As far as this particular question is concerned, as you can see carefully, you're given with a reaction. The reaction is 2 times NH3 gives N2 plus 3 times H2. This is the reaction that's given. Calculate the rate of the reaction in the interval 5 to 15 seconds. I want to calculate rate of reaction in the interval 5 to 15 seconds. This interval, 5 to 15 seconds. First of all, this interval 5 to 15 seconds, this time interval is basically 10 seconds. 5 to 15 means 10 seconds. Okay. So in this particular time interval, I want to calculate rate of reaction. If you look at the graph, first of all, my dear students, with time, concentration is decreasing. With time, concentration is decreasing. So this particular graph is valid for the reactant. This particular graph is valid for the reactant. Because you know, with time, concentration of reactant decreases. And reactant here is NH3. So I would say this particular graph is valid for which particular substance? It is valid for NH3. This is the graph given for NH3. Okay. Now guys, if this is the graph given for NH3, what do I need to calculate? I need to calculate rate of this particular reaction. Let's calculate rate of the reaction with respect to NH3. So what do I write? I'll start with minus sign. 1 divided by 2. Change in the concentration of NH3 divided by time interval delta T. So it's going to be simply minus 1 by 2. Change in the concentration of NH3. Check in this particular time interval, what is the change in the concentration of NH3? Say guys, initial concentration of NH3 is 0.6 at 5 seconds. Final concentration of NH3 is 0.2 at 15 seconds. So I'll write minus 1 by 2. Change in the concentration of NH3, which is final concentration of NH3 minus initial concentration divided by time interval is how much? 10 seconds. Just solve this particular term and get the answer in moles liter inverse second inverse. Clear with this one? Clear with this one, people? Yeah? These sort of questions you should be easily solving from now on. What exactly you need to do? You just need to write the differential form of rate. Once you get the differential form of rate, and you are done. And you are done. And you are done. For example, look at this particular question. Look at this particular question, guys. You are given with the reaction. Find the relation between K1, K2 and K3 and some kind of data is given to us over here. Okay. Some kind of data is given. Have a look. The reaction is N2O5 gas. It gives us 2 times NO2 plus half of O2. This is the reaction that's given to me. Okay. What you need to do in the beginning, I would want you guys to write the differential form of rate. If I would want to write the differential form of rate, let's write it with respect to N2O5. You'll be starting with minus 1 divided by stoichiometric coefficient is 1. What do you write the next? Change in the concentration of N2O5. You write delta N2O5. Either you write delta of N2O5 or you can say D of N2O5. Okay? D of N2O5 divided by, instead of delta T, I'm writing dt is equal. In terms of NO2, I'll be starting with plus 1 divided by 2. I'll write change in the concentration of NO2 divided by time interval dt. Similarly, it's going to be plus 1 upon 1 by 2. 1 upon 1 by 2 is 2. D of O2 divided by dt. This is your differential form of rate. Since you wrote the differential form of rate, now look at the things that are given to me as per the question. My dear students, if you look carefully, minus dN2O5 by dt, minus dN2O5 by dt, it's given to me as K1 multiplied by concentration of N2O5 is equal plus 1 by 2 d of NO2 by dt, it's equal to K2 multiplied by concentration of N2O5 is equal to 2 times d of O2 by dt is given to me as K3 multiplied by concentration of N2O5. Now, if you look at this particular equation, in this equation, do you see any term cancelling out? If you see logically, this is N2O5 cancelling. So what do I get? K1 is equal to K2 divided by 2. It's equal to 2 times K3. Okay. Now, in this particular equation, if you multiply throughout by 2, when you multiply throughout by 2, it becomes 2 times K1 is equal. This becomes K2 is equal. This becomes 4 times K3. 4 times K3. So, this is the relation between K1, K2 and K3 which I was supposed to calculate as far as the question was concerned. Let me know once in the chats if it is also clear. And if this is clear, you guys are going to give a try for one more question. The question is like this. Let's say you've got a question like this. X times A gives Y times B. This is the reaction wherein X and Y are the stoichiometric coefficients of reactants products. X, Y are the stoichiometric coefficients of reactants products. Now, my dear students, as far as the question is concerned, let's say you are given that, for example, log of minus dA divided by dt is equal to log of d of B upon dt plus 0.3. This is something which is given to me as per the question. This information is given to me as per the question. Now, as per the question, what are we supposed to do? Calculate X and Y. We are supposed to get the stoichiometric coefficients of reactants and products. Can we do it? Can we do it, guys? Can we do it? It's an easy question. Why it's easy? Have a look, people. Why is it easy? Have a look. The reaction that's given to me. First thing which you need to do, write the differential form of rate. Differential form of rate says that minus 1 divided by stoichiometric coefficient d of A, change in the concentration of A divided by dt is equal. This is going to be plus 1 divided by Y, change in the concentration of B divided by dt. Right? This is your differential form of rate as far as the equation that's given to me. Now understand one thing. If you look at the given data, my dear students, this term is given to me in terms of log. This term is also given to me in terms of log. So let's do one thing. Let's convert this term also into log form only. And let's see what do we get from that. Now 0.3. 0.3 is nothing. 0.3 is just log of 2 to the base 10. That is 0.3. Log of 2 to the base 10. That's 0.3. You must be knowing. Now, if you think logically, this is the log of minus dA divided by dt is equal to log of m plus log of n. Log of m plus log of n is nothing but log of m into n. So it becomes log of 2 multiplied by dB upon dt. Okay? Perfect? Right, guys? Log of minus d upon dt is equal to log of 2 multiplied by dB upon dt. If you take NT-log on both the sides, if you take NT-log on both the sides, it becomes minus dA upon dt is equal to 2 times d of b divided by dt. Okay? If you take 2 here in the denominator, so it's minus 1 by 2, minus 1 by 2 d of a divided by dt is equal to d of b divided by dt. Now people, look at this particular equation. Look at this particular equation. At the same time, look at this particular equation. If you compare the two equations, you will be getting the value of x here as 2. On comparing the equation, x value is equal to 2 and y value. This is basically 1 by 1, right? And y value, here you are getting directly as 1. This is one of the probable answers of this particular question. If this is clear, let me know once in the chats quickly. Quickly, people, everyone. All clear? Let me know quickly in the chats if this is super clear. Everyone in the chats. Okay. For example, instead of 0.3, let's say instead of 0.3, for example, I'm giving you 0.6. Instead of 0.3, I'm giving you 0.6. At that time, what would be the value of x and y? Can you tell me that? Instead of 0.3, if I'm giving you 0.6. Exactly, 0.6 is log of 4. If 0.6 is log of 4, your final answer would be 4, 1. Your final answer would be 4, 1. Exactly, perfect. Perfect, guys, amazing. Let's move on. Let's move on. My dear students, now comes one more term, that is the law of mass action. Law of mass action. It's one of the simplest topics, okay? What is law of mass action all about? First of all, law of mass action, it also gives me the idea about the rate of reaction only. As per law of mass action, law of mass action also gives me the idea about the rate of reaction only. Okay? First thing which I would want to tell you, it's a complete theoretical concept. Law of mass action, it's a complete theoretical concept. It does not have any experimental background, number one. Number two, it was given by two scientists. Goldberg and P. Vage. These were the two scientists which gave this particular concept, law of mass action. Now, what this law of mass action says? See, guys, as per the statement, law of mass action, what it says? Rate of the reaction, that is directly proportional to the product of active masses of reactants, raised to the powers of their respective stoichiometric coefficients. Before understanding law of mass action, you need to remember few things. My dear students, let me tell you in simple words some things which you need to remember. What are those things? See, whenever you see any reactant or product in aqueous state, whenever you see any reactant or product in aqueous phase, aqueous state, its active mass will be its concentration. Whenever you'll see any reactant or product in aqueous state, its active mass is nothing but its concentration. Whenever you see any reactant or product in gaseous state, its active mass is concentration or pressure as well. Okay. Whenever you see any reactant or product in pure solid state or pure liquid state, its active mass you'll be taking as unity. You'll be taking as 1. These are first of all the 3 things which I would want you guys to remember. Whenever you see any reactant or product in aqueous state, its active mass is its concentration. Any reactant or product in gaseous phase, its active mass is its concentration or pressure. Any reactant or product in pure solid state or pure liquid state, its active mass will be equal to 1. Okay. Now understand what this law of mass action says. See guys, it's pretty much simple. Imagine that you've got a balanced chemical equation as N1A plus N2B. Imagine it gives products. This is, for example, your balanced chemical equation. Okay, this is your balanced chemical equation. Law of mass action says that rate of reaction, that is directly proportional to the product of active masses of reactants. Product of active masses of reactants. Right? This reactant is in aqueous state. So its active mass is basically its concentration multiplied by. This reactant is also in aqueous state. So concentration of B raised to the powers of the respective stoichiometric coefficients. Stoichiometric coefficient of A is N1. Stoichiometric coefficient of B is N2. This is what law of mass action is all about. Rate of reaction is directly proportional to the product of the concentration of reactants raised to the powers of the respective stoichiometric coefficients. Now, my dear students, you can just remove this proportionality sign. You can write a constant here. So, concentration of A raised by N1, concentration of B raised by N2. So, this becomes one more way of calculating rate of reaction. This becomes one more way of calculating your rate of reaction. And guys, let me tell you, whatever rate of reaction you calculate by solving this particular equation, that's what I'll be calling as theoretical rate of reaction. That's what I'll be calling as theoretical rate of reaction. Okay? Whatever rate of reaction we are going to calculate with the help of law of mass action, that's going to give us the theoretical rate of reaction. For example, imagine that you have got a reaction like this. A aqueous plus 2 times B aqueous, it gives C aqueous. If I want you guys to write law of mass action for this particular equation, you should be in a position to do it. You'll be simply writing rate of reaction is equal, constant is K. Now, start with the first reactant, which is in aqueous state. So, write concentration of A raised by stoichiometric coefficient multiplied by concentration of B raised by stoichiometric coefficient. So, this particular equation gives you the theoretical rate of reaction as per law of mass action. Okay? It gives you the theoretical rate of reaction as per law of mass action. Perfect. So, I believe you got to know what your law of mass action is all about. So, if you want to look at the statement again, rate of the reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficient. Okay? Raised to the powers of their respective stoichiometric coefficients. Now, guys, understand. Understand. See, see guys, remember that in order to calculate rate of the reaction, we have got two ways. We have got two ways to calculate rate of reaction. Either I'll be using the law of mass action to calculate rate of reaction, or in short, I'll say that is the theoretical way of calculating rate. in order to calculate rate of reaction, we can use law of mass action, with the help of which we can calculate theoretical rate of reaction, or we can calculate rate of reaction experimentally as well. We can calculate rate of reaction experimentally as well. Okay. Rate of reaction can be calculated theoretically. Rate of reaction can be calculated experimentally as well. Dear students, there are few reactions for which theoretical rate and experimentally determined rate, they will be coming out to be equal. But there will be some reactions for which theoretically determined and experimentally determined rate won't be equal. What does that mean? What does that mean? Understand properly what I'm trying to say. I'm telling you, there are two ways to calculate rate, theoretical or experimental. There would be some reactions for which theoretical and experimentally determined rate of the reaction would be coming out to be equal. But there would be some reactions for which theoretically determined rate and experimentally determined rate, they won't be coming out to be equal. What does that mean? That means this law of mass action, is it always giving you the actual value of rate? Is it always giving you the correct value of rate of reaction? Say yes or no in the chats. Does this law of mass action give you always the correct value of rate of reaction? Does it always give you the actual value of rate of reaction? The answer is no. Not always. Not always. Because if it always gave us the correct value of rate, then theoretical and experimentally determined rate always should have been equal. But there are some reactions for which theoretically determined rate and experimentally determined rate, they come out to be different. Okay? Your theoretical rate and actual rate, theoretical rate, experimental rate, theoretical rate, actual rate, right? They come out to be different for some reactions. So I would say law of mass action does not always give me the correct value of rate of reaction. Why it does not always give me the correct value of rate of reaction? There might be some mistake in this expression. There might be some mistake in this expression due to which it always does not give me the correct value of rate of reaction. So there might be some mistake in this particular expression. So what we need to do? We need to correct this expression basically. We need to correct this expression in such a way that the new expression, the corrected expression, the modified expression of law of mass action, that should always give me the correct value of rate. That should always give me the correct value of rate. Okay. Now, what is that modified law of mass action? That modified law of mass action is what I call as a rate law. Modified law of mass action is what I call as a rate law. First of all, if I talk about rate law, it is based on law of mass action only. It's based on law of mass action only. There are some changes which we have done in the expression of law of mass action. As you can see, the expression is similar. R is equal to K, concentration of A, concentration of B. But in the powers, we used to write N1, N2 in law of mass action. But here, what are we writing? We are writing X and Y. We are writing X and Y. And this X and Y, this X and Y, this X and Y, they are calculated experimentally. They are calculated experimentally. And let me tell you, this X is what you call as order of the reaction with respect to A. Y is what we call as order of the reaction with respect to B. And if I add them up, X plus Y gives me the overall order of the reaction. X plus Y is what I call as the overall order of the reaction. So what is the difference between your law of mass action and rate law? In law of mass action, the powers are always the stoichiometric coefficients. In rate law, these powers are calculated experimentally. This X and Y is calculated experimentally. Okay? Perfect. Now guys, as I told you already, in order to calculate rate, we have got two ways. Now I can modify it like this. Have a look. In order to calculate rate, we have got two ways. Either I'll be using law of mass action to calculate rate, or I'll be using the rate law to calculate rate. Okay. Law of mass action gives me the theoretically determined rate. Rate law gives me the experimentally determined rate. Where is the difference? In the law of mass action, the powers are always stoichiometric coefficients. Here the powers are calculated experimentally. Here the powers are calculated experimentally. So theoretical rate of reaction is nothing but it is equal to. Theoretical rate of reaction is equal to K concentration of A raised power, let's say N1, concentration of B raised power N2. Experimentally determined rate is equal to K concentration of A raised power X, concentration of B raised power Y. Now, my dear students, as I told you, there are some reactions for which theoretical and experimentally determined rate comes out to be equal. And for those reactions whose theoretical rate and experimentally determined rate comes out to be equal, I would say for those reactions, X value would be coming out to be equal to N1. X and Y, they are calculated experimentally. And after calculating X and Y experimentally, X value would be coming out to be same as that of N1. And Y would be coming out to be same as that of N2. Right? And similarly, there is one more set of reactions for which theoretical and experimentally determined rate, they do not come out to be equal. For those reactions, X value won't be coming out to be equal to N1 and Y value won't be coming out to be equal to N2. In short. Am I clear? Is this particular point clear, guys? Is this particular point clear? Quickly, I would want everyone to let me know in the chats if all the things are clear or not. Yeah? Perfect. So this was all about your rate law. And if you look properly, this R gives me the rate of the reaction. K is what I'll be calling as a rate constant. Now, few things which I want you guys to remember about rate constant. What kind of information rate constant gives us? What kind of information this rate constant K gives us? That's something which you need to remember. My dear students, rate constant K, it gives us the idea about the speed of the reaction. More the value of K, faster will be the reaction. Lesser the value of K, slower will be the reaction. So based on the rate constant of the reaction, by looking at the value of rate constant of the reaction, you can say whether the reaction will occur fastly or the reaction will occur slowly, right? That reaction whose rate constant value will be high, that will be fastly occurring, right? Similarly, that reaction whose rate constant will be low, will be less, that reaction would be slowly taking place. Okay, number one. Every reaction has got a particular value of rate constant. Every reaction has got a particular value of a rate constant at a particular temperature, right? So, rate constant of the reaction. Every single reaction has got a fixed value of the rate constant at a particular temperature. Every reaction has got a different values of rate constant, keeping it at a different temperature. What does that mean? For example, you have got the reaction A gives B, right? You have got one more reaction, C gives D. Okay, let's say temperature is 25 degrees centigrade. At 25 degrees centigrade, this reaction would be having its individual its rate constant, for example, as K1. At the same temperature, this reaction would be having its rate constant as K2. And by looking at the values of rate constant, you can identify among these two reactions which reaction will be occurring fastly and which reaction will be occurring slowly. Okay, that's something which you need to remember. So I would say every reaction has got a particular value of rate constant at a particular temperature. And this rate constant, it depends on what? Rate constant of the reaction depends on temperature. Rate constant of the reaction, it depends on temperature. How it depends on temperature? We'll see that in the Arrhenius equation. Right now, I want you to remember rate constant of the reaction is directly proportional to temperature. Okay? When you increase the temperature of the reaction, the rate constant of the reaction automatically increases. And when rate constant of the reaction increases, rate of reaction automatically increases. Rate of reaction automatically increases. So remember, your rate constant, it changes on changing the temperature. And when we increase the temperature, rate constant of the reaction increases. And as the rate constant of the reaction increases, we say the rate of reaction automatically increases. Rate of reaction automatically increases. Okay? Perfect. And this rate constant, as I told you, it only depends on temperature. It does not depend on the initial concentration of reactant. Whatever initial concentration of reactant you had kept, it has got nothing to do with that. Your rate constant only depends on the temperature. If you change the temperature, rate constant will change. No matter what initial concentration of reactant you are taking, rate constant does not depend on that. So these are some characteristic features about rate constant which I would want you guys to remember. Now guys, there are two types of reactions as per chemical kinetics point of view. Two types of reactions are there. One is called as elementary reaction. One is called as complex reaction. What is an elementary reaction? What is an elementary reaction? Elementary reactions, or you can call them directly as simple reactions. Elementary or simple reactions. These are the ones which are completed in one step. These are the reactions which are completed in just single step. And these are the reactions which are completed in more than one step. Okay? These are the reactions which are completed in just one step. These are the reactions which are completed in more than one step. Okay? This is the difference between your elementary and complex. Now let's try to understand them in detail. Let's try to understand them in detail. Just give me a second. Just give me a second, guys. See guys, as I told you, elementary reactions are the ones which are completed in a single step. Which are completed in a single step. Number one. Number two, this statement is important. Law of mass action is truly valid for elementary reactions. Law of mass action is truly valid for elementary reactions. What does that mean? What does that mean? Is, for example, you've got a reaction like this. 2 times A plus B gives C. Imagine it's a balanced chemical equation. At the same time, imagine this reaction is elementary. If this is elementary, that means this reaction will be taking place in a single step. This reaction would be taking place in a single step. Now, as I told you, in order to calculate rate of this particular reaction, how many methods do I have? I've got 2 ways to calculate rate of the reaction. Either I will be using law of mass action or I'll be using rate law. When I use the law of mass action, your rate of reaction comes out to be equal to R is equal to K, concentration of A, concentration of B, raised by stoichiometric coefficients, that is 2 and 1. If I use a rate law, as per rate law, R is equal to K, concentration of A raised by X, concentration of B raised by Y, where this X and Y is calculated experimentally. In case of elementary reactions, when you calculate this X and Y experimentally, let me tell you, after experimentally doing the calculation of X and Y, let me tell you, X and Y, they will exactly come out to be same as your stoichiometric coefficients. As your stoichiometric coefficients. So remember, in case of elementary reactions, law of mass action always gives us the correct result. In case of elementary reactions, law of mass action is truly valid. It's truly valid. It always gives me the correct answer. It always gives me the correct result. Okay? So if you remember, few minutes back, I told you one thing. Few minutes back, I told you there are some reactions for which theoretical rate and experimentally determined rate, they come out to be equal. So which reactions are those? Those are basically your simple reactions. Those are basically your elementary reactions. I was talking about your elementary reactions. So remember, for elementary reactions, whether you want to use the law of mass action to calculate rate or you want to use the rate law to calculate rate, from both the expressions, you'll be getting the same result, right? So law of mass action always gives me the correct value of the rate for the elementary reaction. I'll show you how to calculate experimentally in some time. I'll show you that. Okay. What are complex reactions? Complex reactions are the ones which are not complete in a single step, which are completed in more than one step. Those reactions which are completed in more than one step, you call those reactions as your complex reaction, right? But remember, the steps which are involved in the complex reaction, they are elementary in nature. The steps which are involved in a complex reaction, they are basically elementary in nature. What does that mean? What does that mean? For example, if you look at this particular reaction, NO plus Br2 gives NOBr2. Okay. Now this NOBr2 which is formed here plus NOBr2 plus NO. What does it make? It makes 2 times NOBr. It makes 2 times NOBr, right? My dear students, if I add these two steps, what do I get? When I add these two steps, this NO makes it 2 times NO plus what? Plus Br2 gives 2 times NOBr. Now, if I ask you whether this particular reaction, whether it was completed in one step or more than one step, whether this particular reaction was completed in one step or more than one step, this particular reaction was completed in more than one step, and that particular reaction which is completed in more than one step, what do you call that particular reaction? You call it as complex reaction. So this is your complex reaction. In this complex reaction, how many steps do you see? This is step number 1. This is step number 2. Remember, the steps which are involved in the complex reaction, they're elementary. So this particular step is elementary in nature. Even this particular one is also elementary in nature, right? So remember, that's more than sufficient when it comes to the complex reaction. Okay? When it comes to the complex reaction. Now comes the actual topic. What is that? That is molecularity. Whatever things we have discussed till now, all these things are basically involved in this particular topic, that is molecularity. 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 Have you heard about this particular term, molecularity? Let me know once in the chats. Yeah? See. Exactly, guys. Exactly. You're right. Yes. See, guys, first of all, the molecularity term, the concept of molecularity. Let me tell you, it is given for only elementary reactions. The concept of molecularity, it is valid only for elementary reactions. So for elementary reactions only, we define this particular term. Okay? Molecularity concept, we define only for what? Elementary reaction. Now, first of all, molecularity, it's a complete theoretical concept. It does not have any experimental background. It's a complete theoretical concept. No experimental background at all. Okay? Now, what is molecularity all about? See, guys, in this particular chapter only, there is one theory, which you might have heard, collision theory. And collision theory says that for the reaction to happen, the reacting species, they must collide first. For the reaction to happen, the reacting species must collide first. This is something called which collision theory tells us. For any reaction to happen, reacting species, they must collide first. Okay. Now, the number of reacting species the number of reacting species, which can be either atoms, ions, or molecules. The number of reacting species, which can be either atoms, ions, or molecules, colliding simultaneously to form the products. Colliding simultaneously to form the products. That is something which you call as molecularity. Let's say two molecules are colliding and forming the products. I'll say molecularity of the reaction is 2. Let's say 3 molecules are colliding and forming the products. Molecularity of the reaction is 3. Okay? So what is molecularity basically? It is the number of reacting species which can be either atoms, molecules, or ions, which must collide simultaneously to form the products. That's what you call as molecularity, right? For example, if you look at this particular reaction, in this particular reaction, your reactants are in which form? Are they in atomic form or molecular form? They're in molecular form. This is H2 molecule, this I2 molecule. H2 molecule, I2 molecule. They're in molecular form. So in this particular reaction, if you see, can I say two molecules are colliding and forming the products? And I would directly say molecularity of this reaction is 2. In this particular reaction, can I say 2 plus 1? 3 molecules are colliding and forming the products. So molecularity of this reaction is nothing but 3, right? In this particular reaction, 2 molecules are colliding and forming the products. So I'll say molecularity of this particular reaction is 2. For example, if you have got the reaction like this, half of H2 plus half of I2 gives HI. Can you let me know what is the molecularity of this reaction? Do not say molecularity of this reaction is half plus half 1. Do not say molecularity of this reaction is 1. No, that's wrong. That's wrong. How do you calculate molecularity of this particular reaction, in which the stoichiometric coefficients are given in fractions? What do you need to do? First of all, you need to convert these fractions into natural numbers. You need to convert these fractions into natural numbers. How exactly? Just multiply this reaction throughout by 2. When you multiply this reaction throughout by 2, it becomes H2 plus I2 gives 2 times HI. Now tell me, what is the molecularity of this reaction? 1 plus 1 is 2. Molecularity of this reaction is 2, which eventually becomes molecularity of this reaction also. Okay? Am I clear? Perfect. So remember, from now onwards, molecularity is nothing but the number of reacting species which must collide simultaneously to form the products. Now, if I ask you what about the molecularity of this reaction, look at the stoichiometric coefficient. It's 1. The molecularity of this particular reaction is 1. Okay. Its collision we consider with the wall of the container, right? Its collision we consider with the wall of the container basically. So molecularity of this particular reaction is 1. Now, based on molecularity, you can classify reactions into many types. That reaction whose molecularity is 1 is called as unimolecular. This would be bimolecular. Similarly, trimolecular, etc., etc. Right? So, based on molecularity, you can classify reactions into many types. Moving ahead. See, guys, molecularity of the reaction, it can never be 0. It can never be fractional. It can never be negative. If I say I've got the reaction whose molecularity is 0, what does that mean? That means 0 molecules have collided. If 0 molecules have collided, will the reaction happen? No. Reaction will not happen. Right? Perfect. So, molecularity of the reaction, it can never be 0. Molecularity of the reaction, it cannot be fractional. Fractional, what does that mean? For example, I have got a reaction and I'm telling you its molecularity is 2.3. What does that mean? What does that mean? Does that mean 2.3 molecules have collided and formed the products? Have you ever seen 2.3 molecules? No, right? So it cannot be 0, it cannot be fractional. Molecularity of the reaction cannot be negative as well. If I say I've got the reaction whose molecularity is -3, what does that mean? That means -3 molecules have collided. Is it making any significance? No. So molecularity of the reaction, it can neither be 0, nor it can be negative, nor it can be fractional. Okay? One more thing. Reactions with molecularity greater than 3. Reactions with molecularity greater than 3. They are rarely found. They are rarely observed. Those reactions which have got molecularity greater than 3, they are rarely observed. Right? They are rarely observed. Why is that? Why is that? See the logic. See, guys. Let's say this one molecule, this one more molecule, they are colliding and forming the products. This is the example of that particular reaction whose molecularity is 2. Now, let's say we have got 3 molecules, right? And they are simultaneously colliding and forming the products. This is the reaction whose molecularity is 3. This was the reaction whose molecularity was 2, right? Now, the term which I'm using, that is simultaneous collision. That is simultaneous collision. Perfect. Now, I can say those reactions which have got molecularity greater than 3, they are rarely found. Why is that? Because for more than 3 molecules to collide simultaneously, right? The probability of more than 3 molecules to collide simultaneously is very less. If probability of more than 3 molecules to collide simultaneously is less, if the probability of more than 3 molecules to collide simultaneously is less, what does that mean? What does that mean? That means those reactions which have got molecularity greater than 3, are they rarely found or frequently observed? They are rarely observed. Because the probability of more than 3 molecules to collide simultaneously is less. In short, you are going to remember it like this. Okay? And as I told you already, molecularity is the term which is defined only for elementary reactions. Right? It is defined only for elementary reactions. For complex reactions, molecularity is the term which is defined only for what? Only for elementary reactions. Okay, as I told you already. Now see, these 2 reactions I gave you already. Now if you add these 2 reactions up, when you add these 2 reactions, NOBr to NOBr2 cancels out. My net reaction becomes 2 times NO plus Br2. It gives what? It gives 2 times NOBr. This is your final reaction. This is your net reaction. Correct? Tell me one thing. Is this particular reaction carried out in single step or more than one step? This particular reaction is carried out in more than one step. So I'll be calling this particular reaction as a complex reaction. It is an example of complex reaction. Molecularity term is not defined for complex reactions. Molecularity term is defined for elementary reactions. Right? Molecularity of a complex reaction, it does not have any physical significance. Molecularity of the complex reaction does not have any physical significance. But I've told you the steps of the complex reaction, they're elementary. See guys, as I told you already, molecularity is defined only for elementary reactions. For complex reactions, molecularity does not have any physical significance. Okay? Now, this is the complex reaction. For this reaction, molecularity is not defined. But the steps of this reaction are elementary. Their molecularity would be defined. So what is the molecularity of this particular step? 1 plus 1 makes it 2. What is the molecularity of this particular step? 1 plus 1 makes it 2. Molecularity of this particular reaction, not defined, right? Does not have any significance. Because molecularity is the term which is defined for elementary reactions only. I hope I'm clear with this. I hope I'm clear with this. I hope I'm clear with this. Let's move on to one more thing, that is order. That is order of the reaction. Okay? My dear students, how do we exactly define order of the reaction? What is order all about? What is order all about? Order is simply defined as the sum of the powers of all the concentration terms. Sum of the powers of all the concentration terms involved in the rate expression, involved in the rate law. What does that mean? First thing, people, remember from now on, whenever you are supposed to calculate order of the reaction, the first thing which you need to do, what is that? You need to write the rate law for the reaction. For example, this is the reaction. If I want to define its order, what you need to do, first of all, you need to write rate law for this reaction. How do you write rate law? R is equal to K, concentration of A raised power X, concentration of B raised power Y. Now, in the rate law, as I've told you already, in the rate law, whatever powers you have, these powers actually give you the order of the reaction. As I've already told you, X is what you call as order with respect to A, Y is what you call as order with respect to B, and X and Y, X plus Y is what you call as overall order of the reaction. And at the same time, if you remember, I've told you X and Y are calculated experimentally. X and Y are calculated experimentally. So look at all the steps now. Look at all the steps. We know rate law is experimentally determined. Rate law is experimentally determined. This is rate law. It's experimentally determined because this X and Y are calculated experimentally. If rate law is experimentally determined, what does that mean? That means order is also an experimentally determined quantity because you derive order from rate law only. You derive order from rate law, and rate law you get experimentally. Like your molecularity. Molecularity cannot be zero. Molecularity cannot be fractional. Molecularity cannot be negative. But order can be zero. Order can be zero. Order can be any positive number. Order can be fractional also. Order can be fractional also. Remember, people, order can be negative. Order can be negative with respect to any reactant. Order can be negative with respect to any reactant. But overall order of the reaction cannot be negative. For example, this is the reaction. X is order with respect to A. Y is order with respect to B. See, X can be negative. X can be negative. But remember, X plus Y can never be negative. Y can be negative. But X plus Y cannot be negative. So order with respect to a reactant can be negative. But overall order of the reaction, that can never be negative. This is one more important point. One more thing. For the elementary reaction, order is equal to molecularity. Important point. Why is that? If you will be having an elementary reaction, for an elementary reaction, order is equal to what? Order is equal to the molecularity. What does that mean? See, for example, you have got the reaction like this. 2A plus B, 2A plus B gives C. My dear students, imagine that this reaction is elementary. Imagine that this reaction is elementary. If this reaction is elementary, for elementary reactions, molecularity is defined. So what would be its molecularity? 2 plus 1, 3. So I've got the elementary reaction whose molecularity is 3. Now the point is, if I want to define, if I want to write rate law says that R is equal to K, concentration of A raised by X, concentration of B raised by Y. But I've told you already, for elementary reactions, law of mass action is truly valid. That means for elementary reactions, when you get the value of X and Y comes out to be same as the stoichiometric coefficients. So 2 and 1, right? Because it's an elementary reaction. For elementary reaction, law of mass action is truly valid, right? So experimentally, when you calculate X and Y, it will come out to be same as what your stoichiometric coefficients were. Okay? So as per this particular rate law, what is the order? Order is 2 plus 1, 3. As per this particular rate law, order of reaction is 3. What was molecularity of the reaction? Molecularity of the reaction is also 3. What is the nature of the reaction? It's elementary. So you are directly going to remember one simple thing. In case of elementary reactions, your molecularity and order are same. Okay? In case of elementary reaction, order is always equal to molecularity. Perfect. I believe I'm clear with this. Tell me whether this statement is right or wrong. What do you think? Is this particular statement right or wrong? Is this particular statement right or wrong? A zero order reaction must be complex. Is it right or wrong? See guys, a zero order reaction can never be elementary. A zero order reaction can never be elementary. Because if a zero order reaction is elementary, that means its molecularity should be 0 too. If the zero order reaction is elementary, that means its molecularity should be 0 too. But molecularity is equal to 0. That does not make any sense. So remember, your zero order reaction, that's always complex. That's always complex. Okay? That's always complex. One more thing which you need to know. My dear students, for a reaction, there are different rate constants. In a reaction, there are different rate constants. For example, one is what you call as rate constant of the reaction, which you already know. One is what you call as rate constant of reaction. One is what you call as rate constant of reaction. Rate constant of reaction. Okay. There is one more rate constant which I denote with Ka. One more rate constant which I denote with Kb. Similarly, one more rate constant which I denote with Kc. One more rate constant which I denote with Kd. What is Ka? Ka is what you call as, it is what you call as a rate constant of disappearance of A. Kb is what you call as a rate constant of disappearance of B. Kc is what you call as, it is what you call as a rate constant of appearance of C. And this is what you call as a rate constant of appearance of D. So there are different rate constants involved in a reaction. One is going to be your general rate constant of the reaction. One more would be called as rate constant of disappearance of A, rate constant of appearance of product, etc., etc. And you need to remember the result between them. Remember, I'm going to write a general expression. I'm not deriving anything though. Rate constant of disappearance or appearance of a reactant or product is always equal to rate constant of the reaction multiplied by stoichiometric coefficient. Multiplied by stoichiometric coefficient. It has got the derivation also, but I'm skipping the derivation. What it means, how can we write it? For example, I'm writing K. What is K? Rate constant of disappearance of A. Rate constant of disappearance of A would be rate constant of reaction multiplied by stoichiometric coefficient of A. What is that? That's N1. Similarly, Kb would be equal to rate constant of reaction multiplied by N2. Similarly, Kc would be equal rate constant of reaction multiplied by N3. Kd would be equal to rate constant of reaction multiplied by N4. So if you see from this particular expression, I can say rate constant of the reaction is equal to Ka by N1. Here it will be Kb by N2. Here it will be Kc by N3. Here it will be Kd divided by N4. From all these things, I can conclude one thing. Ka divided by N1 will be always equal to Kb divided by N2, which will be always equal to Kc divided by N3, which will be always equal to Kd divided by N4. And overall, you will be calling it as rate constant of the reaction. Remember this particular point as well. Why is it important? Because from this particular expression, a question is asked like this. Tell me the answer of this question. Tell me the answer of this question quickly. Everyone, guys, tell me the answer of this question. Tell me the answer of this particular question. Everyone. Guys, you should be able to solve this. Lunch break we'll have in some time. See guys, it's a simple question. We have got a reaction given to us as 2A plus 3B gives C. 2A plus 3B gives C, right? Now, rate constant of disappearance of A I'm representing with K1 divided by stoichiometric coefficient would be equal to K2 divided by stoichiometric coefficient. Sorry, it's 3 here. Which would be equal to K3 divided by stoichiometric coefficient, that's 1. And all these I'll be calling as the rate of reaction, rate constant of the reaction. Now guys, if you take the LCM of the denominators, LCM of denominators comes out to be 6, multiplied throughout by 6, this becomes 3 times K1, this becomes 2 times K2, this becomes 6 times K3. So this is the relation between K1, K2 and K3. I hope you got it, how it came. I hope you got how it came. From this particular expression, which I gave you a few minutes back, this one. Okay? Right? So guys, one more thing. If I ask you what are going to be the units of rate constant, what are going to be the units of rate constant? Units of rate constant. Let me tell you, I'm directly going to give you. Units of rate constant are simply going to be moles liter inverse raised power 1 minus n second inverse. Or you can say, let the pressure be in atm. So atm raised power 1 minus n. Let time be in seconds, second inverse. So n over here represents the order of the reaction. N represents order of the reaction, for example. N represents order. Let's say I've got a zero order reaction. In case of the zero order reaction, if I ask you, what is the value of n? N value is 0. If n value is 0, so rate constant units are going to be n value is 0. 1 minus 0 is 1. So it's going to be moles, liter inverse, second inverse, or it's going to be atm, second inverse for zero order. Let's say you've got a first order reaction. For first order reaction, n value is equal to 1. For first order reaction, n value is equal to 1. So 1 minus 1 is 0. Anything raised power 0 is 1. So rate constant units are going to be directly second inverse. From here also, it's going to be second inverse only, right? Or if time is in minutes, then minute inverse. If time is in hour, then hour inverse, right? Similarly, if you'll be having a second order reaction, n is equal to 2, put the value of n as 2 here. 1 minus 2 becomes minus 1. 1 minus 2 becomes minus 1. Accordingly, you'll be getting the units of the rate constant in case of the second order reaction as well. I hope this is clear. I hope this is clear. So remember the units of rate constant. All right. See guys, a simple set of questions which can be asked. Simple set of questions that can be asked. Understand how this question is to be solved. See, as far as this particular question is concerned, we have got a reaction A gives B. We have got a reaction A gives B whose rate constant is K. It is found that rate doubles. It is found that rate doubles when concentration of A is increased 4 times. Okay? Find the order of the reaction. Tell me one thing, guys. Tell me one thing. How many reactants do you see here? One. There is only one reactant. So can I say order with respect to A will be equal to the overall order of the reaction? And let's call the overall order of the reaction as N. Let the order of the reaction be N. Okay? If the order of the reaction is N, can we write rate law? Yes, we can do that. R is equal to K, concentration of A, raised per order, raised per N. Well, in order to calculate order, what do we need to write? In order to calculate order, we need to write the rate law. Here, I have written the rate law. Calling this is equation number 1. As far as the equation is concerned, it is found that the rate doubles. Rate doubles. So initially the rate was R. Now it's 2R. Rate doubles when the concentration of A is increased 4 times. So initially it was A. Now it's 4 times A. Raised per N. Equation number 2. If I divide the two equations, 2 divided by 1, R cancels. So left hand side, you get 2. K and K cancels. A raised per N cancels. This becomes 4 raised per N. Right? So from this particular equation, I would say the value of N has to be 1 by 2. The value of N has to be 1 by 2. Then only LHS and RHS side would be equal. So this N is what you call as overall order of the reaction, which I was supposed to calculate. Right? Is this particular question clear? You can easily solve this question. Similarly, look at this one. Can you solve this? Can you solve this, guys? The rate of the reaction becomes half when the volume of the vessel is doubled. Rate of the reaction becomes half when the volume of the vessel is doubled. Find the order of the reaction. It's a similar type of question. Let the order of the reaction be N. Let the order of the reaction be N. So rate law becomes R is equal to K, concentration of A raised per N. Or I can say R is equal to K. Instead of concentration of A, I can write moles of A divided by volume of vessel raised per N. Because concentration is moles per unit volume. Okay. Calling this is equation number 1. Now, as per the equation is concerned, the rate becomes half. Initially, it was R. Now, it's becoming R by 2. rate becomes half. When volume of the vessel is doubled. Initially, the volume of the vessel was V, now it's 2 times V. Now it's 2 times V. Calling this is equation number 2. Just divide these two equations. If I divide equation 1 with equation 2, what do I get? 1 with 2, RR gets cancelled. On left hand side, you get 2. K and K cancelled. NA by V cancelled. So it becomes 2 raised per N on this side. So comparing both, comparing here, LHS, RHS, so N value is equal to 1. What was N? N was nothing but, it was the order of the reaction. Order of the overall reaction is coming out, V1. Okay? Perfect. Should we take a break here? Are you all tired? Let's take a break for like 15 minutes, okay? Let's take a break for 15 minutes. You can fresh up and come back. Okay? Break for 15 minutes. Or keep it as 120. Be back on time, okay? Be back on time, everyone. Everyone. How much time does it take for lunch? 20 or 30 minutes? Just finish it quickly in 20 minutes. Have your lunch quickly. Quickly, you can have your lunch. Okay, chalo. I'll keep it as 1:30. Finish your lunch quickly and come back. Directly come to the session. Okay, but finish your lunch quickly. I'll see you exactly at 1:30. Take care. See you. Is everyone back? Are you guys done with your lunch? Yeah? Are you done with your lunch? Tell me quickly. I don't know why I'm coughing so much. I think I'll get cold cough soon. All right, that's great. So tell me, whatever things we have discussed till now, is every single thing clear? Is every single thing clear? And I hope you guys are making short notes. Are you doing that? Are you doing that? All right. All right. Perfect. Let's get going then. Let's get going. Let's get going. All right, guys. So now we are going to get into the experimental determination of order. This is one short question which is frequently asked when it comes to your NEET examination, right? How do we calculate order of the reaction experimentally? And my dear students, I'll be making you understand this particular topic directly in the form of question. For example, this is the question over here. In this particular question, we are given with a reaction. As you can see, this is the reaction given. There are 3 experiments given as well. Okay. As per experiment number 1, the concentration of NO is kept 5 into 10 raised power minus 3 molar. Concentration of H2 is kept this much. At that point of time, rate of reaction which was calculated, that came out to be 3 into 10 raised power minus 5. Similarly, experiment number 2, experiment number 3. So there are 3 experiments which have been carried out for this particular reaction. And from the data of these experiments, we have to predict, we have to depict the order of the reaction. Now, how exactly we are going to do it? How exactly we are going to solve it? Try to understand, guys, what I'll be doing. As I've told you already, in order to calculate order of the reaction, what are we supposed to write first? We are supposed to write the rate law. So first thing, for this reaction, I'll be writing the rate law. And rate law for this reaction would be written like this. R is equal to rate constant K, concentration of NO raised power X, concentration of H2 raised power Y. So this is how you have written the rate law for the given reaction. Now, my dear students, in this rate law, you are going to fit the data of all these experiments. For example, if I put the experiment number 1 data in this expression, see how do I write it? As per experiment number 1, what is the rate of reaction? What is R? R is equal to 3 into 10 raised power minus 5 is equal to K. What is the concentration of NO in experiment number 1? It is 5 into 10 raised power minus 3 raised power X. concentration of H2 in the first experiment. It is 2.5 into 10 raised power minus 3 raised power y. This I'm calling as equation number 1. Now in the same rate law, let's introduce the data which is given in experiment number 2. And experiment number 2 says that rate is equal to 9 into 10 raised power minus 5. So 9 into 10 raised power minus 5 is equal to K. What is the concentration of NO? Concentration of NO here is 15 into 10 raised power minus 3 raised power X. What is the concentration of H2? It is 2.5 into 10 raised power minus 3 raised power Y. Calling this is equation number 2. Now, let's introduce the data which is given in experiment number 3 into this particular rate law. As per experiment number 3, rate of the reaction is equal to 36 into 10 raised power minus 5 is equal to K. What is the concentration of NO in the third experiment? In the third experiment, it is 15 into 10 raised power minus 3 raised power X. What is the concentration of H2? That is 10 into 10 raised power minus 3 raised power Y. This is your equation number 3. So we got 3 equations here. People understand. First, you need to write the rate law. After writing the rate law, put all the data in this expression. So you'll be getting some equations here, like I got 3 equations. Now I just have to divide the equations and get the value of X and Y. How do I do it? See guys, what is the first thing which I'll be doing? I'll be dividing equation 2 with equation 1. When I divide equation 2 with equation 1, what do I get? 10 power minus 5, 10 power minus 5 cancel. 9 divided by 3 comes out by 3 is equal to K and K gets cancelled out. 2.5 entire term cancelled out. 10 raised power minus 3, 10 raised power minus 3 cancel. 15 divided by 5 is 3. So it's going to be 3 raised power X, right? So from this particular equation, you can say the value of X is nothing but 1, right? The value of X is 1. So you got the value of X. Now, divide equation 3 with equation 2. When you divide equation 3 with equation 2, what do we get? 10 power minus 5, 10 power minus 5 cancel. 36 divided by 9 is 4. So on left hand side, we got 4. K gets cancelled. This term cancel. 10 power minus 3, 10 power minus 3 cancel. 10 divided by 2.5 is 4. So this is 4 raised power y, right? So 4 raised power 1 is equal to 4 raised power y, which tells you that y value is equal to 1. So you got the value of X, you got the value of Y. And since you got the value of X and Y, so I would say the overall order of the reaction is always equal to X plus Y. So 1 plus 1 comes out to be 2. So overall order of this particular reaction which was given to us is coming out to be 2. So this is the general approach of solving these sort of questions. So frequently I'm telling you these sort of questions are asked. You'll be given with few experiments, and from the experiments you will be supposed to calculate order of the reaction. And this is how you exactly do it. Okay? Ubad, this schedule will be provided tomorrow. From tomorrow you'll have the schedule in the reloaded batch. Okay? I hope it's clear till here. Now, let's move on to one more topic, which is again important. You must be knowing about this one too. That is zero order reactions. Okay? What are zero order reactions first of all? My dear students, zero order reactions are those reactions whose rate does not depend on the concentration of reactants. Those reactions whose rate does not depend on the concentration of reactants. For example, have a look. Let's say you've got the reaction like this. A gives B. Understand, guys. A gives B. I'm assuming order of this particular reaction equal to 0. Order of this reaction is equal to 0. If order of this reaction is 0, what does that mean? That means rate of the reaction does not depend on the concentration of reactant. If you change the concentration of reactant, nothing happens to the rate of reaction. On changing the concentration of reactant, if nothing happens to the rate of reaction, I'll be calling this particular reaction as the zero order reaction. Point number one. Point number two. My dear students, let's assume at time t is equal to 0, initially, the concentration of reactant is A0. This would be 0 automatically because the reaction has not started yet. Now, for example, at time t, at some time t, let's say the concentration of reactant left is AT and the concentration of product formed is BT. So first of all, you should know the meaning of all these terms, A0, AT, BT, because continuously from now onwards, I'll be using these terms. What is A0 exactly? I would say A0 is nothing but A0 is the initial concentration of reactant. Initial concentration of reactant at time t is equal to 0. What is AT? AT is nothing but it is basically the concentration of reactant left at time t. Concentration of reactant left at time t. Try to understand, guys. Try to understand. If I ask you to write rate law for the given reaction, how do you write it? Rate of the reaction is equal to rate constant, concentration of reactant, raised per order. Order is 0. Is there any other way to calculate rate of reaction? Yes. I'll start with the minus sign. 1 divided by stoichiometric coefficient is 1. Change in the concentration of A divided by dt. Perfect. This is one more way of calculating rate of reaction. This is one way of calculating rate with the help of your rate law. This is one more way of writing your rate of reaction. Now, my dear students, try to understand. Try to understand what I do. I'll be writing minus d of A divided by dt. Minus d of A divided by dt is equal to k. A raised power 0 is 1. So I'll be getting d of A is equal to minus k dt. D of A is equal to minus k dt. I'll be integrating on this side as well as this side. This side I'm integrating with respect to time, which is going from 0 to t. So limits here are 0 to t. Here I'm integrating with respect to concentration of reactant, and at time t is equal to 0, concentration of reactant was A0. At time t, the concentration of reactant is AT. Correct? Now, my dear students, try to understand what I do after this. Try to understand what do I do after this. Integral of dA. Integral of dA will be A. Lower limit is A0. Upper limit is AT is equal to minus k comes out of the integral. Integral of dt is t, upper limit, lower limit, so it's just going to be t. So finally, I'll be getting the expression AT minus A0 is equal to minus KT, or I can say AT is equal to A0 minus KT. This particular equation will be calling as integrated rate equation for the zero order reactions. This particular equation you will be calling as the integrated rate equation. You'll be calling it as the integrated rate equation for the zero order reactions. And this particular equation I'll be using almost in all the questions of the zero order reactions. Point number one. Point number one. My dear students, point number two. Point number two for the zero order reaction. What is that? I hope all of you would have heard about a term called as half-life. Half-life, which is represented either with T 50% or you can represent it with T 1 by 2. How do you exactly define half-life? Again, it's very simple concept. Half-life is nothing but it is the time taken. I would say it is the time taken to complete. Time taken to complete what? Time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction is what you call as half-life. Okay? Time taken to complete 50% of the reaction is what you will be calling as the half-life. See how exactly it's calculated. Understand, guys. Again, I'm assuming that we have got the reaction A gives B. Imagine it is following the zero order kinetics. Order of this particular reaction is 0. Imagine that initially at time t is equal to 0, the initial concentration of reactant is A0. So this is going to be 0. Now when the reaction starts, I would say concentration of reactant will keep on decreasing. I would say at time t is equal to t half. At time t half, how much concentration of reactant would be left? This is the time at which 50% of the reaction would be completed. 50% reaction completed means I would say 50% of the reactant would have got converted into product. And if 50% of reactant has got converted into product, so how much reactant would be left at half-life? The reactant left at half-life would be A naught by 2. Initially, I took A naught. From A naught by 2 got converted into product. How much would be left? A naught by 2 would be left. And the concentration of reactant left is represented with AT. My dear students, if I use this particular condition in the integrated rate equation, see what do I get? In the integrated rate equation, AT, instead of AT, I'll be writing A naught by 2 is equal to A naught minus K, I'm writing as such. Instead of T, I'm writing T half. So from this particular expression, you are getting T half equal to A naught divided by 2K. This is one general expression which I would want all of you to remember from now onwards to calculate the half-life of the zero order reaction. To calculate the half-life of the zero order reaction, T half is nothing but A naught divided by 2K. This is the second important thing which can be asked in your exam, right? Half-life of the zero order reaction is equal to A naught divided by 2K. The third point. The third point, people. Third point is nothing but, that's what you call as completion time. That's what you call as completion time. Completion time is represented by T 100%. Time taken to complete 100% of the reaction. Time taken to complete 100% of the reaction. Time taken to complete 100% of the reaction is what you call as completion time. Now guys, how do I get this expression? Understand, you have got the reaction A gives B. I'm assuming it's following the zero order kinetics. Order of this reaction is 0. Imagine at time t is equal to 0, its concentration is A naught. This is 0, right? Now when the reaction starts, the concentration of reactants keeps on decreasing, right? Now people, at time t is equal to T 100%. At time t is equal to T 100%. I would say 100% of the reactant would have got converted into product. And if 100% of reactant would have got converted into product, how much reactant would be left? Nothing. Because 100% entire amount of reactant has got converted into product. So I'm left with nothing. Concentration of reactant left is represented with what? It is represented with AT. If I use this particular condition in the integrated rate equation says that AT is equal to A naught minus KT. Instead of AT, I'll be writing 0 is equal to A naught minus K. Instead of T, I'll be writing T 100%. So from this particular expression, can't we calculate T 100%? T 100% will be nothing but A naught divided by K. This is one more important expression which I would want all of you to remember. This is how you calculate completion time. Completion time in case of the zero order reactions. Okay. Now guys, if you think logically, T half or T 100% we calculate as A naught divided by K, and T 50%, T half-life is equal to A naught divided by 2K. If you divide these two equations, what do you get? If I call this equation number 1, equation number 2, if I divide these two equations, I'll say T 100% is equal to 2 times T 50%, right? T 100% is equal to 2 times T 50%. What does it indicate? What does it mean? It means that a zero order reaction is 100% complete. A zero order reaction is 100% completed in 2 half-life. A zero order reaction is 100% complete in 2 half-lives. For example, if I ask you, let's say I'm asking you like this, half-life of the zero order reaction is 10 minutes. Half-life of the zero order reaction is 10 minutes. What would be its completion time? It will be 2 into 10, right? 20 minutes. That's it. Okay? I hope I'm clear with this. I hope I'm clear with this. But this particular expression is only valid for zero order reactions. Now guys, the next point. Next point. That is point number 4 when it comes to the zero order reaction. Point number 4. What is that? That is the degree of dissociation. Degree of dissociation alpha. How do we calculate degree of dissociation alpha for a zero order reaction? See, Let's say I've got the zero order reaction A gives B. Assume that initially we have got these many moles of reactant, A naught moles of reactant with us. This would be 0. Let's say at time t, the moles of reactant left are 80 and moles of products formed are BT. Let's assume that. Okay. People, do you remember how do we calculate degree of dissociation alpha? Alpha is calculated as number of moles of reactants dissociated into products divided by initial moles of reactants. Number of moles of reactants dissociated into products, number of moles of reactants converted into products divided by initial moles of reactants. Tell me how many moles of reactants dissociated into products. See, initially I had A naught moles of reactants. I am left with 80 moles of reactants. Initially I start with A naught. Now I'm left with 80 moles of reactants. So how many moles of reactants have got converted into product? I started with A naught. Now I'm left with 80. So A naught minus 80. These are the moles of reactants which have got converted into products, right? Divided by initial moles of reactants Ni, that is initial moles of reactant, that's A naught only. So I can say your alpha is equal to A naught minus, what is 80? 80 is nothing but A naught minus KT divided by what? Divided by A naught. So I would say alpha is equal to AT divided by A naught. This is one more general expression which I would want you guys to remember directly. No need to waste your time in deriving all this stuff in the examination. So alpha, degree of dissociation for the zero order reaction is nothing but KT divided by A naught. This was the fourth parameter when it comes to the zero order kinetics. Fifth point. What is the fifth point? How do we calculate the concentration of product? Concentration of product at time t. Concentration of product at time t. How do we get this? Again, I'm writing the equation A gives B. Initially at time t is equal to 0, its concentration is A naught, this is 0. Now at time t, the concentration of reactant left is AT, the concentration of product formed is BT. Imagine that. Concentration of product formed is BT. Now guys, see, understand what I'll be doing. Initially at time t is equal to 0, concentration of reactant is A naught. Now concentration of reactant left is AT. At time t, the concentration of reactant left is AT. So how much concentration of reactant has got converted into product? Whatever concentration of reactant has got converted into product, that is going to give you the concentration of product at time t, right? See guys, it's pretty much simple. Initially I start with A naught moles of reactants. How much is left? 80. So how much has got converted? A naught minus 80. Convert into what? Convert into product. So I would say concentration of product at time t would be nothing but A naught minus 80. Simple. So whenever they are asking you to calculate the concentration of product at time t, you are simply going to write it as A naught minus 80. And since you know, AT is equal to A naught minus KT. See, A naught I'm writing as such. AT is nothing but A naught minus KT. So A naught cancel. So I would say concentration of product at time t is equal to what? Directly you can remember it as concentration of product at time t is nothing but it's equal to K multiplied by T. This is one more important expression which I would want you guys to remember. Now people, the sixth one. Sixth one, or let me write the sixth one here only. Units of rate constant. Units of rate constant. What are the units of rate constant K for the zero order reactions? I've already discussed it with you. What are the units? You should know it now. I told you the general units are moles per liter raised power 1 minus n second inverse, right? And for the zero order, it's directly going to be moles, liter inverse, second inverse, or ATM second inverse. Or let's say pressure is in bar, time is in minutes, so bar minute inverse, etc., etc. Okay, these were the units of rate constant for the zero order reaction. Now comes the seventh point. This is also important. Seventh point. See guys, imagine you have got the reaction like this. A gives B, whose rate constant is K. I'm assuming order of this particular reaction is 0. Order of this reaction is, for example, 0. Initially, its concentration is A naught. This is 0. Let's say at time T1, the concentration of reactant left is AT1. Okay. At time t1, concentration of reactant left is AT1. Let's say at time t2, concentration of reactant left is AT2. Okay, I have chosen 2 times here. At time t1, concentration of reactant left is AT1. At time t2, concentration of reactant left is AT2. Now, my dear students, for example, they're asking you in what time interval the concentration of reactant goes from AT1 to AT2. In what time interval the concentration of reactant goes from AT1 to AT2. So basically, they're asking you this particular time interval, T2 minus T1. They're asking you this particular time interval. Whenever this sort of a question is asked, I'll give you one direct expression, remember that, and utilize that in the questions. Remember the expression like this: AT2 is equal to AT1 minus K T2 minus T1. T2 minus T1. This is one important expression, right? From this particular expression, a particular type of question will be asked. Whenever they'll ask you a question, in what time interval the concentration of reactant goes from AT1 to AT2, this expression you'll be using in the question. Okay? I hope this is clear. Now, guys, one more important thing. One more important thing. It's a shortcut though. It's a short trick though. But anyways, you need to remember it. Reaction is A gives B. Reaction is A gives B. I'm making one table over here. Reaction is A gives B. I'm making one table over here. The table is like this. Let's say here I'm mentioning concentration of reactant. Here I'm mentioning time. Concentration of reactant versus time. Okay. Concentration of reactant versus time. Let's say at time T1, concentration of reactant was A1. At time T2, concentration of reactant is A2. At time T3, concentration of reactant is A3. At time T4, concentration of reactant is A4. Let's assume at time T1, concentration of reactant is A1. At some other time T2, concentration of reactant is A2. Similarly, A3, A4, etc., etc. My dear students, if the time interval is same, if the time interval is same, what does that mean? That means T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. T2 minus T1 is equal to T3 minus T2 is equal to T4 minus T3. Time interval is same. I'm assuming that. My dear students, if in the same time interval, A2 minus A1 comes out to be equal to A3 minus A2, which comes out to be equal to A4 minus A3. If in the same time interval, A2 minus A1 comes out to be same as that of A3 minus A2, comes out to be same as that of A4 minus A3. That means over here I would say common difference is equal to same. And common difference is same in what? Common difference is same in arithmetic progressions. So I would say the concentration of reactants is making what? Concentration of reactants in the same time interval is making AP, arithmetic progression, right? Whenever concentration of reactants in the same time interval would be making arithmetic progression, remember the order of the reaction is going to be 0. This is just going to be a 0 order reaction. Sometimes you'll be given with a table like this and you will be supposed to check what will be the order of the reaction. So if in the same time interval, concentration of reactants forms arithmetic progression, understand and remember the reaction is going to follow the 0 order kinetics. Similarly, my dear students, if in the same time interval, A2 divided by A1 comes out to be same as that of A3 divided by A2, which comes out to be same as that of A4 divided by A3, and so on. What does that mean? That means the concentration of reactants here are forming geometric progression. And whenever in the same time interval, concentration of reactants would be forming the geometric progression, understand the reaction follows the first order kinetics. At that point of time, the reaction is going to have order 1. I hope I'm clear with this, right? When it's AP, 0 order, when it's forming GP, then it's going to be first order. Is it clear? Is it clear, guys? Now, there are some graphs, some important graphs also included here. Let's have a look on what kind of graphs can be asked in case of the 0 order reactions. The graphs which can be made in 0 order reactions. Okay. See, guys, we can make different graphs. Different graphs we can make. The first graph which I'm making over here, that is going to be between AT versus T. AT versus T. Do you know AT is equal to A naught minus KT? You are plotting your AT along y-axis. Time you are plotting along x-axis. This becomes your M. Sign here is minus. This is C. Y is equal to minus mx plus C. Y is equal to minus mx plus C. The graph is going to be like this. Straight line with a negative slope. You should be knowing it, right? So slope of this particular graph is going to be minus M. And intercept. Intercept, that means hair to hair. The distance from hair to hair. Intercept is going to be equal to A naught. Intercept is basically C. Intercept is denoted with C, and C is nothing but C is A naught over here. This is the first graph which can be asked. First graph which can be asked. Let's have a look on the second graph. Second is simply rate versus concentration of reactant. Rate versus concentration of reactant. In case of your zero order reactions, you know R is equal to K, concentration of A raised power 0. Anything raised power 0 is 1, so R is equal to K. So can I say rate is independent of concentration of reactant? Rate is independent of concentration of reactant. And if rate is independent of concentration of reactant, it's going to be a straight line like this. It's going to be a straight line like this, right? Okay. Let's have a look on one more graph. For example, I need to plot a graph between, let's keep it as T half versus A naught. T half versus A naught. Few minutes back only I told you half-life of the zero order reaction is equal to A naught by 2K. Or I can say 1 by 2K multiplied by A naught. T half you are plotting along y-axis. A naught you are plotting along x-axis. This becomes your M. Y is equal to mx means straight line, right? And slope is nothing but that's M. M is nothing but that's 1 upon 2K. Okay? 1 upon 2K. Perfect. Similarly, guys, there can be one more graph asked. For example, they are asking you a graph about T 100%. T 100% versus A naught. T 100% versus A naught will be similar graph, and its slope now won't be 1 upon 2K, it will be 1 upon K. Right? By chance, if they ask you the question about degree of dissociation, alpha versus A naught. You know your alpha is equal to KT divided by A naught. Alpha is equal to KT divided by A naught. So alpha and A naught, they are inversely proportional. If alpha and A naught are inversely proportional, the nature of the curve is going to be rectangular hyperbola. So these sort of questions, these sort of graphs can be plotted when it comes to the zero order reactions. Okay? Perfect, guys. Is that clear till here? These sort of graphs can be plotted when it comes to the zero order reaction. You have to remember all of them one by one. Now, guys. Now, let's see what kind of questions can be asked. Or before the questions, I would want you guys to remember one more thing. Where is it? This is it. I want you guys to remember this as well. Examples of the zero order reactions. These can be the memory-based questions asked. Photochemical reaction between H2 and Cl2, it follows zero order kinetics, right? Similarly, decomposition of Hi on gold surface, it follows zero order kinetics. Decomposition of NH3 over molybdenum, it again follows the zero order kinetics only. So these are the examples of the zero order reactions which I would want every one of you to remember. Okay? Anything can be asked out of these examples in the memory-based form. In the memory-based form. Let's have a look on the first question. Let's see what kind of questions can be asked. This can be one of the patterns of the questions which can be asked from the zero order reaction. What is it exactly? As per the question, you are given with a zero order reaction like this. Imagine zero order reaction A gives B, whose rate constant is, for example, K. Order of the reaction is equal to 0. Okay. A zero order reaction is 20% completed in 10 minutes. 20% completed in 10 minutes. What does that mean? Let's say at time t is equal to 0, the concentration of reactant was A naught. This is 0. Now, as per the question, at t is equal to 10 minutes. At t is equal to 10 minutes. After 10 minutes, it was observed that 20% of the reaction was completed. What does that mean? That means 20% of the reactant has got converted into product. If 20% of reactant has got converted into product, how much reactant would be left? How much reactant would be left? I would say 80% of reactant would be left in the container. 80% of the reactant, 80% of the reactant would be left in the container. And the left out, the concentration of reactant left at any time is represented with 80. It is represented with 80, right? Now, as per the question, at what time? At what time it will be 80% completed? At what time reaction will be 80% completed? 80% complete means what? At what time 80% of reactant would have got converted into product? At what time 80% of reactant would have got converted into product? And if 80% reactant gets converted into product, I would say 20% reactant would be left. 20% reactant would be left. 20% means how much reactant would be left? 0.2 A naught. So I have to check at what time the concentration of reactant left would be 0.2 A naught. At what time concentration of reactant left would be 0.2 A naught. So people, if I ask you how many conditions do we have here? We have got two conditions. Condition number 1, condition number 2. These are two conditions. I'll be using both the conditions in the integrated rate equation. The answer, I'm pretty much sure you know, answer will be 40 minutes. You can solve it with the help of shortcut as well. But I'm showing you the general approach of solving, right? Because everywhere you cannot use the shortcuts. Perfect. General approach is very important. See, these two conditions which we have, I'm going to introduce these conditions in the integrated rate equation. Integrated equation says that AT is equal to A naught minus KT. Now, put this condition here first. This condition says AT is equal to 0.8 A naught is equal to A naught minus K. T is equal to 10. So from here, K will be equal to 0.2 A naught divided by 10. So you got the value of K, rate constant. Since you got the value of K, now introduce this condition into this equation. So this condition says that AT is 0.2 A naught is equal to A naught minus K. K is 0.2 A naught divided by 10 multiplied by T. So A naught cancels out. So T comes out to be equal directly 40 minutes. So what was T? T was the time at which 80% of the reaction is getting completed. So I would say 80% of the reaction is getting completed in 40 minutes exactly, right? I hope I'm clear with this. Yes? Am I clear? Am I clear with this? Perfect. Let's see one more type of the question that can be asked. Look at this question, guys. It's a similar sort of question, right? And I'm pretty much sure you can easily solve this. I am pretty much sure you can easily solve this. See, guys, you have got a zero order reaction, and for the zero order reaction, some data is given. For the zero order reaction, some data is given. Let's say the zero order reaction is like this. A gives B. This is the zero order reaction. Concentration of reactant initially is equal to 1 molar. Initially means at time t is equal to 0. So at time t is equal to 0, concentration of reactant is equal to 1 molar. And concentration of reactant initially we represent with A naught. Okay. Now, if you look carefully, this is the time at which concentration of reactant is equal to 0. This is the time at which concentration of reactant left is 0, right? And what do we call that time when the concentration of reactant approaches to 0? We call that as the completion time. So I would say, as per the question, T 100% is also given to me. How much? T 100% is equal to 120 seconds. At that point of time, concentration of reactant left would be 0. Okay. What am I supposed to calculate? I am supposed to calculate what? Calculate the rate constant. See, we got to know completion time. T 100% is equal to 120, and completion time is nothing but A naught divided by K, which is equal to 120. So K will be equal to A naught divided by 120. What is A naught here? A naught is equal to 1. So 1 divided by 120, and answer is going to be in moles, liter inverse, second inverse. Why? Because time is given in seconds. Time is given in seconds. So this is what you call as the rate constant, which you were supposed to calculate as far as the question was concerned. I hope this also clear to everyone. So guys, this was all about your zero order reactions, and these were the different types of questions which can be asked. Okay. Now, I am moving on to the first order reactions. I am moving on to the first order reactions. I am moving on to the first order reactions and its integrated rate equations. Okay, this is one very important topic. First order reaction. First order reaction. How do you define the first order reaction? I would say these are the reactions. I would say the reaction in which the concentration of reactant, varies linearly. Wait. The reaction in which rate of the reaction varies linearly with the concentration of reactant. Varies linearly with the concentration of reactant. What does that mean? Let's try to understand each one of it one by one, step by step. See, whatever expressions I gave you for zero order reactions, similar expressions I'm going to give you for first order. I'm not going to derive any expression. I'll be giving you the expressions and we shall be applying those expressions in the questions. Okay? See guys. For example, imagine that you have got the reaction A gives B. At time t is equal to 0, this is A naught, this is 0. Let's say at time t, the concentration of reactant left is AT, the concentration of product formed is BT. Let's assume that. I'm assuming rate constant of the reaction is K, and at the same time, order of the reaction is equal to 1. Okay? Order of the reaction is equal to 1. First of all, how do you write the rate law? Rate law is written as R is equal to K, concentration of reactant raised per order here is 1. So this is what its rate law looks like. As you can see, rate is varying with the concentration of reactant linearly. What does that mean? If you double the concentration of reactant, rate becomes double. If you triple the concentration of reactant, rate becomes triple. If you make the concentration of reactant 4 times, rate becomes 4 times. So rate varies linearly with the concentration of reactant. Whereas in case of zero order reactions, rate does not vary with the concentration of reactant. In case of zero order, rate does not vary with the concentration of reactant. Here, rate varies linearly with the concentration of reactant. Perfect. Now, what are the expressions which we have to remember here? There are some different types of expressions which you need to remember. The first expression, guys, the first form of integrated rate expression. What is that? That is ln of AT is equal to ln of A naught minus KT. This is the first form of the integrated rate expression for the first order reactions. Second is a log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This is the second expression. Do remember these expressions directly, guys, which I'm giving you. Your K is equal to 1 divided by T ln of A naught divided by AT. K is equal to 1 divided by T ln of A naught divided by AT. The next expression is your K is equal to 2.303 divided by T log of A naught divided by AT. This is one more expression of the integrated rate law. For the first order reaction, right? Similarly, your AT is equal to A naught E raised power minus KT. This is one more expression which you'll be directly remembering. All these expressions, they were derivations, but I'm skipping the derivations. Those of no need for you at this particular point of time. You just have to remember the expressions and utilize these expressions in the questions. Next point is half-life. half-life of the first order reaction is equal to ln 2 by k, or you can say 0.693 divided by k. Completion time, T 100%. T 100% is equal to infinite. That means a first order reaction never undergoes 100% completion. A first order reaction never undergoes 100% completion. A first order reaction takes infinite time to complete. Remember it directly. Time taken to complete a certain percentage of the reaction. Time taken to complete X% of the reaction. X% can be anything, 20%, 30%, 40%, 50%. T X% is equal to 2.303 divided by K. It is the log of 100 divided by 100 minus 6. This is the formula which I'll be frequently using to calculate time taken to complete a certain percentage of the first order reaction, right? Then comes few more things. What are those? Time taken to complete 75% of the first order reaction is equal to 2 times the half-life. Time taken to complete 87.5% of the first order reaction is equal to 3 times the half-life. Time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life. Again, some direct questions can be made out of these direct results. Okay, some direct questions can be made out of these direct results. Similarly, there are a few more results which I would want you guys to remember. What are those? For example, concentration of reactant left at time t. Concentration of reactant left at time t can be written as A0 divided by 2 raised per n. Concentration of reactant left at time t is equal to A0 divided by 2 raised per n. N represents the number of half-lives. N represents the number of half-lives. How do you calculate N? N is equal to total time divided by T half. For example, what this N means? Let's say you have got the reaction, people. Let's say you have got the reaction whose half-life is equal to 10 minutes. You have got the reaction whose half-life is equal to 10 minutes. If half-life of the reaction is 10 minutes, what is meant by 20 minutes then? 20 minutes means 2 half-lives. 30 minutes means 3 half-lives. 40 minutes means 4 half-lives. So in short, number of half-lives is equal to total time divided by T half. Number of half-lives is calculated as total time divided by T half. Okay? Perfect. Similarly, one more thing. How do we calculate degree of dissociation alpha in case of the first order reaction? Alpha, already I have told you, alpha is equal to what? Number of moles of reactants dissociated divided by initial moles. How many moles of reactants got converted into product? A0 minus AT divided by initial is A0. So alpha is equal to A0 minus AT is A0 e raised power minus KT divided by what? Divided by A0, 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 everywhere cancelled. So 1 minus e raised power minus KT. This is how you calculate alpha. This is how you calculate alpha when it comes to the first order reactions. Okay, this is how you calculate alpha when it comes to the first order reaction. This is again one important expression. This has been frequently asked in the JEE Mains examination, and it's proper and neat standard question. It can be asked too. Right? Perfect. Now, let's have a look on one more thing. My dear students, imagine that you are given with a reaction like this. A gives B. Initially, its concentration is A0. This is 0. Let's say at time T1, the concentration of reactant left is AT1. At time T2, the concentration of reactant left is AT2. Let's assume that. Let's assume at time T1, the concentration of reactant left is AT1. At time T2, concentration of reactant left is AT2. And let's assume at the same time, at time T1, let's assume the rate of the reaction is R1. At time T2, the rate of the reaction is R2. Rate of the reaction is R2. Now, is there any expression which relates all these terms? There is one expression that can easily relate all these terms. I'm directly giving you the expression. I'm not deriving any expression here. So expression is K is equal to 2.303 divided by T2 minus T1, and it's going to be log of 81 divided by 82. 81 divided by 82. This is one of the important expressions from which question can be asked, or you can write it like this. 2.303 divided by T2 minus T1. This is log of R1 divided by R2. Perfect. These are the two expressions from which question can be made and question can be framed too. I hope this is clear to everyone till here. Okay. Now guys, one more thing. There are some graphs which we have to plot here, which can be framed in first order reactions. What are those graphs? How they look like? See, the first graph I can make is between ln AT versus T. Ln AT versus T. You know, your ln AT is equal to ln of A naught minus KT. Ln AT you are plotting along y-axis. T you are plotting along x-axis. K is your M. Sign is minus. This whole term is C. Y is equal to minus mx plus C. Y is equal to minus mx plus C means straight line with a negative slope. And I would say slope of this particular graph becomes minus K. This is the first graph which can be asked. Let's have a look on a few more graphs. For example, you've got a graph like this. Log AT versus T. Log AT versus T. People, right now, a few minutes back, I've given you one expression, that is log AT is equal to log of A naught minus K divided by 2.303 multiplied by T. Log AT you are plotting along y-axis, T you are plotting along x-axis. This becomes your M, sign is minus, and this is C. Y is equal to minus mx plus C, again straight line, right? Its slope now would be minus K divided by 2.303. Are these just the two graphs which can be framed? No. There are a few more graphs which can be asked here. What are those graphs exactly? For example, you're asked a graph like this. Rate of the reaction versus concentration of reactant. You know, in case of your first order kinetics, R is equal to K, concentration of reactant raised power 1. This is how you write rate law for the first order. If rate is plotted along y-axis, concentration of reactant along x-axis, this is your M. Y is equal to mx means straight line. So its slope has to be equal to the value of K. Slope has to be equal to the value of K. Right? Perfect. Similarly, for example, if they ask you a graph between, let's say, what else? T half versus A naught. If you remember, in case of the first order kinetics, T half is equal to 0.693 divided by K. So T half becomes independent of the initial concentration of reactant. T half is independent of the initial concentration of reactant. So the graph is going to be a straight line direct. It's directly going to be a straight line. Okay. Similarly, for example, if they ask you a graph like this, AT versus T, concentration of reactant left versus time. See, this is time T is equal to 0. At time T is equal to 0, concentration of reactant will be A naught. With time, the concentration of reactant will decrease. With time, concentration of reactant will decrease. But this graph will never touch the time axis. Why is that? Because if this graph touches the time axis, at that point, AT becomes 0. And if AT becomes 0, that means concentration of reactant left is 0. And if concentration of reactant left is 0, which means 100% of reaction has got completed. But we know a first order reaction never undergoes 100% completion. So remember, this particular curve is not going to touch the time axis at all. Okay? Perfect. These were some of the questions which can be framed from the first order. I mean, some of the results. Let's see what all different types of questions we have in case of the first order reactions. Can you solve this question? This is easy. You should be able to solve this question. The question is, a first order reaction is 75% completed in 100 minutes. A first order reaction is 75% completed in 100 minutes. That means T75%. T75% is equal to 100 minutes. Calculate the time taken for 87.5% completion. Time taken to complete 87.5% of the reaction. My dear students, we know already time taken to complete 87.5% is equal to 3 times the half-life, right? And time taken to complete 75% is nothing but 2 times the half-life. So I would say half-life here comes out to be 50 minutes. And if half-life is equal to 50 minutes, so 3 into 50 comes out to be 150 minutes. So this is going to be the time taken to complete 87.5% of the first order reaction. Okay? I hope this is clear. I hope this is clear. Yeah? Similarly, you can expect this sort of equation for an elementary reaction. You can expect this sort of equation for an elementary reaction. X gives Y. Elementary reaction. If it is elementary, for elementary reaction, order is equal to molecularity. Molecularity of the reaction is equal to 1. Therefore, this reaction follows the first order kinetics. Order of the reaction is 1. As far as the question is concerned, half-life of the reaction is also given to me. How much? Half-life of the reaction is given to me as 10 minutes. Okay. If half-life is given as 10 minutes, you know half-life is nothing but 0.693 divided by K. So this is 10. I would say K would be equal to 0.693 and it's going to be minute inverse. Right? This is the rate constant here, which I've calculated. Now, as per the question, in what period of time would the concentration of X be reduced? In what period of time would the concentration of X be reduced to 10% of its original value? So what are they asking technically? So initially, let's say the initial concentration of reactant is A0. In what time the concentration of reactant left would be 10%? That means technically they are asking you to calculate the time taken for the 90% completion. Because when 90% reaction would have got completed, at that point itself, I would say 10% of reactant would be left. When 90% of the reaction would have got completed, at that point only, I would say 10% of the reactant would have left. Okay? And that's what they are asking. At what time 10% of the reactant would be left? So they are asking you to calculate the time taken for 90% completion. So I would say, few minutes back, we have derived one result. That result was Tx% is equal to 2.303 divided by K. It is the log of 100 divided by 100 minus X, right? Time taken to complete a certain percentage of reaction. How much percentage? 90%. So T 90% here, I'll be writing as 2.303 divided by K. K is 0.693. This is a log of 100 divided by 100 minus 90 is 10. So log 10 is 1. So just solve it and get the answer in minutes. So here you'll be getting the time taken to complete. Here you'll be getting, oh, have I made a mistake here? K is equal to, okay, K is equal to 0.0693. Got it. 0.0693 minute inverse. So here it's going to be 0.0693. Now clear? So finally, the answer people are saying in the chats is coming out to be 33 minutes. So in 33 minutes, we can say 90% of the reaction has got completed. I hope this is clear. Yes? Perfect, perfect, perfect. Can you solve this question? Can you solve this question? For a first order reaction, choose the correct value of half-life. We have to calculate half-life for the first order reaction. People, half-life for the first order, you know, T half is nothing but 0.693 divided by K. So basically we have to calculate K. How do we get the K value? I'm given with a graph between log 80 versus T. Log 80 versus T slope, few minutes back only we have discussed. It is minus K divided by 2.303. This is the slope of the graph. Slope is nothing but tan of theta. Theta is 135. So tan of 135 is equal to minus K divided by 2.303. Tan 135 is equal to minus 1. So K is equal to 2.303 minute inverse. So if you got K, put the value of K here. That's it. So T half would be equal to 0.693 and K is nothing but 2.303. The value comes out to be 0.3 minutes. This is the half-life of the reaction which you were supposed to calculate. Nothing apart from this. I hope this is clear. I hope this is clear. Right? Similarly, guys, okay, if you look at this particular question, the question is, what amount of reactant for the first order reaction will be left after 3.5 minutes? What amount of reactant will be left after 3.5 minutes? Amount of reactant left means 80. 80 we have to calculate. Few minutes back, I gave you one expression direct. 80 is equal to A naught divided by 2 raised per n. This is one of the general expressions which I gave you. What is n? N represents the number of half-lives, which is total time divided by T half. What amount of reactant will be left after 3.5 minutes? So time is given to me as 3.5 minutes. What do I need to calculate? I need to calculate T half. What is T half all about? T half for the first order reaction is nothing but 0.693 divided by K. So in order to calculate T half, I need K. From where do I calculate K? K can be calculated from this graph. Graph is between ln 80 versus T. And ln 80 versus T slope, few minutes back we have discussed, is equal to minus K. And slope is tan of theta. What is theta? This is theta, which comes out to be 135. So tan of 135 is minus 1. So K comes out to be 1. And I think units are minutes, so it's going to be minute inverse. Yes, K is equal to minute inverse. So T half is equal to 0.693 minutes directly because K is equal to 1. If you put T half here, if you put T half here, 3.5 divided by almost 0.7, it comes out to be 5. So it's going to be A naught divided by 2 raised per 5, or I would say A naught divided by 32 molar. This is the concentration of reactant left after 3.5 minutes, or you can say this is the concentration of reactant left after 5 half-lives. Am I clear with this? Am I clear with this, guys? Everyone? Are we clear with this? Session will end by 11. Session will end at 11 p.m. Okay? Perfect, guys. Let's have a look on one more important topic, that is your collision theory, right? Collision theory, exactly. What this collision theory is all about. See, guys. Arrhenius bimolecular collision theory. See, first of all, this collision theory, I would say it is based on KTG. It's based on your kinetic theory of gases. And I hope you must be knowing, kinetic, as per KTG is concerned. As per KTG, the molecules of the gas, the molecules of the ideal gas, they are assumed to be hard and rigid spheres, right? So basically here, the molecules will be considering as spheres here also. Molecules will be considering as spheres here also. Now see what the collision theory actually is all about. See, guys, as per collision theory is concerned, for any reaction to happen, as per collision theory is concerned, for any reaction to happen, reacting species must collide first. For a reaction to proceed, for reactants to form products, the first thing, reacting species should collide first. Darsana, your second order is not in your syllabus, okay? Don't worry. As per your collision theory is concerned, for any reaction to happen, your reacting species must collide first. Okay? But remember, not from all the collisions. All the collisions between the reactants will not lead to the formation of products. Again, I'm repeating the same thing. As per your collision theory is concerned, reacting species must collide first. But all the collisions between the reactants will not lead to the formation of products. There are only few collisions. There are only few collisions between the reactants which will lead to the formation of products. And those collisions are what you call as effective collisions. Those collisions are what you call as effective collisions. Those collisions are what you call as effective collisions. Now, for the collision to be effective, there are two things. Two things are going to decide whether the collision between the reactants are going to be effective or not. One is going to be energy factor. One is going to be energy factor, and one is going to be the orientation factor. One is going to be the energy factor, one is going to be the orientation factor. As per energy factor is concerned, for the collision to be effective, energy of reactants should be greater or equal to the activation energy. As per energy factor is concerned, for the collision to be effective, energy of reactants should be greater or equal to the activation. Then only the collision is to be effective. As per orientation factor is concerned, collision has to happen with proper orientation. Collision has to happen with a proper orientation. Okay? Collision has to happen with a proper orientation. Now understand what exactly it's all about. See guys, again, let me reiterate the same thing. First of all, for the reaction to happen, for the reactants to form products, reacting species must collide first. Okay? All the collisions between the reacting species will not lead to the formation of products. There are a particular set of collisions through which product is formed. And you call those collisions as effective collision. For the collision to be effective, two factors decide whether the collision is going to be effective or not. Energy factor, orientation factor. As per energy factor, energy of reactant should be greater or equal to activation energy. As per orientation factor, the molecules are supposed to collide with the proper orientation. The molecules are supposed to collide with the proper orientation, right? Now, one more parameter which I'm going to write over here. Guys, these are the conclusions which I'm giving you, end results I'm giving you, okay? End results. Whatever is needed, whatever can be asked in your NEET examination, that's what I'm telling you. I'm not giving you the detailed explanation of everything. I'm just giving you the crux of the things which you have to remember, which can be asked. Understand that. Otherwise, collision theory, it will take 1-2 hours to be discussed, as we have discussed in game of NEET, right? So understand that. Remember, the fraction of molecules which have got energy greater or equal to activation. The fraction of molecules which have got energy greater or equal to activation energy is equal to e raised power minus Ea divided by RT. The fraction of molecules which have got energy greater or equal to activation energy is given by this particular expression. So this particular expression, it gives me the idea about those fraction of molecules which have got energy greater or equal to activation energy. Okay? And more the value of this particular term, that means more fraction of molecules have got energy greater or equal to activation. So more molecules can cross the barrier. And if more molecules can cross the barrier, more product formation. Hence, more is going to be the rate of the reaction. So in short, I would say rate of reaction is directly proportional to e raised power minus Ea divided by RT. And this e raised power minus Ea by RT is what you call as Boltzmann's factor. It's called as Boltzmann's factor. Okay, Boltzmann's factor. Now, there is one more thing which you need to know. What is that? That is collision frequency. Collision frequency, which we represent with ZAB. How do we define collision frequency? Number of collisions between the reactants, number of collisions per unit time, per unit volume. Number of collisions between the reactants per unit time, per unit volume, per unit time. Number of collisions per unit volume, per unit time. That gives me what? That gives me the collision frequency. Now you just tell me one thing. If collision frequency is more, That means more collisions will be happening between the reactants. If more collisions are happening between the reactants, can I say more are the chances of effective collisions? If more are the chances of effective collisions, can I say more product formation can take place? If more product formation can take place, can I say more is going to be the rate of the reaction? I would directly say your rate of reaction and collision frequency. Also, they are directly proportional. Perfect. Now, guys, one more thing. If I want to make the final equation about rate, R is equal to, so first of all, it is going to be E raised power minus EA by RT. It is going to be ZAB as well. Do you think in this equation there is some parameter missing? See, this particular parameter, it is considering your energy factor. But there is no parameter in this equation which is considering the orientation factor. So, I'll be writing a parameter P over here, which gives the idea about the orientation factor as well. Because not only one factor is going to decide whether the collision is effective or not. There are two factors basically. Okay? There are two factors basically which are going to decide whether the collision is effective or not. Perfect. So remove this final expression. Rate of reaction is equal to orientation factor, collision frequency, E raised power minus EA by RT. Perfect. Now guys, if you look at the energy diagram here, let's say I'm making a diagram for endothermic. For endothermic reactions. First of all, for endothermic reactions, your delta H, is it positive or negative? For endothermic reactions, your delta H is positive. You know it already. Okay. Now, how the graph looks like for this? This is energy versus reaction progress. Or I'll say progress of reaction. The graph for endothermic comes like this. This point represents your energy of reactants. This represents your energy of products. Okay, energy of products. This particular gap here is what you call as activation energy of forward reaction. This particular gap is called as activation energy of backward reaction. This particular gap represents your delta H, and delta H is always equal to EAF minus EAB. Okay, EAF minus EAB. This is valid for your endothermic reactions. Similarly, if you want to have a look on your exothermic graph, you can make the graph for exothermic as well. First of all, for exothermic reactions, your delta H, is it positive or negative? It is negative. If you want to plot a graph for exothermic, you can do that too. This is your energy. This is your progress of reaction. The graph, for example, starts from here and it comes down here. This point represents your energy of reactants. This point represents your energy of products. Similarly, this particular gap represents your activation energy of forward reaction. This particular gap represents activation energy of backward reaction. This particular gap represents your delta H. And here also you can say delta H is equal to EAF minus EAB. From this particular expression, remember a question has been frequently asked from past couple of years. Okay? Perfect. Right? Nihar, there is not the detailed discussion required for the pseudo first order. You can just remember its definition, that's it. You don't have to discuss its kinetics. Kinetics you have to discuss only for zero order and first order. Kinetics only you have to discuss for zero order and first order. For pseudo first order, you can just, remember the definition. That's it. Okay? I hope I'm clear with this. Okay, for example, I'm giving you a question like this. Can you let me know the answer of this question? Let's say A gives B is an exothermic reaction in which enthalpy change is 40 kilojoules per mole. Activation energy of backward reaction is equal to 20 kilojoules. Calculate activation energy of forward. Can you solve this question? I want to see what will be your answer. I want to see what will be your answer for this particular question. What do you think? See guys, first of all, the reaction is exothermic. If the reaction is exothermic, that means delta H has to be negative. So it has to be minus 40 kilojoules. Delta H is nothing but it is EAF minus EAB. EAF minus EAB is equal to minus 40. EAF I need to calculate. EAF is equal to minus 40 plus EAB. I think I need to change the values or no, it's fine. Is equal to minus 40 plus EAB. EAB is how much? EAB is how much? I have to change. I have given you the random values, so we need to modify the values first. Let me call this as just a second. Let's call this as EAF, and for example, you need to calculate EAB. You need to calculate EAB. You need to calculate EAB, and let's keep it as 80 kilojoules. Let's keep it as 80 kilojoules. Now tell me. I would say EAF is equal to minus 40. Sorry, we have to calculate EAB now. EAB we have to calculate. So I would say EAF plus 40 is equal to EAB. EAF is 80. 80 plus 40 is 120 is equal to EAB. So EAB we got to know as 120 kilojoules per mole. Okay, these sort of basic formula-based questions can be asked, but make sure you do not mess up here. See, the reaction in the reaction I had given that the reaction is exothermic, so you had to consider the sign as well, right? You are supposed to consider the sign as well. Perfect. Now, guys, there is one more topic from which the question frequently comes. What is that? That all of you would be knowing. That is your Arrhenius equation. That is your Arrhenius equation. Okay, that's your Arrhenius equation. See guys, what this Arrhenius equation is all about. As per your Arrhenius equation is concerned, I'm directly writing the equation. Rate constant of the reaction is equal to A e raised power minus EA by RT. K is equal to A e raised power minus EA divided by RT. If you look at this particular expression, on increasing the temperature of the reaction, what will happen to EA divided by RT term? If you increase the temperature, that means denominator you are increasing. If denominator you are increasing, whole term you are decreasing. This whole term you are decreasing. So if I multiply it with minus EA divided by RT, this entire term will be increasing. If minus EA by RT is increasing, so that means the entire term is increasing. Entire term means A e raised power minus EA divided by RT. This whole term is increasing. If this whole term is increasing, what does that mean? That means the rate constant of the reaction is increasing. So I must say, with the increase in the temperature of the reaction, rate constant increases. This is simply which you have to remember. Rate constant of the reaction is directly proportional to temperature. With the increase in the temperature, rate constant of the reaction that increases. Okay? With the increase in temperature, rate constant of the reaction increases. And remember one thing. Remember one thing, guys. I told you with the increase in temperature, rate constant of the reaction increases. Remember, on increasing the temperature by 10 degree, rate constant doubles or becomes even more. So when you increase the temperature of the reaction by 10 degree, rate constant, it doubles or becomes even more. Rate constant doubles or becomes even more. So here I'm going to define a term called as temperature coefficient. Here I'm defining a term called as temperature coefficient, which I'm representing with N. How do you define this temperature coefficient? It is defined as rate constant of the reaction at temperature T plus 10 degree divided by rate constant of the reaction at temperature T. So N would be equal to, if rate constant of the reaction at temperature T was K, so rate constant of the reaction at temperature T plus 10 degree would be 2 times K. So over here, N value comes out to be 2. Now it's not necessary that it will be 2K exactly here. It can be 2.1K, it can be 2.2K, because I told you on increasing the temperature by 10 degree, rate constant either doubles or becomes even more, right? So here I have mentioned that rate constant is doubling, but it can become even more. It can be 2.1K, 2.2K, 2.3K. So remember, temperature coefficient value, it's always between 2 and 3. Temperature coefficient value, it's always between 2 and 3. This was one more point. Similarly, there is one more point which I would want to share with you. What is that? Imagine that you have got the reaction A gives B. Let's say at temperature T1, rate of the reaction is R1. At temperature T2, rate of the reaction is R2. Now, is there any way we can relate all these 4 terms here? Yes, there is a way. I can say R2 is equal to 2 raised power delta T divided by 10 multiplied by R1. From this particular expression also, questions have been asked, questions will be asked too. For example, let's say you have got the reaction A gives B. I'm giving you a question like this. Let's say the temperature of the reaction is raised from 10 degree to 100 degree. Let's say the temperature of the reaction has raised from 10 degree to 100 degree. Since we know on increase in temperature, rate of the reaction increases, right? On increasing the temperature, rate of the reaction increases. We know that. Now we are increasing the temperature from 10 degree to 100 degree. How many times, or I will say, how many folds? How many folds rate of the reaction increases? Can you check it? Simple. It's pretty much simple. See, your T1, T2 is given, right? How many folds rate of reaction will increase? You'll directly say R2 is equal to R1, 2 raised power delta T, change in temperature. Final minus initial is 90 divided by 10. So R2 will be equal to 2 raised power 9 times R1. So rate has increased how many times? If the initial rate of the reaction was R1, now renewable rate of the reaction will be 2 raised power 9 times R1. So rate of reaction has increased 2 raised power 9 times. These sort of questions have been asked in different examinations, and you can expect these sort of questions as well in the upcoming examination too. Okay? Right? I hope this is clear. Now, if this is clear, there are a few more things which I would want to share with you. What is that? Remember, guys, for a reversible reaction, rate constant of forward as well as rate constant of backward reaction increases on increase in the temperature. For example, you have got the reaction like this, A gives B. Let's say rate constant of forward reaction is Kf, rate constant of backward reaction is Kb. If you increase the temperature of this reaction, On increasing the temperature of this particular reaction, Kf as well as Kb, Kf as well as Kb, both will increase. Both will increase by different amounts, but both will increase. Both will increase by different amounts, but both will increase. Okay? Remember that. When you increase the temperature, rate constant always increases, be it the rate constant of forward or the rate constant of backward. Both the things increase. Okay? I hope I'm clear with this. I hope I'm clear with this. Am I? Just let me know once in the chats. These are some important points, guys, which I'm telling you. Direct conclusions. Right? A hypothetical case I'm giving you. For a hypothetical reaction, whose activation energy is 0. For a hypothetical reaction whose activation energy is 0. See, rate constant for a hypothetical reaction whose activation energy is 0, rate constant becomes temperature independent. Rate constant becomes temperature independent. What exactly is the meaning of this stuff? Try to understand. See, guys, you know your K is equal to A e raised power minus EA divided by RT, right? If activation energy is 0, if EA is 0, this entire term becomes 0. Anything raised power 0 is 1. So K directly becomes equal to A. If K is equal to A, that means rate constant becomes temperature independent. So that particular reaction whose activation energy would be 0, I would say its a rate constant would be temperature independent. On changing the temperature, nothing happens to the rate constant. Remember this particular point as well. This is important. This is also important. Okay? Am I clear with this? Am I clear with this, guys? These are direct statement-based questions which can be asked. Direct statement-based questions which can be asked. Why I mentioned hypothetical reaction? Because as per your NCERT, there is no reaction which can have activation energy 0. Okay? As per your NCERT, there is no reaction which can have activation energy 0. Okay? Yes, this is according to your NCERT. Perfect. Now let's have a look on few more things when it comes to Arrhenius. See, guys. As per your Arrhenius equation, I told you your K is equal to A e raised power minus EA divided by RT. This is your one of the forms of the Arrhenius equation. Now, if we do one thing, if I multiply this equation with ln, it becomes ln of K is equal to ln of A minus EA divided by RT. This is one more form of the Arrhenius equation. Similarly, there is one more form which you can write as log of K is equal to log of A minus EA divided by 2.303 R multiplied by 1 by T. This is one more form of the Arrhenius equation. Okay. Similarly, I can make one more form. Log of K2 divided by K1 is equal to EA divided by 2.303 R. This is going to be 1 upon T1 minus 1 upon T2. These are different forms of the Arrhenius equation, and we can plot few graphs as well. Sir, what about second order? Second order is not in your NEET syllabus, okay? Don't worry. Second order is not in the syllabus. Yes, Mohammed Rafi, you can consult it. All right, let's have a look on few graphs. The first graph which I'm making over here is between ln K versus 1 by T. Ln K versus 1 by T. People, ln K and 1 by T. Ln K and 1 by T. Ln of K you are plotting along y-axis. 1 by T you are plotting along x-axis. This is your M. Sign is minus and this is C. So y is equal to minus mx plus C. Y is equal to minus mx plus C. So it's a straight line like this. Minus mx plus C. So slope of this particular graph will be equal to minus EA divided by R. And I would say its intercept. Its intercept would be equal to ln of A. Similarly, if you plot a graph between log of K versus 1 by T. Log of K versus 1 by T is going to be a similar graph. But remember, its slope now will be equal to minus EA divided by 2.303 R. And here, I would say its intercept would be equal to log of A. Would be equal to log of A. Okay? See guys, what kind of questions can be asked from Arrhenius? This can be first and the basic question asked. Calculate the activation energy. Calculate the activation energy in kilojoules per mole or kilocalories per mole. Kilojoules per mole or kilocalories per mole. See guys, log K versus 1 by T graph is given. We know slope of this graph, log K versus 1 by T, is equal to what? Minus EA divided by 2.303 R. Right? Slope is nothing but tan of theta. Slope is nothing but tan of theta, and you know this is your theta here. This is the theta, which is tan inverse minus 3, or you can directly say tan theta is equal to minus 3. So is equal to tan of theta, and tan theta is equal to minus 3, or I would say EA is equal to minus 3. Sorry, EA will be equal to minus gets cancelled. It becomes 2.303 multiplied by 3 multiplied by R. This is your activation energy. Now, depending on the value of R, first answer I need to get in kilojoules per mole. If I need to get the answer in kilojoules per mole, I'll be taking the value of R as, see, this will be 2.303 multiplied by 3. R value I'll be taking as 8.314 joules per Kelvin per mole, but I'll be dividing with 1000, then only it will be coming in kilojoules, right? Similarly, if I need the answer in kilocalories per mole, then I will take the value of R as 2. So it is 2.303 multiplied by 3. R value I'll be taking as 2 calories divided with 1000. Now the answer will be in kilocalories. Perfect. This can be one of the types of the question which can be asked. Okay. This is one of the types of the questions that can be asked. Similarly, I believe this sort of a question you can easily solve, right? You can see it is completely formula-based question. This is one more type of question that can be framed, right? At two different temperatures, your rate constants are given. You have to calculate activation energy. So basically K1, K2 is given, T1, T2 is given. R value you know, you just have to calculate EA. Activation energy you have to calculate after putting the values. That's it. So it becomes your, formula-based question. So why did you divide with 1000? Because if I do not divide with 1000 here, the answer will be coming in joules, because I use the value of R as 8.314 joules per Kelvin per mole. Okay, that's why I'm dividing with 1000 to get the answer in kilojoules. Similarly, if I do not divide with 1000 here, I'll be getting the answer in calories. That's why I divide with 1000. The answer came out to be in kilocalories. Okay. Perfect. So guys, let me tell you, if whatever things I've told you in the chemical kinetics one, if you just follow this particular one, you'll be getting a question directly from these topics only. You will be directly getting the questions from these topics only, whatever I've told you. It is just you need to revise it. That's it. Okay. Electrochemistry will be starting after the break. Okay. So at what time you'll be back? Tell me. Break till 3:30. Okay. It's okay. Break till 3:30. At 3:30 exactly, I'll be starting the electrochemistry. So be back on time. Okay. Be back on time. Everyone. I'll see you. Is everyone back? Welcome back. Perfect. So should we start electro now? Should we start the electrochemistry now? Welcome back. Ready for electro? Sangeeta, your live class will be scheduled from tomorrow in the batch. Okay? It will be scheduled from tomorrow in the batch. Perfect. Tell me, have you studied this chapter before? Have you studied this chapter before? Okay. Majority has studied, huh? Got it. Whatever things I have discussed in chemical kinetics, just be relaxed. Everything will be asked from this only. Whatever things you'll be seeing in your modules and all, like the theoretical part, factors affecting rate, etc., that's not asked. That's a pure boards question, huh? That's a pure boards question. Okay, so let's start the chapter electrochemistry then. My dear students, in the electrochemistry chapter, the first topic that we shall be discussing, which is asked frequently, right? What is that? That is your Daniell cell. That is your Daniell cell. So, let me tell you the Daniell cell which we are going to discuss. It is the most typical example of the galvanic cell. It is the typical example of the galvanic cell. And what does a galvanic cell do? Galvanic cell converts chemical energy into the electrical energy. Galvanic cell converts chemical energy into the electrical energy. Now, people, let's exactly see how this Daniell cell, which is the typical example of the galvanic cell, is going to convert chemical energy into the electrical energy. Let's understand this one by one. Okay. First of all, if I talk about the Daniell cell, in the Daniell cell, we have got two electrodes. Imagine here, I'm taking a container. And in this particular container, I'm keeping zinc sulfate. If I'm keeping zinc sulfate in this container, this zinc sulfate would have dissociated into zinc dipositives and your SO4 dinegatives. So I'm assuming right now in the container there are equal number of cations and anions present. There are equal number of cations and anions present. In this container, I'm introducing a rod. I'm introducing a zinc rod, the rod which is made up of zinc atoms. So this zinc rod I've introduced into a solution. The zinc rod I've introduced into a solution containing its own ions. Whenever a rod is dipped into a solution containing its own ions, let me tell you this setup, this entire setup, I'll be calling as electrode. So which electrode this is? This is your zinc electrode over here, which I've taken. Number one. Number two, here I'm taking one more container. And in this particular container, my dear students, what exactly am I keeping? I'm keeping copper sulfate. I'm keeping copper sulfate in this container. And this copper sulfate would have dissociated as copper dye positive plus SO4 dye negative. So in this solution, imagine right now there are equal number of cations and anions. So this solution right now is electrically neutral. Now in this particular container, I'm introducing a rod. Which rod? I'm introducing a copper rod. I've introduced copper rod into this particular solution. I've introduced copper rod in a solution containing its own ions. So this setup also I'll be calling the electrode. Which electrode this is? This is the copper electrode. So how many electrodes we have? Two electrodes. One is your zinc electrode, one is your copper electrode. My dear students, I am connecting these electrodes externally. I'm connecting these electrodes externally and I'm connecting these electrodes internally as well. Well, internally I'm connecting these electrodes with the help of inverted U-type tube. And this inverted U-type tube, it contains inert electrolyte. Inert electrolyte like your K2SO4, like your NH4Cl. So this inverted U-type tube contains inert electrolyte which is mixed with gelatin. And let me tell you, whenever the inert electrolyte is mixed with gelatin, what do we get? We get a jelly-like paste. And that jelly-like paste is basically inserted in this inverted U-type tube. And this inverted U-type tube, its ends are sealed with cotton balls. And let me tell you, this inverted U-type tube, right, which I've used over here, I'm calling this as the salt bridge. So people, I have taken two electrodes, connected them externally as well as internally. Now, the zinc electrode here in this Daniell cell, it behaves like your anode. And the copper electrode here, it behaves like the cathode. And remember, at anode, oxidation takes place. And at cathode, reduction takes place. At anode, oxidation takes place. At cathode, reduction takes place. Oxidation means loss of electrons. Reduction means gain of electrons. So what happens here? At anode, since I told you at anode, oxidation takes place. This rod is made up of zinc atoms. And the zinc atoms of which rod is made up of, those zinc atoms will undergo oxidation, will get converted into zinc dye positives and will give 2 electrons. The rod is made up of zinc atoms. Those zinc atoms will undergo oxidation. They'll get converted into zinc dye positives and will give 2 electrons, right? These 2 electrons are accumulated on the rod, and this zinc dye positive goes into the solution. Earlier, the solution was neutral. There were equal number of cations and anions present. Now, the extra zinc dye positive goes into the solution, due to which solution gets the positive charge. And since the electrons are accumulated on the rod, due to which this rod gets the negative charge. Okay? Due to which this rod gets the negative charge. Now, what happens exactly at cathode? As I told you already, at cathode, reduction takes place. Reduction means gain of electrons. In this solution, there are copper dipositives, and these copper dipositives would be colliding with the rod. Copper dipositives in the solution, they would be colliding with the rod. They'll be taking 2 electrons from the rod, getting converted into copper solid. The copper dipositives in this solution, they would be colliding with the rod. They would be snatching 2 electrons from the rod and will be getting converted into copper solid. And that copper solid would be deposited on this particular rod. Since electrons are being snatched from the rod, therefore rod gets which charge? Rod gets positive charge. Okay. Now people, if you understand properly, see, electrons are accumulated on this particular rod. Electrons are accumulated on this particular rod. The path is already made. The path is already made. Can I say there will be movement of electrons through this particular path in the external circuit? There will be movement of electrons. Is it just the movement of electrons? No. I would say it is the movement of electrons in a particular direction. It is the movement of electrons in a particular direction. And whenever electrons move in a particular direction, current gets generated. Okay, current gets generated, due to which there will be deflection over here. There will be deflection over here, right? So people, what is happening here? When I'm connecting these 2 electrodes, at anode oxidation is happening, at cathode reduction is happening, due to which electrons are accumulated on this rod. And finally, there is the directional movement of electrons. Directional movement of electrons, due to which current is produced. Due to which current is produced. So what is the main use of this particular cell? It converts your chemical energy, right, into what? Into your electrical energy. I hope this is clear. I hope this is clear. So the first and the most important point, what is the direction of electrons here? The direction of electrons is from anode to cathode. Direction of electrons is from anode to cathode. And if you know the direction of electrons, opposite to the direction of electrons would be the direction of current. So what would be the direction of current? It would be from cathode to anode. It would be from cathode to anode, right? It would be from cathode to anode. Now, since this zinc rod is made up of zinc atoms, and those zinc atoms are undergoing oxidation, getting converted into zinc dipositives, and those zinc dipositives are entering into the solution. So what would be happening to the thickness of zinc rod? Thickness of zinc rod decrease with time. Since copper is being accumulated on this rod, so thickness of copper rod would be increasing with time. With time, the thickness of zinc rod would be decreasing and the thickness of copper rod would be increasing. Now people, this is the reaction at anode, this is the reaction at cathode. Now, if I ask you to write the net cell reaction, net reaction. In order to write the net reaction, what do I need to do? I need to add these 2 reactions. But remember, these 2 reactions will be only added if electrons are balanced in these 2 reactions. These 2 will be only added if electrons are balanced. And if you can see properly, electrons are balanced here. So if electrons are balanced, I can directly add these 2 reactions. And when these reactions are added, my net reaction is going to be zinc solid plus copper dipositive aqueous. It gives zinc dipositive aqueous plus copper solid. This is your net reaction. This is your net reaction. Now, my dear students, this is your net reaction. Tell me how many electrons got cancelled here? 2. So I would say N value is equal to 2. What does that mean? Number of moles of electrons exchanged. Number of moles of electrons exchanged in the net cell reaction is nothing but 2. Okay? Is nothing but 2. Perfect. Clear till here? Clear, guys? Now, this salt bridge which we have used, what are the functions of this salt bridge? Let me tell you, first of all, your salt bridge over here, it completes your internal circuit. It completes the internal circuit. Number 1. Number 2, it maintains the electrical neutrality. It maintains the electrical neutrality of both the solutions. Or in other words, I can say it avoids the liquid junction potential. It avoids the liquid junction potential. Remember these three, right? Important things about the salt bridge. Salt bridge here, it will be completing the internal circuit. It maintains the neutrality of these two solutions, and it avoids the liquid junction potential as well. These are the three important uses of the salt bridge which we use here in case of Daniell cell. So what is the main function of the Daniell cell? What does it do? This Daniell cell, I must say, it converts your chemical energy into electrical energy, number one, right? It converts your chemical energy into electrical energy, okay? And the main features about this particular cell is reaction at anode, reaction at cathode, net reaction, value of N, electron movement, current movement, zinc rod thickness, copper rod thickness, right? Functions of salt bridge, all these things. Among all these particular things, anything can be asked in your examination. Okay? Number one. Number two, how do you represent a cell? How do you represent a cell basically? Okay? How do you represent a cell? Understand. Cell representation. You just draw two lines, and these two lines, they represent your salt bridge. They represent your salt bridge, okay? On the left side of the salt bridge, you'll be always writing anode. On the right side of the salt bridge, you'll be writing the cathode. Okay, you'll be writing the cathode. Guys, let me tell you again, whatever things we are going to discuss in the marathon, like we'll be only discussing those things which will be directly asked in your examination. Okay? We are not going to discuss anything in very detailed form like we did in the game of NEET, right? Every single thing was being discussed in very detailed form. So here we are keeping the lectures short, precise, to the point. Okay? Short, precise, to the point. Wherever I would feel explanation is needed, I'll give explanation there. Wherever I feel explanation is not needed, the best way is to remember things. There you will have to remember things. Okay? So this is your short and precise, crisp to the point. Perfect? All right. So in between, we draw two lines which represent your salt bridge. On the left side of the salt bridge, we have got anode. On the right side of the salt bridge, we have got cathode. Now, people, how do we represent the cells exactly? For example, have a look. Let's say you have got a galvanic cell in which the net cell reaction is like this. Zinc solid plus copper dye positive aqueous gives zinc dye positive aqueous plus copper solid. Let's say this is the net cell reaction. This is the net cell reaction given in some cell. Okay? Given in some cell. Now, from this net cell reaction, how do we represent the cell? How do we represent the cell in which the cell reaction is this one? Okay. See. First of all, if I ask you what is the oxidation state of zinc here, it's 0. Oxidation state of copper, +2. Oxidation state of zinc, +2. Oxidation state of copper, 0. Now, is the oxidation state of zinc increasing or decreasing? 0 to +2, increase. And you know, increase in the oxidation state is something which we call as oxidation. And oxidation takes place at anode. Similarly, +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. And reduction takes place at cathode. So first of all, you identified your anode and cathode. You identified your anode and cathode. Well, after identifying the anode and cathode, I'll be drawing two lines which represent your salt bridge. On the left side of the salt bridge, I'll be writing anode. At anode, zinc is getting converted into zinc dye positive. At anode, zinc solid is getting converted into zinc dye positive aqueous. Now tell me one thing. Is the phase over here same or different? This is solid, this is aqueous. So phase is different. When the phase is different, you'll be separating them with a single line. When the phase is different, separate them with a single line. If the phase is same, separate them with the help of comma. That's it. If the phase is different, single line. If the phase is same, comma. Now, on the right side, what do? We write cathode. At cathode, reduction takes place. Copper dye positive gets converted into copper solid. Copper dye positive aqueous gets converted into what? It gets converted into copper solid. Okay? Aqueous solid. Phase is different. So draw a single line. So you have represented your cell successfully over here. Okay. This is how you represent the cell out from the given cell reaction. Let me show you one more case. For example, you have got a galvanic cell in which the net cell reaction is, let's say, like this. Zinc solid plus twice Ag positive aqueous. Let's say it gives your zinc dye positive aqueous plus 2 times Ag solid. For example, you have got a galvanic cell in which the net cell reaction is this. Net cell reaction is this. Okay. From this net cell reaction, you have to represent the cell. What do you do here? Again, the same process. Zinc oxidation state 0. Silver oxidation state plus 1. Zinc oxidation state plus 2. Silver oxidation state 0. Now, 0 to plus 2. 0 to plus 2. Increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. I would say the zinc is undergoing oxidation here. Ag positive. Plus 1 to 0. Decrease. Decrease means reduction. So this Ag positive is undergoing reduction here. And you know, oxidation takes place at anode and your reduction takes place at cathode. Okay. What I'll be doing? I'll be drawing two lines. They represent the salt bridge. On the left side, you write anode. At anode, oxidation takes place. Zinc solid gets converted into zinc dye positive. So at anode, your zinc solid gets converted into zinc dye positive aqueous. Phase is different, draw a single line. Okay. Perfect. On the right side, what do we do? On the right side, we write cathode. At cathode, reduction takes place. At cathode, reduction takes place. Ag positive is getting converted into Ag. So I would write Ag positive aqueous getting converted into Ag solid. Phase is different, draw a single line. So you have represented this particular cell as well. You have represented this particular cell as well. Okay. Perfect. My next marathon is going to be class 11th in organic chemistry. Class 11th in organic chemistry will be my next marathon. I'll be taking that. Okay, let's have a look on one more case. For example, you have got the net cell reaction given like this. H2 gas plus copper dye positive aqueous. It gives 2 times H positive aqueous plus copper solid. This is your net cell reaction. That's given. From the net cell reaction, we have to represent the cell. How do you do it? Two lines. Two lines represent the salt bridge. Now, oxidation state of hydrogen here is 0. Here it's plus 2. Here it's plus 1. Here it is 0. Now check it out. 0 to plus 1. Increase in the oxidation state means oxidation. Oxidation takes place at anode. So this is your anode and automatically this becomes your cathode. And now, on the left side of the salt bridge, you write anode. At anode, your H2 gas is getting converted into what? Is getting converted into H positive aqueous. Is the phase same or different? Phase is different. So, single line, right? Okay. Now guys, understand. H2 gas, H positive. Tell me how I told you electrode is made. Let's say you have to make a zinc electrode. What do? You take the zinc rod, introduce the zinc rod into the solution containing zinc ions. Here you have to make the hydrogen electrode. Can you take the hydrogen rod directly? Can you take the hydrogen rod directly? You cannot do that. You cannot do that. So, you'll be taking the help of platinum solid here. How exactly? I'll show it in some time. Whenever a electrode is not made normally under normal conditions, what do we use? We use platinum solid there. We use platinum solid. Or you can use graphite. Generally, we use platinum. Now, on the right side, what do we have? On the right side, we have got cathode. At cathode, reduction takes place. Copper dye positive gets converted into copper. So I would say copper dye positive aqueous is getting converted into what? Copper solid. Phase is different. So draw a single line. So this is how you have represented this particular cell as well. Okay. You can directly solve questions after this particular session. Is it clear? Is it clear, guys? So basically, this was a hydrogen electrode. Hydrogen electrode is not made under normal conditions. How can you make hydrogen electrode? How do you make, basically, how do you make the electrode? You take the rod. Let's say you have to make the electrode of copper. You'll be taking the copper rod first. You'll be introducing that copper rod in a solution containing its copper ions. Okay? You'll be taking the copper rod first. You'll be introducing the copper rod into a solution containing copper ions. The whole setup I'll be calling as copper electrode. Right? Now here, you have to make hydrogen electrode. Hydrogen is gas. How do you make the rod of gas? Cannot make it normally. So for that purpose, you'll be using platinum solid. Okay? Session PDF you'll be getting on my Telegram, Wassim Bhat Chemistry Official. I hope this is clear. Now guys, let's see some other things. What are those other things? Have a look. Imagine that you're given with a cell like this. Zinc solid, zinc dipositive aqueous, zinc solid, zinc dipositive aqueous, salt bridge, copper dipositive aqueous, copper solid. Imagine this is your cell that's given to us. Now from the cell, what all things we can depict? What all things we can do? First of all, we can write the reaction which would be taking place at anode. See, on the left side of the salt bridge, we always have the anode. And at anode, you can see zinc is getting converted into zinc dipositive. So the reaction is going to be zinc solid getting converted into zinc dipositive aqueous and will be losing 2 electrons. Right? Zinc would be losing 2 electrons, getting converted into zinc dipositive. Okay? Perfect. Now, what would be the reaction taking place at cathode? At cathode, what happens? A reduction. Reduction means gain of electrons. So your copper dipositive is getting converted into copper solid. I would say copper dipositive aqueous would be gaining 2 electrons, getting converted into copper solid. Right? Because at cathode, reduction takes place. Reduction means gain of electrons. Okay? Perfect. Now guys, in both the reactions, are the electrons balanced? Yes, the electrons are balanced. And if the electrons are balanced, what do we do? If the electrons are balanced, you'll be directly adding the reactions. When you add the reactions, your net reaction becomes like this. Zinc solid, copper dipositive aqueous, zinc dipositive aqueous, and copper solid. This is your net reaction. This is your net reaction. Once you make the net reaction, if I ask you how many moles of electrons are exchanged in the net cell reaction, you'll say 2 moles of electrons are exchanged in the net cell reaction. Okay. Now, the last point, how can you write the reaction quotient? How can you write the reaction quotient? See guys, how do we write the reaction quotient? See, reaction quotient is written the similar way as you write the expression for equilibrium constant. Now, how exactly? Have a look. QC is equal to, first of all, that reactant product which will be in aqueous state, you will be using the term concentration for that. That reactant product which will be in solid state, you have got nothing to do with it. It's ectomasses unity. That reactant product that is in gaseous state, you will be using pressure for that. You'll be using pressure for that. You'll be using pressure for that. These are the 3 things which first of all you have to remember. That reactant or product which will be in aqueous state, you'll be using concentration for that. Solid, nothing to do with that. Gas, you'll be using the term pressure for that. Pure liquid, nothing to do with that. It's ectomasses unity. Now, understand. In order to write the QC expression, you'll be always starting with the product. Start with the product. This particular product is in aqueous state, and the one that's in aqueous state, we use the term concentration for that. So I'll be writing concentration of zinc dipositive raised power stoichiometric coefficient, that's 1. Multiplied by. Look at this product. It's in solid state. If it is in solid state, it's ectomasses unity. Nothing to do. Nothing to do. Divided by. This is in solid state. It's ectomasses unity. Nothing to do with it. Now, this particular one, it's an aqueous state. So you'll be using the term concentration. So concentration of Cu dipositive raised power 1. So with this, like this, you get QC for the reaction. you get N value for the reaction, you get the net cell reaction as well. Okay, let me take a few more examples so that you understand all this properly. See guys, for example, I've got the reaction like this. Sorry, I've got the net cell reaction. I've got the cell like this. Platinum solid. Let's say this is your H2 gas. This is your H positive aqueous. For example, you have got Ag positive aqueous here, and this is Ag solid. Let's say this is the cell. Now, from this cell, we have to write all the things again. From this cell, we have to write all these things again. First of all, what is the reaction at anode? At anode, oxidation takes place, right? Your H2 is getting converted into H positive. I would say H2 gas is getting converted into 2 times H positive aqueous, and with this you'll be writing 2 electrons. This is the reaction at anode. Similarly, what is going to be the reaction at cathode? At cathode, a reduction takes place. Ag positive getting converted into Ag. So I would say Ag positive aqueous will be gaining 1 electron and getting converted into Ag solid. If I ask you, are the electrons balanced in both the reactions? No, electrons are not balanced in both the reactions. Here you have got 2, here you have got 1, right? So I'll just multiply this reaction with number 2 so that electrons are balanced. So after multiplying this reaction with number 2, electrons are balanced. Now, tell me what is the net cell reaction? Net cell reaction is going to be H2 gas plus 2 times Ag positive aqueous. It gives 2 times H positive aqueous plus what? Plus 2 times Ag solid. This is your net reaction. This is your net reaction. My dear students, since this is the net reaction, if I ask you how many moles of electrons are exchanged here, 2 moles of electrons are exchanged. Can we write the QC expression? Absolutely, we can do that. How do we write the QC expression? We start with right. We start with right, with the products. This product is in aqueous state, so write the term concentration. So concentration of H positive raised power 2. This is in solid state, its active-mass is unity, nothing to do with this. Divide by. This is in gaseous state, we use the term partial pressure, pressure of H2 raised power 1. This is in aqueous state, we use the term concentration, so concentration of Ag positive raised power 2. So this is how you get QC expression over here, right? Am I clear with this? After this, after platinum, you'll be always writing comma only. This line or comma is here, right? Here always you have to write comma only. You don't have to show it. I hope all this is clear till here. Okay, let me take one more example. Let me take one more example. Can you write all the things for this particular cell? Can you write all the things for this particular cell? Hiba Fazal, it is possible. Just start studying for 10-12 hours a day. Why not? See guys, here you might do certain mistakes. Here you might do certain mistakes. Here you might do certain mistakes. See, on the left side of the salt bridge, anode. What happens at anode? Oxidation. Fe di positive getting converted into Fe tri positive. So Fe di positive aqueous is getting converted into what? Fe tri positive aqueous plus 1 electron. Reaction at anode. Similarly, reaction at cathode. Reaction at cathode. At cathode, what is happening? Manganese here is in +7 oxidation state, so +7 to +2. Decrease. Decrease means reduction, gain of electrons. So I would say MnO4 negative aqueous would be gaining 5 electrons and then getting converted into Mn di positive aqueous. Right? So I wrote the reaction at anode, I wrote the reaction at cathode as well. Yeah? Now, are the electrons balanced? Electrons are not balanced yet. So balance the electrons. You'll be multiplying this reaction by number 5. When you multiply this reaction by number 5, this becomes 5, this becomes 5, this becomes 5. So electrons are balanced. If electrons are balanced, so add the reactions. When you add the reactions, your net reaction becomes 5 times Fe di positive aqueous plus MnO4 negative aqueous. It gives 5 times Fe tri positive aqueous plus Mn di positive. Now, if I ask you whether this is the net reaction or not, this is not your net reaction yet. This is not your net reaction yet. See, no doubt, iron is balanced, manganese is balanced, but oxygen is not balanced. So I'll be balancing oxygen with the help of what? With the help of water. I'll be balancing oxygen with the help of water. See, you've got 4 oxygen here, you've got no oxygen here. So right side is oxygen deficient. Right side is oxygen deficient. That side which is oxygen deficient, add water molecules to that side. How many? Here you have got 4 oxygen. So add 4 water molecules on that side. Which side is oxygen deficient? Right? Now oxygen got balanced. Now hydrogen is not balanced. You have got 4 2s are 8 hydrogen on this side, but no hydrogen on this side. So this side is hydrogen deficient. How many hydrogen deficiencies? 8. So in order to avoid 8 hydrogen deficiencies, add 8 H positives on this side. Now the reaction is balanced. Now it's a complete balanced chemical equation. If it is a complete balanced chemical equation, you can write the expression for QC. Start with the product. Aqueous state, concentration. Concentration of Fe tri positive raised by stoichiometric coefficient 5. Mn di positive aqueous, concentration. M N di positive aqueous. This water is a liquid state, nothing to do with it. Divided by this H positive is aqueous state, so concentration of H positive raised by 8. Fe di positive concentration raised by 5. MnO4 negative concentration raised by 1. This is how you are going to get the QC as well. Now, if I ask you, what is the value of N? How many moles of electrons got exchanged? 5 moles of electrons got exchanged. 5 moles of electrons got exchanged in the net cell reaction, so N value is just 5. So these are some basic things which you must know, right? I hope this is clear to everyone. I hope this is clear to everyone. Now we are going to move into electrode potential. Okay? Electrode potential. How do we exactly define the term electrode potential? First of all, electrode potential, it is denoted by capital E, right? Now, how do you define it? What is electrode potential? What is electrode potential? See guys, electrode potential is defined as the potential difference created between the rod and the electrolytic solution. The potential difference which gets created between the rod and the solution. What does it mean? Try to understand. For example, let's say I'm taking zinc sulfate. Let's say this is zinc sulfate which I'm taking in the container. I'm assuming this zinc sulfate, it has got converted, it has got dissociated into its ions. Its ions are zinc dipositives and SO4 dinegatives. So I'm assuming this particular solution is right now electrically neutral as it has got equal number of cations and anions into it. this solution. It's right now electrically neutral because it has got equal number of cations and anions into it. Now, if I introduce a zinc rod here, so I've introduced a rod into a solution containing its own ions. So this setup I'll be calling as electrode. This is your zinc electrode basically, right? This is your zinc electrode. Now, my dear students, if this is your zinc electrode, it can behave like anode or it can behave like cathode. Depends, right? It has got the capability to behave like anode as well as cathode. If the zinc electrode behaves like anode, for example, if the zinc electrode behaves like anode, what happens at anode? Oxidation. So, rod is made up of zinc atoms. Those zinc atoms will undergo oxidation. And you know, when zinc undergoes oxidation, it gets converted into what? Zinc di-positive. And with that, you get 2 electrons. These electrons are accumulated on the rod. And this solution, which was initially electrically neutral, now extra zinc di-positives entering into the solution, due to which solution gets with charge. Solution gets positive. Since electrons are accumulated on the rod, can I say rod gets negative? Since negative charge is accumulated on the rod, negative is accumulated on the rod, right? Positive charge is there on the solution. So can I say between the rod and the solution, potential difference got created? This potential difference which gets created between the rod and the solution, potential difference that gets created at the interface between the rod and the solution, right? That potential difference is what you call as electrode potential. Okay, that's what you call as electrode potential. Perfect. Did you understand what electrode potential is? Did you understand what electrode potential is? It is nothing but the potential difference that gets created between the rod and the electrolytic solution. Okay. Now, this electrode potential which we are talking about, as I told you, this electrode potential is represented by what? This electrode potential is represented by E. Represented by E. And let me tell you, this electrode potential, we classify into 2 types. We classify electrode potential into 2 types. One is called as oxidation potential. One is called as the reduction potential. Oxidation potential and reduction potential. Oxidation potential, you can represent it like this as well. E of M gives Mn positive. Reduction potential, you can represent it like this. E of Mn positive gives N. See, oxidation state of M here is 0, 0 to plus N means increase in the oxidation state. Increase in the oxidation state means oxidation, right? So this is oxidation potential. Similarly, plus N to 0, decrease in the oxidation state, reduction. So this represents your reduction potential. So one is your oxidation potential, one is your reduction potential. Okay. Now guys, one more thing. Electrode potential when measured, under standard conditions. Electrode potential when measured under standard conditions is called as standard electrode potential, which is represented by E naught. Whenever electrode potential is measured under what? Under standard conditions. Standard condition means, what is first of all electrode potential? It is the potential difference between the rod and the solution. When that potential difference is measured under standard conditions. Standard condition means when pressure is kept as 1 bar, temperature is kept constant, generally 25 degrees centigrade. Concentration of solution is kept as 1 molar. This is what you call as the standard conditions. And when electrode potential, when the potential difference between rod and the solution is measured under standard conditions, you call it as the standard electrode potential. And this standard electrode potential is represented by what? It's represented by E naught, right? So I'll be classifying this also into 2 types. One is called as standard oxidation potential. One is called as the standard reduction potential, right? Is there any other way of representing this? Yes. So it's going to be E naught of M gives Mn positive. Similarly, this is going to be E naught of Mn positive gives M. This is your, you can call it as SOP, standard oxidation potential. You can call this as SRP, standard reduction potential, right? Standard oxidation potential, standard reduction potential. Perfect. Now guys, one more thing. Remember, for an element, standard oxidation potential is always equal to minus times standard reduction potential. Remember this particular point as well. So if you have got the element, whose oxidation potential is, for example, 1.1 volt, so its reduction potential will be minus 1.1 volt. Perfect. So remember this particular thing as well. Okay. Now the point is, what kind of information this SOP and SRP gives us? Okay, what kind of information this SOP and SRP gives us? Before talking about that, remember one more point. See, you would have seen in your NCERT a series of elements is given, right? And in that particular electrochemical series, I hope you have seen that. In that electrochemical series, SRP as well as SOP of all the elements is given, right? You call that particular series as electrochemical series, right? I hope you would have seen that. So in electrochemical series, we have got the SOP, SRP of all the elements. We know the SOP, SRP of all the elements. The point is, SOP or SRP of the elements is calculated with the help of a reference electrode. With the help of the reference electrode. And that reference electrode is what you call as standard hydrogen electrode. So whatever electrochemical series you see on which the SOP, SRP of all the elements are given to us, those SRPs of all the elements have been calculated by taking a reference electrode, which is called as standard hydrogen electrode, right? Remember this particular point as well. Now, the point is, where is all this used? Where is this SOP, SRP used? See, guys. One important point. SOP of an element. It gives an idea about the tendency of an element to undergo oxidation. It gives the idea about the tendency of an element to undergo oxidation. Similarly, if I talk about your SRP gives us the tendency of an element to undergo reduction. SOP of an element it gives us the tendency of an element to undergo oxidation. SRP gives us the tendency of an element to undergo reduction. Now, guys, remember, more the SOP of an element, more is the tendency of an element to undergo oxidation. And that element which undergoes oxidation, that's called as the reducing agent. So I would say better is the reducing agent. The one that undergoes oxidation easily, that is the better reducing agent. And the one that is the better reducing agent, I can say its reducing power is more. So different sorts of questions can be asked. Just remember this particular statement. More the SOP, more the tendency of an element to undergo oxidation, better the reducing agent, more will be its reducing power. Similarly, one more statement, guys. more the SRP of an element, more is the tendency of an element to undergo reduction. More the SRP of an element, more is the tendency of an element to undergo reduction. The one that undergoes reduction is the oxidizing agent. So better is the oxidizing agent, more will be its oxidizing power. So remember these two statements. You can solve almost all the types of the questions on SOP, SRP from this particular statement only. I hope this is clear to everyone. Is that? Is it clear? Okay, for example, see. For example, guys, let's say I'm given with 4 elements. Element A, element B, element C, and element D. These are the 4 elements which we have. These are the 4 elements which we have. Okay. Let's say I'm writing E naught of M gives Mn positive. Here I'm writing this is 2 volt, 3 volt, 4 volt, and 5 volt. Tell me first of all, what is this? Is it SOP or SRP? I'm asking you. M gives Mn positive. M gives Mn positive. Is it SOP or SRP? What do you think? Is it SOP or SRP? M gives Mn positive. 0 to plus N, increase, oxidation. It's SOP. So which has got the maximum SOP? This is the maximum value of SOP. More the SOP, more the SOP of an element, more is the tendency of an element to undergo oxidation, and better the reducing agent. So this is the better reducing agent, or I can say its reducing power is more. So I believe you can easily give the order of reducing powers here, right? Similarly, guys, let's say I'm writing E naught of M gives Mn positive. Here I'm writing minus 2 volt, minus 3 volt, minus 4 volt, minus 5 volt. This is again your SOP only. But which one has got more SOP now? Which one has got more SOP now? This is having more SOP now. This is more SOP. And more the SOP, more the SOP, more the tendency to undergo oxidation, better the reducing agent. So this is the better reducing agent. If it is the better reducing agent, its reducing power would be more. Okay, its reducing power would be more. I hope this is also clear to everyone. All right, for example, I'm giving you a scenario like this. E naught of Mn positive gives M. Let's say again this 2 volt, this is 3 volt, 4 volt, 5 volt. Now, is it SOP or SRP? What do you see? Is it SOP or SRP? What do you see here? Is it? Yes, it's SRP. Now, which one has got more SRP? You tell me that only. Which one has got more SRP? Which one has got more SRP? Simple, guys. Tell me. This has got more SRP. More the SRP. More the SRP of an element. More is the tendency of an element to undergo reduction. Right? Better oxidizing agent. So more oxidizing power. Clear? More oxidizing power. And at the end, if I write like this, E naught of Mn positive, this is M. This is minus 2, minus 3, minus 4, minus 5. Tell me. This is again SRP only. Which one has got more SRP? This is more SRP. More SRP means more tendency to undergo reduction. Better oxidizing agent. Better oxidizing agent. More oxidizing power. So you can give the order of oxidizing agents, oxidizing powers, etc. Every single thing can be done. Okay? Every single thing can be done with the help of the two statements that I gave you. I think, yeah. Sorry. Okay, look at this particular question. What do you think? Strongest reducing agent. Which one is the strongest reducing agent? Can you check it out? Can you check it out quickly? Which one is the strongest reducing agent? Strongest reducing agent. Reducing agent is the one which undergoes oxidation. You should be able to solve this question. There should be no second thought. See what do you do here? Understand properly. First of all, in the first reaction, if you see properly, in the first reaction, magnesium dipositive is gaining electrons. So it's undergoing reduction. It's undergoing reduction. Okay. That means, what about this particular value? Is it SOP or SRP? This is SRP, right? Even this is SRP. This is SRP. This is SRP. So these are the SRP of these particular ions basically which we have, which are undergoing reduction. Okay. What do we have to check? Strongest reducing agent. Reducing agent itself undergoes. Reducing agent itself undergoes oxidation. The one that undergoes oxidation easily, that's going to be the better reducing agent. And which one can undergo oxidation? The one that has got more SOP. The one that has got more SOP will undergo oxidation easily, will be the better reducing agent. That's the concept. Now, so first of all, I have to check, I have to solve the question in terms of SOPs over here. But I am given with SRPs. I am given with SRPs. So I need to convert them into SOPs first. So SOP of magnesium. SOP of magnesium will be 2.37 volt. Right? SOP of zinc would be 0.76 volt. SOP of nickel would be 0.73 volt. SOP of iron would be 0.04 volt, right? Now, which one has got maximum SOP? Maximum SOP is for magnesium. The one that has got more SOP will undergo oxidation easily, better reducing agent. So it's the magnesium which is going to be a better reducing agent, because magnesium will undergo oxidation easily. Magnesium will undergo oxidation. Magnesium will lose electrons. Don't mention the answer as Mg dipositive. Mg dipositive, it has already lost electrons. It cannot further lose electrons. It has already, Mg dipositive has already lost 2 electrons. It cannot lose further electrons. It cannot undergo oxidation. It cannot undergo oxidation. It cannot be the reducing agent. Okay? You're Mg dipositive. I hope this is also clear. Perfect. Now guys, there is one more thing. There is one more thing. That is, how do we calculate EMF of the cell? How do we calculate EMF of the cell? So first of all, what is EMF? EMF is nothing but, it is the maximum potential difference between the electrodes. When no current is drawn from the cell. When no current is drawn from the cell. So basically, you have seen your galvanic cell. In galvanic cell, we have got 2 electrodes, right? The maximum potential difference between those electrodes when the cell is not in use, when no current is drawn from the cell. What do we call that as? We call that as EMF. My dear students, when EMF is measured under standard conditions, EMF is represented by E cell. E cell when measured under standard conditions. E cell when measured under standard conditions becomes E naught cell. What is E naught cell? E naught cell is what you call a standard EMF of the cell. It's what you call a standard EMF of the cell. And how do you calculate standard EMF of the cell? It is calculated as E naught of cathode minus E naught of anode. E naught of cathode minus E naught of anode. Remember, this E naught of cathode is nothing but this is the SRP of cathode and this is the SRP of anode. This is SRP of cathode, this is SRP of anode. Okay? And this EMF is measured with the help of potentiometer. Do you remember that? EMF of the cell is measured with the help of potentiometer. How exactly? You have got nothing to do with that. Just remember all these points only. It's super sufficient for you. See guys, understand. Let's say I'm writing E naught of A gives A positive is equal to 3.1 volt. Let's say I'm writing E naught of B gives B negative minus 5.1 volt. Can you first of all tell me, what is this particular term? Is it SOP or SRP? A gives A positive. A gives A positive. 0 to plus 1, increase. Increase means oxidation. Oxidation, right? So this is your SOP. What about this? 0 to minus 1, decrease. Decrease means reduction, so SRP. So one is given in SOP, one is given in SRP. So convert both in SRPs. So what do you think will be the SRP of this? SRP would be minus 3.1 volt, right? Now compare the SRP values. Compare the SRP values. See guys, before comparing the SRP values, if I ask you how many electrodes do I have? I have 2 electrodes. I have 2 electrodes, right? Now people, I am connecting these electrodes externally as well as internally. I've got 2 electrodes, connecting these electrodes externally and internally. I've got 2 electrodes, connecting these electrodes externally and internally. Now, first of all, among these electrodes, I need to check which one is your anode and which one is your cathode. How do you check it? For that, I have got SRP of both electrodes. Whose SRP is more, this or this? Whose SRP is more? This has got more SRP. More the SRP, more the tendency to undergo reduction, and reduction happens at cathode. So this is going to behave like your cathode and this is going to behave like your anode. So the cell, a galvanic cell which you have made, in the galvanic cell, this is your anode, this is your cathode and this is your anode. Now, can you calculate standard EMF of that galvanic cell which you have made out of these 2 electrodes? You can do it. It's going to be E naught of cathode minus what? Minus E naught of anode. So SRP of cathode. SRP of cathode. SRP of cathode is minus 3.1 volt minus SRP of anode is how much? Minus 5.1 volt. So the value comes out to be 2 volt. So this is your E naught cell. This is your standard EMF of the cell which you have created over here. I hope this is also clear. Okay. That's going to be sufficient. You can do that. You can do that. Let me give you one more example. See guys, for example, I have got 2 electrodes. These are 2 electrodes which I have. Okay, imagine that these are the 2 electrodes which I have. Now I am, for example, connecting these electrodes externally, internally. Externally as well as internally, I'm connecting them. Now when I'm connecting these electrodes externally and internally, I'm getting a complete cell. Now the complete cell which I got, I need to calculate the standard EMF of that complete cell. I need to calculate standard EMF of that complete cell. Now how do I do it? See guys, how do I do it? Plus 3 to 0. Plus 3 to 0. Decrease means reduction. So this SRP given. Plus 1 to 0. Decrease, reduction. So this again SRP given. So which one has got more SRP? This has got more SRP. More SRP means the one that has got more SRP will undergo reduction. Reduction takes place at cathode. So this is your cathode. This is your anode. So you have identified in the cell which you have created which one is your anode and which one is your cathode. You have identified that. Now, E naught cell is equal to E naught cathode minus E naught anode. E naught cathode means SRP of cathode. SRP of cathode is 5.1 volt minus SRP of anode is 3.1 volt. The value comes out to be exactly 2 volt. So this is going to be the standard EMF for the cell. So you saw exactly how standard EMF, how EMF for the cell is calculated under standard conditions. I hope this is clear to everyone. Okay, I hope this is clear to everyone. Right? Now, my dear students, you would have heard about a topic that's called as standard hydrogen electrode, SHE. What is this SHE all about? As I told you, it's a reference electrode with the help of which we calculate SOPs and SRPs of different elements, right? The point is how this standard hydrogen electrode exactly is made. Understand what I'll be saying. Guys, imagine that you have got a container like this, okay? And in this particular container, for example, you have kept H positive ions. Let's say the concentration of H positive here, you have kept 1 molar, for example. And in this container, you have kept one more inverted tube like this. You have kept an inverted tube like this. And in this inverted tube, I have kept a platinum wire. I have kept a platinum wire. This is platinum wire coated with platinum black. Now guys, from this opening, I'm going to introduce H2 gas. I'm going to introduce H2 gas at the pressure of 1 bar. Okay? Concentration of H positive here is 1 molar. And temperature I'm keeping constant. Let's say I'm keeping temperature 25 degrees centigrade. First of all, do you see the conditions? I've kept the conditions as the standard conditions. Concentration is 1 molar, temperature constant, pressure as 1 bar. The conditions are standard. The conditions are standard. Now guys, if you see carefully, you are introducing H2 gas here. The H2 gas which you are introducing, that will be adsorbed on the surface of platinum. That would be adsorbed on the surface of platinum. That would be adsorbed on the surface of platinum. So this wire used to look like platinum in the beginning. Now when H2 gas is introduced, all that H2 gas is on the surface of the platinum now. Now this wire does not look like a platinum wire to me. It looks like a hydrogen wire to me from outside, because all the surface is covered with hydrogen molecules. So it looks like hydrogen wire to me. Can I say I have got the hydrogen wire? I have introduced the hydrogen wire into a solution containing its own ions? Yes. I have taken the hydrogen wire, introduced the hydrogen wire into a solution containing its own ions. I'll be calling this setup as the electrode. Which electrode this is? This is your hydrogen electrode. And I have kept hydrogen electrode under standard condition. I have kept hydrogen electrode under standard conditions. So I'll be calling this particular setup over here as the standard hydrogen electrode. Now this hydrogen electrode which we have, again, it can behave like anode. It can work like cathode as well. And it's pretty much simple. When it works like anode, at anode what happens? Oxidation takes place. At anode what happens? Oxidation takes place. Now people, this rod has got hydrogen molecules on it. Those hydrogen molecules will undergo oxidation. And those hydrogen molecules will undergo oxidation and they will get converted into 2 times H positives. With that, you'll be getting 2 electrons as well. This reaction will be taking place when hydrogen electrode will be behaving like anode. Similarly, when the hydrogen electrode behaves like cathode, at cathode what happens? Reduction. Reduction means gain of electrons. In the solution, you already have H positives. Those H positives will collide with the rod, will take electrons from the rod and will get converted into H2. So basically, a reverse of this reaction. The H positives which were there in the solution, they collided with the rod. They took 2 electrons from the rod and got converted into H2 gas. This is the reaction which will happen when hydrogen electrode behaves like the cathode. This is the reaction which will happen when the hydrogen electrode behaves like the cathode. My dear students, irrespective of the fact whether hydrogen behaves as anode or hydrogen behaves as cathode, irrespective of that, remember that SOP as well as SRP of hydrogen electrode, SOP as well as SRP of hydrogen electrode is taken as 0 for reference. Standard oxidation potential of hydrogen electrode as well as standard reduction potential of hydrogen electrode is taken as 0 as per reference. Remember this particular point. Okay? I hope I'm clear with this. I hope I'm clear with this and you got it properly. What do you think is going to be the answer of this question? What do you think is going to be the answer of this question? Standard oxidation potential for the half cells is given. SOP values are given. What do you need to calculate? EMF of the cell. EMF of the cell needs to be calculated. See guys, if you look at the cell, oxidation state of zinc here is 0. Oxidation state of iron is +2. Here zinc is +2. Iron is 0. So 0 to +2 increase oxidation. Oxidation takes place at anode. Similarly, this is your cathode. One is your anode, one is your cathode. Now, zinc is your anode, iron is your cathode. You got it, right? What we need to calculate? We need to calculate E naught cell. What is E naught cell? E naught cell is nothing but E naught cathode minus E naught anode. What is E naught cathode? E naught cathode means SRP of cathode. SRP of iron. This is SOP of iron. What do I need? I need SRP of iron. So reverse the sign. Minus 0.41. Minus SRP of anode. SRP of anode means SRP of zinc. This is SOP of zinc. What do I need? I need SRP of zinc. So minus 0.7. The value comes out to be 0.354. Right? So this is going to be the E naught cell. Perfect. Perfect. I hope this is also clear to everyone. Yeah. I hope this is also clear to everyone. Perfect. Guys, now comes one more important topic. What is that? That is the relation between delta G and E cell. Since you know I'm not deriving any result today, right? I'm just giving you the results and showing the application part properly. See guys, understand what I'll say. Relation between delta G and E cell. First of all, if I ask you how a galvanic cell is made, your answer will be just take 2 electrodes, externally, internally connect them, you'll be getting an electrode, right? That will be your answer. No doubt you can make a galvanic cell. You can make a cell by just taking 2 electrodes, connecting them externally, internally. But The point is whether that cell will be working or not. Whether that cell will work or not. That cell will only work if cell reactions, that means reaction at anode, reaction at cathode, if cell reactions will happen on its own. I hope you are getting what I'm trying to say. No doubt you can make a lot of cells. You just have to take 2 electrodes, connect them externally, internally. But will that cell work or not? That depends on, after connecting the electrodes, whether cell reactions are happening on its own or not. If cell reactions are happening on its own, cell will work. Cell will produce current. If cell reactions are not happening on its own, cell will not work. I hope I'm clear with this. Okay. Perfect. See guys, what I was telling you, I'm going to write everything in the form of 2 statements and we are done. I'll say for the cell to be working, for the cell to be working, its cell reactions must be spontaneous. For the cell to be working, its cell reactions must be spontaneous, right? And for the cell reactions to be spontaneous, for any process to be spontaneous, delta G for the cell should be negative, right? For any spontaneous process, delta G has to be negative. You must be knowing about that. For any cell, for any process to be spontaneous, its delta G must be negative. Similarly, for cell reactions in a cell to be spontaneous, right? So delta G for the cell should be negative. What is this delta G for the cell all about? Delta G for the cell is nothing but it is minus NFE cell. This is the result. Delta G is equal to minus NFE cell. Okay. So delta G for the cell must be negative. What does it mean? It means that minus NFE cell, this should be negative. When can this whole term be negative? This whole term can only be negative if E cell is positive. If E cell is positive. Okay. So for the cell reactions to be spontaneous, I would say delta G for the cell should be negative and E cell has to be positive. Okay, E cell has to be positive. So for any cell to be working, delta G for the cell has to be negative and E cell has to be positive. This is the condition. Okay. Now similarly, if I say, if for example, delta G for the cell is positive, or if delta G is positive, delta G can only be positive if this term is positive. When can this term be positive? This term can be positive if E cell is negative. If delta G for the cell is positive or E cell is negative, I must say cell will not work. Or I can say cell reactions will be non-spontaneous. Right? Cell reactions will be non-spontaneous. Now one last case here. If delta G for the cell is equal to 0, or I can say E cell is equal to 0. This condition in a cell is called as equilibrium condition, which will be discussed in some time. Equilibrium condition. Okay. Remember one thing. A question is asked from here. The question is asked from here. Remember, when you talk about the delta G, Gibbs free energy, it's an extensive property. It is an extensive property. Your E cell is the example of intensive property. And if you have studied thermodynamics sometimes before, you must have studied that extensive properties can be added, intensive properties cannot be added directly, right? Extensive properties can be added or subtracted directly. Intensive properties cannot be added or subtracted directly. Okay, intensive properties cannot. Perfect. Remember this particular point as well. One more thing. I told you your delta G is nothing but it is minus NF E cell. And when delta G is calculated under standard conditions, should you be calling this as delta G or delta G naught? This would be called as delta G naught is equal to minus NF E naught cell. What is the difference between the two? This one is written under standard condition. Under standard condition. Okay? One is written under standard conditions, one is written under non-standard conditions. That is the difference. That is the difference. Now, guys, few things. Let's say I'm writing Fe tri-positive plus 3 electrons gives Fe solid. Fe di-positive plus 2 electrons gives Fe solid. Fe tri-positive plus 1 electron gives Fe di-positive. For example, I'm giving you some random values. Let's say E1 for this reaction is equal to X volt. E2 for this reaction is equal to Y volt. I want E3 for this particular reaction. Can you give it a try? Tell me. See, guys, how these sort of questions are to be solved. See, first of all, this is the reaction for which E cell is to be calculated. This is the reaction for which E is to be calculated, right? This is the reaction for which E is to be calculated. This is the reaction for which E is given. This is the reaction for which E is given. This is the reaction for which E is to be calculated. Remember, that reaction for which E is to be calculated, that reaction for which E is to be calculated, we are supposed to make that reaction. We are supposed to make that reaction out of the given reaction. Now, how can I make this third reaction? How can I make this third reaction from first and second? If I subtract second from first, what do I get? Subtracting second from first, I think I'll get third. How exactly? 1 minus 2. 1 is your Fe tri-positive plus 3 electrons. Minus 2 is your Fe di-positive minus 2 electrons. Right? Gives. This cancelled, so nothing is here. So I would say 3 electrons minus 2 electrons gives 1 electron. So Fe tri-positive plus 1 electron minus Fe di-positive goes on the other side. So it's Fe di-positive. Was this the reaction which I was supposed to make? Yes, this was the reaction I was supposed to make. Right? So can I say third reaction I made when I subtracted second from first? Perfect. if you think the same operation you are going to do with their E values, if you think the same operation you are going to do with your E values, then the answer is going to be wrong. That's not the case. That's not how you do it. Why? Because your EMF is intensive property. E is intensive, right? Intensive properties cannot be added or subtracted directly. You have to solve this question in terms of delta G, in terms of extensive property. So what you need to do, instead of third, instead you write delta G3. Here you write delta G1. Here you write delta G2. Delta G3 is equal to delta G1 minus delta G2. Now what is delta G3? Delta G3 is going to be simply minus N3FE3 is equal. Delta G1 is nothing but minus N1FE1. Delta G2 is equal to minus N2FE2. So first of all, F everywhere cancels out. I would say at the end, E3 will be equal to N1E1 minus N2E2 divided by N3. What is N1? N1 means this value. This is N1. This is your N2. This is your N3. So N1, N2, N3. All these things are given. E1, E2 are given. Put the values. Get the value of E3. That's something I was supposed to calculate. Am I clear with this? Am I clear with this, guys? Perfect. All right, amazing. Chalo, I'm moving on. I am moving on. Now, guys, I'm introducing a term. That's what you call as Nernst equation. Nernst equation, one of the important topics here. If you look at your Nernst equation, let me write its actual format first. I'll directly write its format. I'm not deriving it. So I'm writing E cell is equal to E naught cell minus 2.303 RT divided by NF log of QC. This is your Nernst equation. This is your Nernst equation. Where it's used, you'll get the idea in some time. But if you want to simplify it a bit, so what you need to do is take the value of R as 8.314 joules per Kelvin per mole, number one. Take the Faraday's constant as 96500 coulombs, right? Take the temperature as 298 Kelvin. When you put all these things into this particular expression, what do you get? You get the modified form of Nernst equation. What is that? That is your E cell is equal to E naught cell minus 0.0591 divided by N, and it's log of QC. It's log of QC. This is your modified Nernst equation, which you will be using in the questions. Now the point is, where do we use the Nernst equation? Where do we use the Nernst equation? The first use of Nernst equation is to calculate oxidation potential or a reduction potential of an electrode. Oxidation potential or reduction potential of an electrode under non-standard condition. Under non-standard condition. To calculate oxidation potential or reduction potential of an electrode under non-standard conditions. How exactly? For example, if oxidation potential of an electrode is to be calculated, then Nernst equation is written like this. EOX is equal to E naught OX minus 0.0591 divided by N log of QC. This is when oxidation potential of the half cell, oxidation potential of the electrode is to be calculated. But if reduction potential of the electrode is to be calculated, how do we write the Nernst equation that time? Nernst equation at that time is written like this. ERED is equal to E naught RED minus 0.0591 divided by N, and it's log of QC. Okay, it's log of QC. This expression I'll be using when oxidation potential of the half cell is to be calculated. This expression I'll be using when reduction potential of the half cell, reduction potential of the electrode is to be calculated. But when EMF of the cell is to be calculated under non-standard conditions, at that time also we use the Nernst equation, and we use the Nernst equation in this form. E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Okay? Is it clear till here? So how many uses are there? How many Nernst equation uses do we have? You tell me. How many uses do you see for the Nernst equation? 3. One is to calculate oxidation potential of the electrode, one is reduction potential of the electrode, and one is EMF of the complete cell. One is EMF of the complete cell. Okay? Now, let's try to see what kind of questions can be asked from the Nernst equation. Let's see what kind of questions can be asked from the Nernst equation. Just a second, guys. Or we can do one more thing here. We can check one more thing. Let's first of all see how Nernst equation is written for the half cells. Then we'll see the questions. Okay. So I'm writing the heading here as Nernst equation for half cell. How do we write Nernst equation for half cells? See guys, half cell means electrode. Half cell means electrode. We'll have the break at 5:30, okay? At 5:30 we'll have the break. Nernst equation for half cells. Half cell means first of all electrode. First of all, imagine that this is your container. And in this particular container, for example, I am keeping, let's say I'm keeping some salt, some electrolyte. Okay, let's say which electrolyte? Any random electrolyte I'm keeping, due to which in the container there are Mn positive ions. For example, let's say I've kept some electrolyte in the container, due to which in the container which ions do we have? We have got Mn positive ions. Now in this particular container I'm dipping a rod. I've introduced a rod into a solution containing its own ions. So this electrode I'm calling as, this setup I'm calling as electrode, right? I've taken the metal rod M, dipped it into a solution containing its own ions. So this entire setup I'm calling as the electrode over here. So I've got an electrode, number one. Number two, imagine if this electrode behaves like the anode. If this electrode behaves like the anode, what's going to happen? At anode, oxidation takes place. Oxidation means loss of electrons. This rod is made up of metal atoms. Those metal atoms will undergo oxidation. They lose electrons. And when metal atoms of which a rod is made up of, when they lose electrons, it gets converted into Mn positives. And here you get N electrons. Okay? Here you get N electrons. Perfect. Similarly, what happens at cathode? At cathode, I must say, a reduction takes place. Oh, leave cathode aside just a second. Leave cathode aside. Okay, see, this particular electrode, I'm assuming that it's behaving like anode. When this electrode is behaving like anode, oxidation took place. Let's assume that I want to calculate oxidation potential of this electrode. Let's say I want to calculate oxidation potential of this electrode under non-standard conditions. Under non-standard conditions, what do? I'll be using the Nernst equation. Before using the Nernst equation, can you tell me in this particular reaction how many moles of electrons are exchanged? N moles of electrons are exchanged. If I ask you what is the value of QC, QC is going to be concentration of Mn positive raised power 1. That's it. Divided by it's solid. Nothing to do with that. Right? Now, how do I write Nernst equation? Nernst equation is written like this. Since I want to calculate oxidation potential of the half cell, EOX is equal to E naught OX, standard oxidation potential of the half cell, minus 0.0591 divided by N, and it's going to be log of QC. QC here is nothing but concentration of Mn positive. This is how you are going to write the Nernst equation. This is how you are going to write the Nernst equation. Now, try to understand what I say. My dear students, since I took the electrode, I wanted to calculate the oxidation potential of the electrode. I wanted to calculate oxidation potential of the electrode. That's why I made this electrode to work like an anode, because at anode only oxidation takes place. Because at anode only oxidation takes place. The point is different here. The point is, if I increase the concentration of electrolyte in the container, if concentration of electrolyte in the container increases, if concentration of electrolyte in the container increases, that means concentration of Mn positives in the container increases. If concentration of electrolyte in the container increases, what does that mean? That means Mn positive concentration in the container will increase. And when Mn positive concentration in the container increases, when this term increases, I would say this whole term increases. If this whole term increases, I would say difference between these two decreases. That means oxidation potential of the electrode decreases. So in simple words, I can say if the concentration of electrolyte in the container keeps on increasing, oxidation potential of the electrode keeps on decreasing. So your oxidation potential of the half cell is inversely proportional to concentration of electrolyte present in the container. Okay, it's inversely proportional to concentration of electrolyte present in the container. Perfect, right? Similarly, if the same electrode behaves like a cathode, it could have behaved like the cathode as well. If the same electrode behaves like the cathode, what happens then? At cathode, reduction takes place, right? So reaction is going to be reverse of this. A reverse of this means Mn positive aqueous would be gaining N electrons, getting converted into M solid, right? This is your reaction at cathode. So, how many moles of electrons exchanged? N. If I ask you QC, QC is going to be solid, its active mass is 1 divided by concentration of Mn positive raised by stoichiometric coefficient 1. Now, I made the electrode to behave like the cathode. At cathode, reduction takes place, and I wanted to calculate the reduction potential of the half cell. The reduction potential of the half cell, which is equal to E naught Red minus 0.0591 divided by N log of QC. QC is 1 upon concentration of Mn positive. Okay, this is how you calculate reduction potential of the half cell. And I can summarize it like this. I can say reduction potential is directly proportional to concentration of electrolyte present in the container. More the concentration of electrolyte in the container, more is going to be the reduction potential of the half cell. More is going to be the reduction potential of the electrode. Let me know once in the chats if I'm clear. Okay. Break, I told you break will take at 5:30. Let's do some questions first. Let's do some questions so that you'll get the idea of how What kind of questions are asked from Nernst? See, one of the basic questions which we have, calculate the oxidation potential of the following half cell. We are given the half cell. This is the half cell which is given to us. We are supposed to calculate its oxidation potential. In order to calculate its oxidation potential, I'll make sure that this half cell behaves like the anode. If the half cell behaves like the anode, at anode oxidation takes place. 0 to +2. Increase means oxidation. So reaction is going to be Fe solid gives Fe di positive aqueous plus how many electrons? Plus 2 electrons. This would be the reaction at anode. This would be the reaction at anode. And similarly, if I ask you how many moles of electrons are exchanged, you'll directly say 2 moles of electrons are exchanged. What would be the QC value? QC is going to be concentration of Fe di positive raised by stoichiometric coefficient. This is solid, its active mass is 1, right? And concentration of Fe di positive, as you can see, 0.1, which means 10 raised power minus 1. This is QC. You got N, you got QC. Now, what do I need to calculate? I need to calculate the oxidation potential. So I can use the Nernst equation as EOX is equal to E naught OX minus 0.0591 divided by N, and it's log of what? Log of QC. So I would say E naught OX, standard oxidation potential of the half cell. Is it standard oxidation potential or standard reduction potential? Plus 2 to 0, decrease. Decrease means reduction. So this is SRP. But what do I need? I need SOP. I need SOP. So just reverse the sign. It's plus 0.44 minus 0.0591 divided by N value here is 2 log of QC value. QC we have calculated as 10 raised power minus 1. Now it's just the matter of calculation. Solve it and you'll be getting the oxidation potential of the half cell which we were supposed to calculate. Right? I hope I'm clear with this. I hope I'm clear with this. I hope I'm clear with this. Perfect. Let's see one more type of the question of the similar format so that you'll get used to it. Something wrong with me? I'm drinking water, but cough is not stopping at all. Anyways, have a look. Calculate the oxidation potential of the following half cell. Again, I'm given with the half cell. I need to calculate its oxidation potential. Look at this half cell first of all. It's an hydrogen electrode. It's a hydrogen electrode. I need to calculate oxidation potential of this hydrogen electrode. How do you do it? In order to calculate oxidation potential, what you need to do? You need to make sure that electrode behaves like anode. At anode, oxidation takes place. And you know, when hydrogen electrode behaves like anode, what reaction takes place? H2 gas gives 2 times H positive aqueous. And with this, you write 2 electrons. This is the reaction taking place at anode. So in this particular reaction, how many moles of electrons are exchanged? 2. N value here is 2. If I ask you QC, QC is going to be concentration of H positive raised power 2 divided by partial pressure of H2 gas. Right? What is the concentration of H positive? That is 0.1 molar. So 10 raised power minus 1 because square is 10 raised power minus 2. Partial pressure of H2 gas is 10. This 10 comes up, so it's 10 raised power minus 3. So this is QC. You got N also, you got QC also. What do you need to calculate? You need to calculate oxidation potential. Oxidation potential of the half cell is nothing but standard oxidation potential of the half cell minus 0.0591 divided by N, and it's going to be log of QC. Now, standard oxidation potential of the half cell. See, half cell is your hydrogen electrode, and SOP as well as SRP of hydrogen electrode is 0. So this term is 0 minus 0.0591 divided by N value is 2 log of QC. QC is 10 raised power minus 3. You just need to solve this and you'll be getting the answer. Okay? Perfect. I hope this is clear. Now, let's see one more question so that it becomes clear to you. For example, this is the question. Calculate the EMF of the cell. So till now, I was showing you how to calculate oxidation potential or how to calculate reduction potential of the half cell, right, with the help of Nernst equation. Now let's see how to calculate EMF of a complete cell. How to calculate EMF of a complete cell. Let's try to understand. First of all, this is the complete cell which is given to me. In between these two lines, they represent your salt bridge. On the left side anode, on the right side cathode, right? Now first of all, at anode, what happens? Oxidation. Sn solid gives Sn dye positive aqueous, and you'll be writing 2 electrons. This is the reaction at anode. What is the reaction at cathode? At cathode, reduction takes place. Pb dye positive gives Pb solid. Pb dye positive aqueous would be gaining 2 electrons, getting converted into Pb solid. You got the reaction at anode, you got the reaction at cathode, right? This is something which we have learnt earlier only. Now guys, if you got the reaction at anode and cathode, are the electrons balanced in both the reactions? I would say yes, electrons are balanced. And if the electrons are balanced, you can directly add these two reactions. When you add these two reactions, Sn solid plus Pb dye positive aqueous, what does it give us? Sn dye positive aqueous, and with this, you'll be writing Pb solid. This is your net reaction. In this net reaction, if I ask you what is the value of N value is 2. N value is 2. 2 moles of electrons are being exchanged, right? If I ask you what is the QC value, QC is going to be concentration of Sn dye positive raised by stoichiometric coefficient. This is solid, its active mass is unity. Its active mass is also unity, divided by concentration of Pb dye positive raised by stoichiometric coefficient. What about the concentration of Sn dye positive? That's 1 molar, divided by. What about the concentration of Pb dye positive? That's 10 raised per minus 3 molar. The value overall comes out to be 10 raised per 3. So in order to use the Nernst equation, I got the N value, I got the QC value. After getting N and QC, what else do I need? I need E0 cell as well, which I'm not given with. But I know E0 cell is equal to E0 of cathode minus E0 of anode. E0 of cathode means SRP of cathode. Cathode is your lead. What is SRP of lead? SRP of lead is given to me as minus 0.13. Minus SRP of anode. SRP of anode is given to me as minus 0.14. The value comes out to be 0.01 volt. This is your E0 cell, right? This is your E0 cell. You got your E0 cell, you got QC, you got N. Now I'll be directly using Nernst equation as E cell is equal to E0 cell minus 0.0591 divided by N, and it's going to be log of QC. What is E0 cell? E0 cell I have calculated as 0.01 minus 0.0591. What is N value? That's 2 log of QC. QC is 10 raised per 3. Just solve this particular equation and you'll be getting the value of EMF of the cell. I hope I'm clear with this. Okay. Okay. I think let's take a break and you guys have some tea or something. I'll also have something. And then we'll move on. Okay. So we have got break till. What is the time? Break till 6, huh? But at 6 p.m. I would want everyone to be back. At 6 p.m. I would want everyone to be back. Okay? Yeah, I'll have some hot water or something. So I'll see you exactly at 6. But be back, okay? Be back. We have got a lot of things to cover up. Is everyone back? Yes. Welcome back, guys. So whatever things we discussed till now, is everything clear? Yes, my cough is not stopping. I don't know what's wrong. I don't know what's wrong. All right, should we start then? Should we start? Should we start? All right. So guys, you mark the heading as just mark the heading as Nernst equation at equilibrium. Nernst equation at equilibrium. Just mark this heading first. This is also important. See guys, I hope you remember your Daniel cell, right? In your Daniel cell, if you remember, we had taken 2 electrodes. One was your zinc electrode and one was your copper electrode. Externally, they were connected. At the same time, they were connected internally. They were connected internally. This was your zinc electrode on this side. And this was your copper electrode. If you remember, your zinc electrode, it was behaving like the anode. And copper electrode was behaving like the cathode. Now, my dear students, it's pretty much simple. For any electrode to behave like the cathode, for any electrode to behave like cathode, for any electrode to work like cathode, its reduction potential has to be more. Its reduction potential has to be more. So I would say reduction potential of copper is more and reduction potential of zinc is comparatively less. That's why reduction is taking place here, right? See, it's pretty much simple. Since your zinc electrode is behaving like the anode, copper electrode is behaving like the cathode. For any electrode to behave like cathode, its reduction potential should be more. So I would say reduction potential of copper is more than that of reduction potential of zinc. That's why reduction is happening here, due to which this electrode is behaving like the cathode, right? Now people, let me give some random values just to make you understand. Let me give some random values here so that you'll understand it properly. For example, imagine that the reduction potential of cathode was, copper was 5 volt. Reduction potential of anode, that is zinc, for example, that was 1 volt. Reduction potential of cathode was 5 volt and reduction potential of your zinc was, for example, 1 volt. That is the reason why this particular electrode behaved like the cathode, because its reduction potential is more. Now people, understand properly what I will be saying. Understand properly. See, at anode what happens? At anode oxidation takes place. We have seen that. At anode oxidation takes place, due to which the zinc atoms of which a rod is made up of, those zinc atoms will undergo oxidation. They will get converted into zinc dipositives, and those zinc dipositives will enter into this particular solution. Due to which, can I say, concentration of electrolyte in this particular chamber, in this particular part of the container, is increasing. Of course, I can say concentration of electrolyte in the left container. Concentration of electrolyte in the left container, it increases with time, right? Similarly, people, if you remember, on this particular electrode, reduction takes place. On this particular electrode, reduction takes place, right? So basically, copper dipositives which were there in this solution, those copper dipositives were colliding with the rod, gaining electrons from the rod and getting converted into copper solid. And that copper solid was deposited on this particular rod. Due to which, the concentration of Cu dipositives in the solution, that would be decreasing with time. Or I can say, in general, the concentration of electrolyte in the right container, it decreases with time. Right? It decreases with time. So when the cell starts working, concentration of electrolyte in the left container, it starts increasing. Concentration of electrolyte in the right container, it starts decreasing. Right? Earlier, reduction potential of copper was 5 volt. Reduction potential of zinc was 1 volt. So there was potential difference due to which current was flowing. Now if you can see, with time the concentration of this electrolyte is increasing. And we know already, we have discussed one thing. The reduction potential of the electrode is directly proportional to the concentration of electrolyte in the container. Since the reduction potential of zinc was initially 1 volt, copper was 5 volt. Now, the concentration of electrolyte here is increasing with time. If the concentration of electrolyte is increasing with time, that means the reduction potential of zinc electrode, it will be increasing with time. With time, reduction potential of zinc electrode will be increasing. The concentration of electrolyte in this container is decreasing with time. Therefore, I would say reduction potential of the copper electrode here would be decreasing with time. So on one side, reduction potential of zinc is increasing. On another side, reduction potential of copper is decreasing. Can I say there will be a time when the reduction potential of both the electrodes would have got equal? Can I say there would be a time when reduction potential of both the electrodes would be equal? At that point of time, when the reduction potential of both the electrodes would be equal, will there be any potential difference between the electrodes at that time? There will be no potential difference. If there is no potential difference, will the cell produce any current at that point of time? The cell is not going to produce any current at that point of time. And that stage in a cell is something which you call as the equilibrium stage. I hope you got exactly what is the meaning of the term equilibrium stage. If yes, let me know once in the chats. So I would say at equilibrium, when cell attains equilibrium, I would say E cell, the potential difference between the electrodes becomes 0. So your Nernst equation, the general form of your Nernst equation was E cell is equal to E naught cell minus 2.303 RT divided by NF, and it used to be log of QC, right? But at equilibrium your E cell becomes 0. If E cell becomes 0, I would be getting the final result as E naught cell is equal to 2.303 RT divided by NF. Now log of, instead of QC, I can directly write as KC, equilibrium constant. I can directly write it as equilibrium constant. or if you further want to simplify it, if you want to put the value of Faraday's constant, if you want to put the value of R, 8.314, temperature 298 Kelvin, the reduced form finally would be like this. E naught cell is equal to 0.0591 divided by N, and it's going to be log of equilibrium constant. So this particular equation is used only when equilibrium is established in the cell, right? Is this clear, guys? Let me know once. Is this point clear? Is this particular point clear? Yes. Now sometimes they'll give you some different types of questions wherein E naught cell would be given, N would be given, and you'll be supposed to calculate equilibrium constant. I believe you can easily do that. I believe you can easily do that. Okay. Similarly, guys, one more thing. One more thing. One more thing. I told you E cell is equal to 0. If E cell is equal to 0, what about delta G? Delta G is equal to minus N of E cell. If E cell is equal to 0, means delta G also comes out to be 0. Delta G also comes out to be equal to 0, right? One more thing. If I talk about delta G naught is equal to minus NF E naught cell. Minus NF E naught cell. And already few minutes back only I've told you, E naught cell can be written like this. E naught cell can be written like this, which is going to be 2.303 RT divided by NF, and it's going to be log of Kc. So guys, here you can do a bit of calculation, and when you do the calculation, this NF gets cancelled. So your delta G naught comes out to be equal to minus 2.303 RT log of Kc. This expression also, I would want every one of you to remember. From this expression also, question can be asked. Okay. Delta G naught is equal to minus 2.303 RT log of Kc. A naught cell is equal to 0.0591 divided by N log of Kc, right? These things you need to remember from now onwards. Right, people? I hope all this stuff is clear. So let's move on. Okay. Guys, the next topic that we are going to discuss here, what is that going to be? The next topic that we are going to discuss here, that's going to be concentration cells, right? Well, I'm not going to discuss the concentration cells in very much detailed form. I'll just tell you those things which can be asked in your examination. Okay? Kc is equilibrium constant. Concentration cells. First of all, what do we have in concentration cells? The first thing which you must remember from now onwards. In case of concentration cells, I must say two same electrodes are used. Two same electrodes are used. Number one. Number one. If two same electrodes are used, then E naught cell, which is equal to E naught cathode minus E naught anode. If two same electrodes are used, if electrodes are same, then E naught cell value has to be 0. E naught cell value has to be 0. Now understand first of all what it means. See guys, imagine that this is your one container carrying zinc sulfate. Okay, this is the zinc rod here. Similarly, imagine this is one more container in which you have got again zinc sulfate, and this is the rod. Okay. So this is a zinc rod, and here also I have kept zinc rod. So guys, one thing if I ask you, are the electrodes same or different? I have taken two same electrodes. Now, I'm connecting them externally as well as internally. Whenever you see this kind of the cell in which two same electrodes are used, whenever you see this kind of the cell in which two same electrodes are used, you'll be calling the cell as the concentration cell, right? You'll be calling the cell as the concentration cell. Now, how this concentration cell is going to generate EMF? How this concentration cell is going to, produce current? That is the point now. See, there are two things which you need to remember. Before talking about how this concentration cell generates EMF, how this concentration cell produces current, before talking about that, if we have got two same electrodes, out of which, for example, one is your anode and one is your cathode. If I want to calculate E naught cell is E naught cathode minus E naught anode. So SRP of cathode, for example, cathode here is your zinc minus SRP of anode. Anode is also what? Anode is also zinc. So SRP of zinc minus SRP of zinc, that comes out to be 0, right? So that's the point. In case of your concentration cells, your E naught cell value, that is equal to 0. Okay? Your E naught cell value, that is equal to 0. Now, how this concentration cell exactly works? How this concentration cell produces current? How in this concentration cell EMF is generated? Let me tell you, in case of concentration cells, I would say EMF is generated either due to concentration difference or due to partial pressure difference. Concentration difference or the partial pressure difference. In case of your concentration cells, EMF is generated either due to the difference in the concentrations or the difference in the partial pressures, which you will understand in detail in some time. Before that, let me tell you, based on this particular point, we are going to classify concentration cell into two categories. One is your electrolytic concentration cell. One is your electrode concentration cell. Electrode concentration cell. Well, in case of your electrolytic concentration cell, EMF is generated due to concentration difference. EMF is generated due to concentration difference. In case of electrolytic concentration cell, in case of electrode concentration cell, EMF is generated due to partial pressure difference. EMF is generated due to partial pressure difference. Now we have to understand this a bit more in detail. So mark the heading as electrolytic concentration cell. Electrolytic concentration cell. My dear students, in case of electrolytic concentration cells, we'll be using two same electrodes. The difference lies in the concentrations of electrolytes. For example, if I make a cell over here like this, let's say I've got M solid, it gives Mn positive aqueous. The concentration of Mn positive in the solution is, for example, C1 molar. This is your salt bridge. On the right side, we have again Mn positive aqueous, whose concentration is C2 molar. It gives your M solid. Just look at the cell and tell me whether we are using the same electrodes or different electrodes. We are using two same electrodes. Where the difference lies? Difference lies in the concentrations of the electrolytes in both the containers. Well, the concentration of electrolyte in the left container, in the anodic container, is C1. Concentration of electrolyte in the right container, in the cathodic container, that is C2. Okay. Now let's see what condition this cell has to follow so as to work like a normal galvanic cell. What all conditions it has to follow? See guys, first of all, for this cell to be working like a normal galvanic cell, what should happen at anode? At anode, oxidation should happen. So this M should get converted into what? This M solid should get converted into Mn positive aqueous with concentration C1 plus how many electrons? Plus N electrons. This is going to be the reaction which should take place at anode, number one. Number two, what should be the reaction taking place at cathode? What should be the reaction taking place at cathode? At cathode, Mn positive should get converted into M solid. So Mn positive aqueous plus N electrons should get converted into M solid. Concentration of this Mn positive here was C2 molar. If I ask you, are the electrons balanced in both the reactions? Electrons are balanced. I can directly add the reactions. When I add the reactions, what do I get? This M solid gets cancelled out. So I would be getting Mn positive aqueous with concentration C2 molar gives Mn positive aqueous with concentration C1 molar. This is our net cell reaction. If this is our net cell reaction, can we get the QC value here? Absolutely, we should be getting. So QC is going to be equal to concentration of this Mn positive, which is C1, divided by concentration of that Mn positive, which is C2. So QC is equal to C1 divided by C2. QC is equal to C1 divided by C2. If you got the QC, tell me what about the E0 cell value? E0 cell already is 0. E0 cell is already 0, right? Now use the Nernst equation. Nernst equation says that E cell is equal to E0 cell minus 0.0591 divided by N log of what? Log of QC. This is the expression. This is the expression. Now, just put the values. Just put the values. First of all, E cell is equal to E0 cell is 0 minus 0.0591 divided by N log of QC. QC is how much? QC is C1 divided by C2. If I remove this minus sign here, I can write it as, instead of C1 by C2, I'll be writing C2 by C1. I'll be writing C2 divided by C1. So this is the expression which we got. Now, my dear students, the point is, when this cell will start working? What is the condition that this cell has to follow so as to work? That is the important point. Now, we know for any cell to be working like a normal galvanic cell, its cell reactions must be spontaneous. And cell reactions will be only spontaneous if delta G for the cell will be negative or E cell will be positive. Correct? So I would say for the electrolytic concentration cell, involving which electrodes? Involving metal ion electrodes. Involving metal ion electrodes to be working like a normal galvanic cell, or let's write it as such, to be working, comma, E cell should be positive. When can be E cell positive? E cell can only be positive if this particular term is positive. When can this particular term be positive? This log term can only be positive if this term is greater than 1. If C2 divided by C1 is greater than 1, which tells you if C2 is greater than C1. If C2 is greater than C1, right? Because if C2 is greater than C1, then only this term is greater than 1. If this particular term is greater than 1, then only this term comes out to be positive. If this term comes out to be positive, the entire term will be positive. Okay? So for this electrolytic concentration cell to be working like a normal galvanic cell, its E cell should be positive. That means C2 has to be greater than C1. What does that mean? That means the concentration of electrolyte in the cathodic container should be greater than that of concentration of electrolyte in the anodic container. So let me write it over here. Concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Then only EMF of the cell will come out to be positive. And once EMF of the cell comes out to be positive, I would say then only the cell will start producing current. Is this particular point clear? Is this particular point clear? Yeah. Perfect. Perfect, guys. So this was your electrolytic concentration cell. So do remember, for the electrolytic concentration cell to be working, the concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anodic container. If the cell involves metal, metal ion electrodes. Okay. Now, let's move on. One more cell is there. What is that? That is your electrode concentration cell. Electrode concentration cell. What happens in electrode concentration cell? In electrode concentration cell, only thing that we change, what is that? We keep the concentration of electrolytes as same. We keep the concentration of electrolytes as same, but we keep the partial pressure as different. For example, let me show it to you. Let me show it to you. Let's say you have got a cell like this. Platinum solid, H2 gas with the pressure of P1 bar. Okay. This is H positive aqueous with a concentration of C molar. Salt bridge. H positive aqueous with the concentration again as C molar. H2 gas with the partial pressure as P2 bar. And this is platinum solid. If you look at this particular cell carefully, you have got two same electrodes first of all. So it is the concentration cell. In this concentration cell, concentration of electrolytes in both the containers is kept same. Where the difference is? The difference lies in the partial pressures. So I have kept the partial pressure different. That particular concentration cell in which EMF is generated due to partial pressure difference. Due to partial pressure difference. Okay? Due to partial pressure difference. You call that particular concentration cell as electrode concentration. Okay? Now let's make a condition for this particular cell to be working. Understand? For this cell to be working, what has to be the reaction at anode? At anode, this H2 should get converted into H2 with the pressure of P1 bar. It should get converted into 2 times H positive with the concentration C molar plus how many electrons? Plus 2 electrons. This is the reaction at anode. Similarly, what has to be the reaction at cathode? H positive should get converted into H2. So reaction has to be 2 times H positive with the concentration C molar plus 2 electrons will be getting converted into H2 gas with the pressure of P2 bar. So I got the reaction at anode, reaction at cathode. Okay. Since you got reaction at anode and reaction at cathode, now people, are the electrons balanced? Electrons are already balanced. Yes. Now add the two equations. When you add the two equations, what all things will get cancelled out? All this stuff will get cancelled out. So I'll be left with H2 with the pressure P1 gives H2 with pressure P2. Now, if I ask you to write QC expression, QC here is going to be simply partial pressure of this divided by partial pressure of reactant. So this is QC. If you got QC, what about E naught cell? E naught cell is already 0. What about N value? N value is equal to 2. Now use the Nernst equation. If you use the Nernst equation, we can say E cell is equal to E naught cell. E naught cell is already 0 minus 0.0591 divided by N. N value is 2 log of QC. QC is how much? P2 by P1. What was P2? P2 was the partial pressure of cathode, right? P1 was the partial pressure of anode. Perfect. If I remove the minus sign here, okay, so I would say this will be log of P2 by P1. Instead of that, I'll be writing log of P1 by P2. Log of P1 by P2. Now, my dear students, you can say one thing. Understand. I can say for this cell to be working, E cell should be greater than 0. Because if E cell is greater than 0, then only delta G would be negative. For this cell to be working, its E cell should be greater than 0. E cell can only be greater than 0 if this particular term is greater than 0. How can this particular term be greater than 0? This particular term will be greater than 0 only if P1 by P2 value is greater than 1, or I can say if P1 is greater than P2. What is P1 and what is P2? P1 was the partial pressure of anode and P2 is the partial pressure of cathode. So you got the criteria, partial pressure of anode should be greater than that of partial pressure of cathode. Then only EMF of the cell will come out be positive, and once EMF of the cell comes out be positive, once EMF of the cell comes out be positive, then only I would say the cell would be working. Am I clear with this? Am I clear with this, people? Quick. Can you tell me the answer of this question? Can you tell me answer of this particular question? Okay, tell me one thing. Is it a normal cell or a concentration cell? What do you think? Is it a normal cell or concentration cell? See, if you see on both the sides we have got same electrodes. If we have got same electrodes, so it's a concentration cell. Okay, number one. Number two, concentration of electrolyte in anode is kept as C2, concentration of electrolyte in cathode is kept as C1. If you look carefully, in both the containers, concentrations are kept different. Concentrations are kept different. Right? So which cell is it? Is it electrode concentration cell or electrolytic concentration cell? Tell me that first. Electrode or electrolytic? I just want that. It is electrolytic concentration. If it is electrolytic concentration cell, we know for the electrolytic concentration cell to be working, what is the criteria? What is the criteria? Concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Right? So I would say for this particular cell to be working like a normal galvanic cell, concentration of electrolyte in cathode, which is C1. I would say C1 should be greater than C2. In cathode, this is an anode. C1 should be greater than C2. Then only cell reactions would be spontaneous. Then only cell reactions would be spontaneous. And if cell reactions are spontaneous, that means automatically the moment of electrons would be from anode to cathode and moment of current would be from cathode to anode. Now we can select your options. You can select your option. The cell reaction will be spontaneous if C1 is greater than C2. This is correct. This is correct. If C2 is greater than C1, if C2 is greater than C1, current will flow. Current does not flow then. If C1 is greater than C2, if C1 is greater than C2, current will flow from cathode to anode. Current will flow from cathode to anode. This is also correct. If C1 is equal to C2, cell will not work. If concentration, if both the concentrations are same, right? There will not be any concentration difference. If there is no concentration difference, there will be no EMF generated. If there is no EMF generated, there will be no current. So D is also correct. ACD is the correct answer. Okay, ACD would be the correct answer. I hope I'm clear with this. Yeah? Perfect. All right. So let's move on then to your electrolysis part. Let's move on to the electrolysis part now. Electrolysis part. See guys, this electrolysis I'll make you understand with the help of this particular heading. Understand what happens here. See. My dear students, for example, imagine that you have got a container like this. This is the container. Okay. One simple container I have taken. Imagine this is the container, and in this particular container, for example, I have kept molten NaCl. I have kept molten NaCl in this particular container. What is molten NaCl? Would say there will be Na positives as well as Cl negatives. There is molten NaCl present in the container. NaCl in liquid state, basically. So we have taken basically NaCl solid first. Imagine we have heated up NaCl, and we have heated up NaCl till it gets converted into NaCl liquid, right? So initially I had taken NaCl solid. I have heated it up, right? I have heated it till NaCl solid gets converted into NaCl liquid, and that NaCl liquid I'm calling as molten NaCl, or you can say fused NaCl. Okay? Molten NaCl or fused NaCl. Now, what am I going to do over here is, I'm going to introduce two rods. These are the two rods which I've introduced. Okay? Now, people, these two rods I'm connecting with the external battery. That rod which I'm connecting with, the negative terminal of the battery will get negative charge, and that rod which I'm connecting with the positive terminal of the battery will get positive charge. Well, let me tell you, the negatively charged rod over here is what you call as cathode, and this positively charged rod is what you call as anode. And this particular cell which I got over here, you call this particular cell as the electrolytic cell. Electrolytic cell. The device in which electrolysis will be carried out will be called as electrolytic cell. Now, guys, what's going to happen here? As soon as negative charge comes on this rod and positive charge comes on this rod, I'll say this negatively charged rod will start attracting Na positive towards itself, because unlikes attract. Similarly, this positively charged rod will start attracting Cl negative towards itself. So I would say this Na positive is going towards cathode, Cl negative is going towards anode, right? If Na positive is going towards cathode, at cathode reduction takes place. This is going towards anode, at anode oxidation takes place. So how many reactions will be taking place here in this particular case? There will be two reactions. One reaction will be taking place at anode, one reaction would be taking place at cathode. Anode and cathode. So at cathode, I must say, at cathode reduction takes place. Na positive at cathode will be gaining an electron. Na positive at cathode will be gaining an electron and will be getting converted into Na solid, and that Na solid would be deposited here on this particular rod. It would be deposited here on this particular rod. Similarly, what happens at anode? At anode, oxidation takes place. So Cl negative at anode undergoes oxidation. When Cl negative undergoes oxidation, it gets converted into Cl2 gas, and with this, it will be giving 2 electrons. So at anode, I must say Cl2 gas is being liberated. At anode, Cl2 gas is being liberated. Well, these are the two things which you need to remember here. At anode, Cl2 is liberated, and at cathode, sodium solid is deposited. Perfect. These are just the two things which you need to remember here. Just the two things which you need to remember here. Okay? For example, if I do the electrolysis of molten PbBr2, you should be able to do it. In the container, there will be Pb di positive and Br negative. Pb di positive will go towards cathode, Br negative will go towards anode, right? Again, oxidation and reduction will take place. There will be two reactions again. Okay? So at cathode, I would say lead will get deposited. At anode, Br2 will get liberated. That's all. Okay? Mohammed Hamiz, I'll check that. I have no idea. I'll check that. Okay? Is it clear, guys? This is the easiest part here. This is the easiest part. Now see. See, guys, understand. I was taking molten electrolyte. Instead of molten electrolyte, if I take aqueous electrolyte, what happens then? Instead of molten electrolyte, if I take aqueous electrolyte, what happens then? That is the point. Before showing you the electrolysis of aqueous electrolytes, I need to show you certain reactions. One is called as oxidation reaction of water, One is called as the reduction reaction of water. One is called as oxidation reaction of water. One is called as the reduction reaction of water. My dear students, you need to remember these two reactions directly. This is oxidation reaction of water. This is the reduction reaction of water. Okay. Why am I giving you this? Before letting you know where do we use this, these are the, just a second. These are again the two series which I want you guys to remember. You call these series as discharge potential series. Discharge potential series of cations and discharge potential series of anions. See where exactly I'm going to use all this. Okay. But first of all, you need to remember the discharge potential series. See, K positive has got maximum discharge potential followed by Na positive, calcium dipositive, magnesium dipositive, etc. etc. Similarly, in case of anions, it's SO4 dinegative, NO3 negative, OH negative, Cl negative, right? Discharge potential series of anions. See, where do I use this now? See, where do I use all this now? For example, imagine that I have got, instead of molten NaCl, imagine that I have got aqueous NaCl in the container. If I have got aqueous NaCl in the container, so how many types of ions will be there? Na positive, Cl negative, H positive, as well as OH negative, because I have taken aqueous NaCl now. Imagine that these are two rods which I have introduced here. One is your, let's say, cathode, one is your anode. This is your cathode, this is your anode. And we already know these rods are basically connected with the external battery, right? Now, this negatively charged rod, it will be attracting this as well as this towards itself. So basically, I can simplify it like this. I can say both H positive as well as Na positive. Both H positive as well as Na positive would want to go towards cathode and would want to undergo reduction. Both, because at cathode what happens? At cathode reduction happens. So I would say both Na positive as well as H positive would want to undergo a reduction here. But among these two, only one will undergo reduction. Among these two, only one will undergo reduction. And that cation will undergo reduction which has got lesser discharge potential. That cation will undergo reduction here which has got lesser discharge potential. Now, Na positive or H positive, which one has got lesser discharge potential? I would say H positive has got lesser discharge potential. So it is H positive which will undergo reduction here. Similarly, this anode, at which what happens? At which oxidation takes place? This anode will try to attract this one as well as this one. So both these anions would want to get oxidized here, but only one ion will undergo oxidation. Only one ion will undergo oxidation, and that ion will undergo oxidation whose discharge potential is low. Now, whose discharge potential is low among Cl negative and OH negative? It is Cl negative whose discharge potential is low. So Cl negative here will undergo oxidation, right? Perfect. So I would say, if I ask you now, what is the reaction which will be taking place at cathode? You will say at cathode, H positive undergoes reduction. At cathode, H positive undergoes reduction. But this H positive has come from where? H positive has come from where? H positive has come from water. So you will write the reduction reaction of water. So this is the reaction which is taking place at cathode. When we are doing the electrolysis of aqueous NaCl, this is the reaction which is taking place at cathode. Similarly, what is the reaction taking place at anode? At anode, you saw Cl negative undergoes oxidation. At anode, you saw Cl negative undergoes oxidation. If Cl negative undergoes oxidation, so what would be the reaction? What would be the reaction? Reaction at anode would be Cl negative is undergoing oxidation, so 2 times Cl negative, it would be giving Cl2 gas. With it, you'll be getting 2 electrons as well. So these are the products of electrolysis which you need to remember. These are the two things which you need to remember here. That at cathode, H2 gas is produced. At anode, Cl2 gas is also produced. Okay? At anode, Cl2 gas is produced. These are the two things which I would want you all to know, to remember. Perfect? All clear, guys? All clear, all clear? So these two series are very important. So you need to remember these two series. And from this series, you can do anything. See, electrolysis of aqueous NaCl. So when we do the electrolysis of aqueous NaCl, which I was teaching you right now, Cl2 is produced at anode and H2 is produced at cathode. This conclusion you have to remember. That's more than sufficient. That's more than sufficient. Similarly, for example, electrolysis of aqueous copper sulfate. When we do the electrolysis of aqueous copper sulfate, okay, this is the reaction which will be taking place at anode, and this is the reaction which will be taking place at cathode. So at cathode, copper is being deposited. At anode, O2 is being liberated. Just the two things. Okay, just the two things. So these are the conclusions which are important and needs to be remembered. Am I clear with this? By the way, today in the Telegram, I'll give you the list of electrolytes. I'll send you a table on Telegram. Right? I'll send you a table on Telegram. Table would be like this. Here would be type of electrolyte. There will be almost 15 electrolytes which I'll be showing, which will be there in the table. 15 different electrolytes. And here will be which electrode is used, product obtained at cathode, and product obtained at anode. I'll show you this. I'll send this particular table on the Telegram. Okay? And do remember that. Do remember that. 15 different electrolytes, product obtained at anode, product obtained at cathode. Perfect. On the Telegram. Wassim Bhat Chemistry Official is the Telegram channel name. After the at the end of this particular session, I'll be sending that. Okay. Let's move on to one more thing. What is that? What is that? That is your Faraday's laws of electrolysis. Faraday's laws of electrolysis. Faraday's laws of electrolysis. See, there are two laws you must be knowing, Faraday's first law and Faraday's second law. As per your Faraday's first law is concerned, my dear students, since we saw during electrolysis, either at electrode, either metal is being deposited or gas is being liberated. We saw two things. At electrode, either metal is being deposited, or at the electrode, either gas is being liberated. These are the two possibilities. Either metal is deposited or gas is liberated. Now, Faraday's first law says that the mass of the metal deposited, the mass of the metal deposited in grams, the mass of the metal deposited in grams at the electrode, or the mass of the gas produced at the electrode, mass of the metal deposited or the mass of the gas produced at the electrode, that is directly proportional to the charge that goes into the solution because of the battery. Since the rods are connected with the battery, that battery sends charge into the solution. More the charge going into the solution, more the charge going into the solution, that means more mass of substance will be deposited or liberated at the electrodes. In short, right? Perfect. So people, I would say mass of the substance deposited or liberated is directly proportional to the amount of charge that goes into the solution. Now, if you simplify it a bit, instead of proportionality, I'll use a constant Z multiplied by Q. This Z over here is what you call as electrochemical equivalent. This is called as electrochemical equivalent, and it is equal to E divided by 96500, where E stands for equivalent mass of the substance which is being deposited or liberated. Where E stands for equivalent mass of the substance which is being deposited or liberated. See guys, let me write it like this. Mass of the substance deposited or liberated in grams is equal. Z is equal to E divided by 96500. Instead of Q, I'll be writing I multiplied by T, current multiplied by time. So this is the first result from which questions will be asked. Mass of substance deposited or liberated is equal to equivalent mass of the substance deposited or liberated, current multiplied by time, divided by 96500. 96500. Okay. The second result. See guys, mass of substance deposited or liberated in grams is equal. Instead of equivalent mass of the substance, I'll be writing molar mass of the substance divided by n factor of the same substance which is being deposited or liberated, multiplied by 96500, and this is I multiplied by T here. Okay. Take this M in the denominator over here. Take this m in the denominator. So mass of substance deposited or mass of gas released. Divided by molar mass of the same. Given mass by molar mass gives you a number of moles. So n is equal to I multiplied by T divided by n factor multiplied by 96500. So this is the result which is used to calculate moles of the substance deposited or liberated at the electrode. This is going to give us moles of the, mass of the substance deposited or liberated at the electrode. This is going to give us moles of the substance deposited or liberated at the electrode. Similarly, if you are asked to calculate volume of the gas produced at STP, volume of the gas produced at STP, how do you calculate volume of the gas produced at STP? Once you get the moles of the gas through this formula, at the end you'll be multiplying that with 22.4 liters. This is going to give us volume of the gas produced at STP as well at the electrode. Okay, at the electrode. Now directly I'm going into the questions which will make all these concepts very, very clear to you. But before showing the questions, remember one more thing. Whenever you'll be given with a balanced chemical equation like this, whenever you'll be given with a balanced chemical equation like this, for example, if sometimes I ask you to calculate n factor of A, n factor of A, n factor is simply going to be equal moles of electrons exchanged, that is 12, divided by stoichiometric coefficient, that's 1. So 12 by 1 is 12. 12 divided by 2 is 6. 12 divided by 3, 4. 12 divided by 4 is 3. 12 divided by 6, that is 2. So these are the respective n factors of these reactants and products, right? Whenever I'll be giving you a balanced chemical equation, right? Whenever I'll be giving you a balanced chemical equation and I ask you to calculate n factor of any reactant product, how you are going to do it? Moles of electrons exchanged divided by stoichiometric coefficient. Moles of electrons exchanged divided by stoichiometric coefficient. That's all. That's all, people. Okay. Why am I doing this? Have a look. The first question on your screen. The first question on your screen. A solution of aqueous copper sulfate. A solution of aqueous copper sulfate is electrolyzed for how much time? For 10 minutes. A solution of aqueous copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. With a current of 1.5 amperes. What is the mass of copper deposited at the cathode? What is the mass of copper deposited at cathode? See, guys. First of all, we are doing the electrolysis of aqueous copper sulfate. And few minutes back only we have seen when we do the electrolysis of aqueous copper sulfate at cathode, what gets deposited? Copper gets deposited. At cathode, copper gets deposited, right? At cathode, copper gets deposited. And my dear students, as per the question, we are supposed to calculate the mass of copper that is being deposited. I'll say mass of copper deposited in grams is equal to equivalent mass of copper multiplied by I multiplied by T divided by 96500, right? Equivalent mass of copper is equal to molar mass of copper divided by n factor of copper. What is n factor of copper? N factor of copper will be 2 divided by 1. That will be 2 multiplied by 96500. Current I. How much is the current? 1.5 amperes. For how much time current goes into the solution? 10 minutes. So multiplying with 60 so that it comes in seconds. So solve this. And this value will come out to be 0.29 grams. So I would say 0.29 grams of copper would be deposited at the cathode. Okay. Is this clear? Is this clear? Everybody? Is this clear? I hope this is clear. Okay, let's move on one more question so that it becomes like clear to you. Okay, look at this question. Look at this question. Look at this question. The question says 1 farad of electricity. 1 farad of electricity is passed through 10 liter of an aqueous solution. through 10 liter of an aqueous solution of NaCl. Calculate the pH of the solution. So basically we are doing the electrolysis of what? We are doing the electrolysis of, again, aqueous NaCl. And when we do the electrolysis of aqueous NaCl, these are the reactions taking place at the respective electrodes, reaction at anode as well as reaction at cathode. Due to the reaction at anode, if you see, Cl2 gas is produced. Due to the reaction at cathode, if you see, H2 gas is produced. At the same time, OH negatives are produced. Due to this particular reaction, at cathode, OH negatives are produced. OH negatives are produced. My dear students, the OH negatives which are produced at cathode, where do they go at the end? They go into the solution. They go into the solution, right? They go into the solution. So can I say, since OH negatives are continuously going into the solution at cathode, so when the electrolysis would be complete, the final solution after the electrolysis is done, would that be acidic or basic? Would that be acidic or basic? Generally, what do you see? What do you see? Tell me. Would that be acidic or basic? It's a simple question which I'm giving you. Tell me. That's going to be basic, right? What do I have to calculate? I have to calculate pH of the solution. 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 How do I do it? See guys, in order to calculate pH of the solution, I won't be considering this particular reaction. I'll be considering this one. I'll be considering this reaction. Okay? I'll be considering this reaction because this reaction is responsible for pH. What's happening to me? Okay. See guys, let's first of all try to calculate the number of moles of OH negatives which are liberated through this reaction. The number of moles of OH negatives which are liberated through this reaction. Number of moles of OH negative is equal to number of moles of OH negatives produced is equal to I multiplied by T divided by N factor of OH negative multiplied by 96500. How much current is going into the solution? It's not given. Instead of I multiplied by T means Q, right? So Q is given, 1 farad. 1 farad means 96500 coulombs. So instead of Q, I'm writing 96500. N factor of OH negative. N factor of OH negative would be 2 divided by 2. That's 1. 96500. The value comes out to be 1, right? Number of moles of OH negatives which are liberated here, that's 1. Number of moles of OH negatives liberated here, that's 1. If you got the moles of OH negatives liberated, can I calculate the concentration of OH negative in the final solution? These are the moles of OH negatives which are in the solution at the end. I can easily calculate the concentration of OH negative which is in the solution. And concentration of OH negative in the solution means moles of OH negative in the solution divided by volume of solution in liters. Moles of OH negative in the solution is 1 divided by volume of the solution in liters is 10. The value comes out to be 10 raised power minus 1 molar. Right? This is the OH negative concentration. This is the OH negative concentration which is there in the final solution. If you got the OH negative concentration, can we calculate pOH of the final solution? Which is minus log of OH negative. So minus log of 10 raised power minus 1. Value comes out to be 1. If you got pOH, can we calculate pH? pH will be 14 minus pOH. So 14 minus 1 is 15. Is this clear? Is this clear, guys? Quickly in the chats. Is it clear? Yeah? Just give me 2 minutes, guys. I'm not well, basically. I think I got fever. Yes, I got fever. I'm sweating, and the temperature right now is -2 degree. By the way, in -2 degree, I'm sweating. I think I'm going to fall ill for more than a week. We are just left with 3 more hours. That's it. 3 more hours. That's it. In 3 more hours, it will be done because solution is like 1.5 hour chapter only. I already took the medicine when I took the break. Let's wait for 5 minutes. Okay? Just notes of this session I'll be sharing on my Telegram. Okay. Notes of this session I'll be sharing on my Telegram. Guys, should we end the session right now? Can you watch the last 3 hours from this session? I'll pin it in your comment section because I don't think I can continue. Just a second, let me check whether it's here or not. Guys, last 3 hours you'll watch from here, okay? Last 3 hours you'll watch from here. I'll pin the link of this session in the comment section. The last 3 hours you'll watch from here. It contains solution also, okay? Okay, but do not create backlog. Right, once I end this session, you continue, right? It will end by 10:30. It will end. But do not create the backlog. It might look 4 hours, but it's not 4 hours. In between, I have given you half an hour. In between, there's a break of half an hour. Okay, in between, there's a break of half an hour. Okay. All right. So please watch the last 3 hours from here. And my next marathon will be class 11th in organic chemistry, and that will happen after HSP sir's class. Okay, so see, next class is Yavar sir's, then Ambika ma'am's, then HSP sir's, then comes my turn again. Okay. I'm really sorry for this. Okay. I should not have taken the class in the morning itself, but even the team had told me not to take the class today. But when I saw you guys waiting in the session, so I started the session. I thought I'll be fine. But it's okay, happens. But we'll be standing. Okay? So watch the last 3 hours from here. But do that. Okay, I'll be coming up with the next session, which will be the 5th session, which is complete class 11th in organic chemistry. That I'll be taking care of. You guys take care. And do let me know in the comment section whatever you would want to let me know. Okay? Take care, guys. God bless you all. Bye-bye.